Welcome to APEC. It's August 5th, and I'm your moderator, Tim Ventura. First, I'd like to thank everyone for joining us on this call, along with everyone watching us on YouTube. Today, Dr. Raymond Chiao will discuss spin-gravity coupling between EM and GR. Dr. Kevin Knuth will provide updates and a detailed analysis of the UAP phenomena, and our panel discussion will explore the changing narrative emerging from the US Congressional UFO hearings. We're also going to hear the latest updates from our lab partners, and we will be finishing off the event with open discussion and ad hoc presentations by conference attendees. So a couple of quick updates here. Today's event uses StreamYard. Again, we use that for APEC webinars. We're broadcasting through the Alt Propulsion YouTube channel as well as our partner channels. If you haven't subscribed, please do so now. You can ask questions using the live chat feature on the right-hand side of the page, and we will ask them to our presenters depending on time constraints. You can also always view replays of this, details, and speaker info on our website at altpropulsion.com. So without any further ado, I want to introduce our first speaker. It is an honor to have Dr. Raymond Chiao with us. He's a physicist, best known for his experimental work in quantum optics. He's currently an emeritus faculty member at the University of California Merced Physics Department, conducting research on gravitational radiation in collaboration with Professor Jay Sharping. So without any further ado whatsoever, I will bring Dr. Chiao in. Sir, welcome. Welcome. And you have a presentation for us on spin GR, let me see, entangled pair coupling. So I believe that I will have to do the back and forth on this slideshow. So what I will do is take myself out of the stream, but I can still hear you. So I would say just start presenting, and when you need me to do the next slide, just say next.
Okay. This is a talk on spin-gravity coupling via pairs of entangled electrons in a gravitational wave. My name is Ray Chiao. I'm a professor emeritus at the University of California at Merced, and this is a talk at the APEC conference on August 5th, 2023. Next slide, please. There has been a recent search for spin-gravity coupling by the authors are S.B. Zhang et al., and the title of the paper is Search for Spin-Dependent Gravitational Interactions at Earth Range, and it was published in PhysRev Letters last May. The authors searched for a spin-gravity interaction Hamiltonian of the form where X is some unknown constant that mediates the coupling between the spin S and the gravitational G field of the Earth. They found that the magnitude of this spin gravity interaction Hamiltonian is less than 5 times, oh, it's missing here, 10 to the minus 22 electron volts in isotopes of xenon. However, they did not explore the possibility of a huge enhancement of the spin-gravity interaction that arises from the entangled states of electron pairs in ferromagnetic materials. Next slide, please. Let us begin with a classical spherical model of the electron, which consists of a spinning ball, indicated in green here, of charge E, mass m sub E, that's missing mass m sub E, that's the electron mass, and a spin S, which is this red arrow pointing upwards. Now, the spin implies that it is a gyroscope, because spinning objects are gyroscopes that can be used for inertial guidance. For example, a gyroscope can point towards the North Star Polaris and can be used for inertial guidance. Here we show this green spinning ball, which has an equatorial velocity v, which carries an electrical current with it because the ball is charged. And therefore, there is a generation of a magnetic field line indicated here in purple that loops from the South Pole over to the North Pole. And therefore, there is a magnetic moment, mu, that's generated by the spin S. Next slide, please. Oh, no. Hey, Tim.
Yeah.
Problem.
You know, so, let me take a look. Okay. You have animations there. Ah, okay. So the animations are not playing in this, and I am not sure how to get those to play. We may be a little bit stuck. Is that something that you could just describe for us, do you think?
It's going to be hard. I need the equations. And
Oh, yes.
it's missing from this.
Okay. Well, let me see. You know what? Let me bring in Jeremy. Let me bring in Jeremy really quick because Jeremy's here. Jeremy, how do you think that we might be able to fix this?
What's going on? I'm trying to work
yeah,
on
he has animated equations. Actually, you know what? I know what we can do. Hang on. I bet that if I save this as a PDF.
Let's see here.
Okay.
I'm trying to streaming on. I wanted to broadcast this in the live. We're doing the live feed of the superconductors baking in this oven right behind me, our LK99. So,
okay.
I was trying to get that set up, but let me think. If
you know what,
in his equation, if you could do like a screen capture of the screen rather than, I don't know if there's a second way to do it through another party like OBS or something. I don't know what you're running, but
yeah. Well, let me try this. I'm going to remove that. I will add that.
Now, yes, now it works. Yes.
Okay.
Great.
Quick fix. Okay. Jeremy, thank you for your help, sir. Let me remove you back out. Okay. And let me see. We're on slide 4, right? Right.
Okay.
Wonderful. My apologies for the difficulties. I think we should be good now.
Okay. Can I get back now? This is a slide describing the gyromagnetic ratio of the electron, which is denoted by the Greek letter gamma, and it's defined as the ratio of the magnetic moment mu divided by the spin s of the electron. And it works out that this gyromagnetic ratio is approximately the charge of the electron E divided by the mass m sub E of the electron. And experiments have shown that this gyromagnetic ratio is minus 1.76 times 10 to the 11th coulombs per kilogram. This is a huge quantity because the mass of the electron m sub E that appears in the denominator of the gyromagnetic ratio gamma is a very tiny quantity. And it is important to note that the gyromagnetic ratio gamma and not Newton's constant G, that is the gravitational constant G, nor Einstein's kappa, that is the coupling constant that couples the Einstein curvature tensor to the stress energy tensor. None of the capital G or kappa couples electron spin to gravity and to gravitational waves. Since the range of the entangled state is very large, the scattering cross-section for gravitational waves can also be very large. Okay, next slide, please, Tim. Next slide, Tim, please. Oh, yes, here. This is a slide on Einstein's field equations, which can be written as G sub mu nu is equal to kappa times T sub mu nu, where G sub mu nu is Einstein's curvature tensor, and kappa is Einstein's tiny coupling constant. It's given by 4 pi Newton's constant, capital G, divided by c, the speed of light, to the fourth power. And since the speed of light is a huge quantity, the fourth power of it is even much larger quantity. And therefore, it turns out kappa is 2 times 10 to the minus 43 Newtons inverse. The inverse Newtons are the dimensions of kappa. And it is a very, very small quantity. And also the T mu nu on the right side of Einstein's field equation is the stress energy tensor. But note that the stress energy tensor T mu nu doesn't include the spin 1/2 h bar, where h bar is Planck's constant divided by 2 pi of the electron. So the spin of the electron is missing in Einstein's field equation. Next slide, please. Now we turn to the quantum mechanics of this problem. Consider entangled states of 2 electrons in a magnet. The total wave function for 2 identical electrons is described by psi, subtotal of 4 variables. The first is R1, which is the location of electron 1, R2, which is the location of electron 2, and then tau 1 is the spin variable of the first electron, and tau 2 is the spin variable of the second electron. This total wave function can always be factorized into a spatial part and a spinor part. The spatial part is denoted by capital Phi of R1 and R2, the 2 positions of the 2 electrons, times chi, a spinor wave function of tau 1 and tau 2, which are the spin variables of electrons 1 and 2. Now, there is an important symmetry in this problem. The electrons are fermions, and they must obey what is called fermionic exchange symmetry. That is to say, the total wave function must be totally antisymmetric under the interchange of the 2 electrons 1 and 2. Thus, if it is the case that the spinor wave function chi is an even function of tau 1 and tau 2, then that happens when the electrons are in a spin triplet state. Then it follows that the spatial wave function capital Phi must be an odd function under interchange. An example of this is when the spatial wave function is a superposition state of 2 product states of a single electron states, which are denoted by capital Phi sub p minus p of the 2 position variables. And this is an entangled state. An entangled state is defined as a superposition of the product of 2 single particle states. And it is important to note that the superposition occurs here with a minus sign in the middle. So that means that if we were to set R1 equal to R2, that is to say, if the electron 1 happens to coincide in location exactly with the position R2 of the second electron, then obviously the wave function vanishes due to this minus sign. And this is this is the Pauli exclusion principle. Okay, next slide, please. It turns out that experiments show violations of Bell's inequalities by entangled states. Now, the equivalence principle of general relativity is a local principle which relies on the locality of all physical systems. That is to say, their spatial separability. Entangled states, on the other hand, imply quantum violations of spatial separability. For example, the entangled state in a two-electron system in a magnet that was shown in the previous slide. These entangled states cannot be factorized, and so they are not spatially separable. Einstein, Podolsky, and Rosen showed that entangled states are non-local. That is to say, they are spatially non-separable. For example, a measurement of the momentum of one electron instantly leads to the measurement of the opposite momentum of the other electron in the example shown in the previous slide. However, experiments contradict Bell's inequalities that follow from spatial separability assumptions, and thus the locality of the equivalence principle is violated. What consequences does this lead to? In the next slide please, Tim, we summarize what we have learned so far, that two electrons in a magnet are in an entangled state which obeys fermionic exchange symmetry. The two green spheres here represent two electrons with spins pointing upwards, so they are in a spin triplet state. And therefore, under exchange symmetry, their spatial wave functions must be odd, which means that if one were to measure the momentum of the first electron on the left, and it were to point towards the left, then instantly at the right electron must have a momentum that's pointing to the right, and this follows from the conservation of momentum, in which the total momentum of the two electron system must be always conserved under all circumstances. Likewise, the two electrons, if one were to measure the momentum of the electron and it was pointing to the right, then instantly at a distance, the right electron would exhibit a momentum that's pointing to the left, again, in order to conserve momentum. So there are correlated outcomes of measurements in an entangled state. That leads to an interesting interaction with gravitational waves, as shown in the next slide. Next slide, please. So consider two electrons indicated in green here, with their two spins indicated in red. And I am going to try to convince you that the spins of two entangled electrons in a passing gravitational wave tilt in compass needle librational motions or tilting motions that are indicated here. So imagine that a gravitational wave comes in from the left with a wave vector k subgravitational at t equals 0, supposing that the gravitational wave has gravitational fields t, which is pointing downwards on at the plane z equals 0, and pointing upwards minus g at the same plane. This indicates that the gravitational wave is squeezing space as the tips of these two arrows are pointing towards the z-axis. Likewise, half a wavelength later at the plane z equals lambda over 2, the gravitational fields G and minus G reverse in sign such that the gravitational fields are going away from z-axis, and this shows that the gravitational fields of the gravitational wave are stretching space away from the z-axis at the plane z equals lambda over 2. This means that there will be tilting motions of the spin vectors indicated in red, and this is shown in the next slide. Next slide, please, Tim. So we answer here, why do the spins of two entangled electrons passing over the gravitational wave tilt towards each other? And we must start from the fact that spins of the electron S are gyroscopes, and they point towards freely floating dust particles indicated by the blue dots here, A, blue, and B, blue, C, blue, D, blue, such that the tips of the spin vectors point towards these blue dots, both at the tail and at the uh, at the front of these spin vectors. The spin vectors are following the motions of these freely floating dust particles. And therefore, the squeezing of space produced by the gravitational fields G and minus G of the incoming gravitational waves causes the dust particles to move towards each other at z equals 0 and away from each other at z equals lambda over 2, half a wavelength away, and therefore there results a tilting motion of the spin vectors indicated in red. But remember, the spin vectors are coupled to the magnetic moment of the electrons. And if the spins are tilting, then so must the magnetic moments be tilting. And the motion of the magnetic moments leads to the emission of gravitational electromagnetic waves because of the magnetic moment changing in time. Therefore, the gravitational wave is transduced, that is, it's converted as it passes over the two electron system. It is going to produce electromagnetic waves indicated by the wave vector k sub electromagnetic, which goes out to the right. Now, imagine that we were to take a movie of this process of transduction from gravitational waves coming in from the left and leaving as electromagnetic waves going to the right. Then, by time reversal symmetry, the electromagnetic waves, which are coming in from the right in time reversal, as they pass over the two electron system, they produce tilting motions of the spins in such a way that it generates a gravitational wave. So it goes both ways. A gravitational wave can be converted into an electromagnetic wave, and by reciprocity, the electromagnetic wave can be back converted into into a gravitational wave. It goes both ways. Okay, so next slide, please. Now, here is a possible practical implementation of these ideas. Consider putting two Ig spheres into a gravitational wave. The Ig spheres are indicated by these yellow spheres, one on the left side and one on the right side. And let a gravitational wave here shown face on, not side view, but a face on view, which can be described by these blue hyperbolas as force fields of the gravitational wave. And now consider the motion of two electrons indicated by the red dots in the presence of these force fields. The force fields along the z-axis are denoted by G, that is the gravitational field of the gravitational wave is pointing on the left to the, is an arrow which is pointing to the right on the left side of the diagram, and the gravitational field on the right side is pointing towards the left. Thus, there is a squeezing of space in between the tips of the two gravitational field vectors. The squeezing of space produces motion of the spin of the two electrons indicated in red, such that the spin vectors indicated by the red dots with the red circle around them, the spin vectors will tilt towards each other, indicated by the green arrows with velocities v and minus v, respectively. So the two spin vectors tilt towards each other, and therefore, because the spins carry magnetic fields with them, because there's a magnetic moment that's moving, the motion of the magnetic field produces electric fields, and it works out that the motional electric fields is pointing upwards on the left side and pointing downwards on the right side. And so this is how a gravitational wave is converted into an electromagnetic wave. It's via emotional EMF that is generated by the motions of the spin vectors of the two electrons. Okay, in the next slide, we show a photo of a Higgs sphere. This is a Higgs sphere whose diameter is approximately 300 microns, and it was produced in a machine that is used for polishing gems that tumbles a single crystal of Ig. That Ig, by the way, stands for yttrium iron garnet, which is a ferrite material, and produces this black sphere which you see. And this black ball that you see is a magnetized ball. It has a permanent magnetic field from it, just like in a magnet. And this magnetization is equal to the magnetic moment of all these electrons in the ball per unit volume. And so because there are a large number of electrons in this ball, the magnetization of this ball could be huge. And in practice, there are fields of the Higgs spheres that are produced on the order of 1,000 Gauss, or about 1/10 of a Tesla. Okay, next slide, please. The spins in the ball undergo spin precession in a magnetic field and leads to magnetic spin resonance. Here is a sketch of how this spin precession proceeds. In the red here is indicated the spin vector S, and the tip of this vector is orbiting in a circular orbit around the z-axis, the vertical axis, in a blue circle here. The blue circle is the orbit of the tip of this spin vector when there is a permanent magnetic field, B naught, or DC magnetic field, or remnant magnetic field due to the magnetization of the Higgs sphere. So now let's apply, in addition, an RF, or radio frequency magnetic field, indicated by the radio magnetic field B sub RF that points towards the tip of the red vector S. And if we tune the RF frequency so that it is in resonance with the motion of the spin vector, that is to say, if the tip of the red vector coincides at all times with the tip of the purple vector of the RF magnetic field, then we have what is called spin resonance, in which there is a transfer of energy from the RF or from the radio frequency field to the spins, and vice versa. There could be a back transfer from the spins back into the RF field. So there's both emission and absorption of RF radiation, and that is possible when you have magnetic spin resonance. The next slide, please. Now we describe the power emitted or absorbed in electron spin resonance. This, this can be described by an equation which equates the torque, which is given by mu cross. This diamond symbol should be a cross symbol. Sorry about the font mistake. It's mu cross B is the torque, and that is equal to the time rate of change of the spin vector S with respect to time. And so we get a differential equation, ds dt is equal to gamma S, that's the magnetic moment, mu, cross that diamond shape is again the cross product of S cross B. And this can be solved, this equation of motion can be solved, and we can calculate the power by taking the dot product of the torque with the instantaneous angular velocity of the spin vector, and taking a time average of it gives us the power. And it turns out the answer to this calculation is that the power emitted per electron is given by gamma squared, the square of the gyromagnetic ratio, times the magnitude of the spin vector S, times the magnitude of the DC magnetic field B naught, times the magnetic field B sub RF of the radio frequency magnetic field. So let's put in now some numbers. Since gamma is a very large number, gamma is minus 1.76 times 10 to the 11 coulombs per kilogram. Gamma squared is an even larger, huger number, and this allows us to do the experiment. Or if we put in now the remnant magnetic field of a typical Ig sphere, which is around B naught is around a tenth of a Tesla, or about 1,000 Gauss, and we put in B sub RF for the radio frequency magnetic field to be 6 microtesla, which is for a 1 watt of RF power applied to the system at microwave frequencies at 10 gigahertz. Then the time average power emitted per electron works out to be around 1 attowatt, or 10 to the minus 18 watts, but this is per electron, and there's a lot of electrons inside the Ig sphere. So in the next slide, we calculate, next slide please, we calculate the power emitted in gravitational waves by 2 Ig spheres. And the number of electrons in a millimole of a millimole Ig sphere is 10 to the minus 3 of Avogadro's number, which is around 6 times 10 to the 20th electrons. It's a huge number. And therefore, the total power in gravitational waves emitted or absorbed by electrons in 2 Ig spheres is around 600 watts divided by the Q of the spin resonance. Q QRF is the magnetic spin resonance quality factor. And if the quality factor, as experiments show, can be around 600, then we get that the power emitted in gravitational waves by the two Higgs spheres can be on the order of watts, a huge number. And the reason for this is because Avogadro's number is a huge number. Okay, and now we can look at it. The next slide, please, Tim. Here is a possible experiment, and we call it a Hertz-like experiment for gravitational waves. Supposing we have a transmitter and a receiver placed in two rounded Faraday cages. The left one contains inside it two antennas indicated here in orange, and they generate an electromagnetic wave which irradiates a pair of levitated Higgs spheres. These spheres can be levitated, for example, above superconductors at millikelvin temperatures, above a RF stub cavity, which makes it have a high Q, and the temperature is low, so that the quality factors here of the spin resonance can be quite high. And so the incident electromagnetic wave causes tilting motions of the spin, as described earlier, which then will radiate the gravitational wave with a wave vector k subgravitational, which leads towards the right. But now comes the crucial point. Gravitational waves are not blocked by Faraday cages, unlike electromagnetic waves. So the gravitational wave passes right through the left Faraday cage into the right Faraday cage. And in the right Faraday cage, we have placed another pair of levitated Higgs spheres with time-reversed magnetic fields and spins, which then time reversal allows the back transduction of the gravitational wave back into electromagnetic wave, which leads through the right through two antennas, again indicated on in orange on the right side of the grounded Faraday cage. So here is a very simple experiment, and remember that the powers we're talking about here are on the order of watts. So it's a very easy experiment. It's not a low signal to noise ratio experiment, so it's going to be very high. So this experiment has never been done as far as we know, but if we do it, then it leads to what I would call, I'll give it a nickname, gravity radio. That is, that we can communicate via gravitational waves in the same way that we communicate with electromagnetic waves or radio waves. And one important feature of this is that the Earth is transparent to gravitational waves. So this opens up the possibility of communicating right through the middle of the Earth, say from California to Australia, and vice versa from Australia back to California. And furthermore, the oceans are also transparent to gravitational waves, and this opens up the possibility of communicating with, say, nuclear submarines that are underneath the ocean. So there are all sorts of applications, both civilian and military, of this kind of device, which we have dubbed gravity radio. With that, I should conclude. Is there another slide, Tim? Yes. Oh, yes. Here are the conclusions of my talk. The first conclusion is that the spin of the electron behaves like a gyroscope. The spin is an inertial guidance object. The spins of two entangled electrons tilt towards and away from each other periodically with time, like two compass needles, as a gravitational wave passes over them. The periodic motions of the two spins lead to periodic motions of their magnetic moments, thus generating electromagnetic waves. By reciprocity, that is, by time reversal symmetry, gravitational waves will be generated by electromagnetic waves passing over the two spins. These pairs of entangled electrons that exist in ferromagnetic matter, like Higgs spheres, imply quantum violations of the equivalence principle due to quantum non-locality. And the Avogadro's number, a very large number of electrons in Higgs spheres, leads to watt-level emissions of gravitational wave power for spin resonance, magnetic spin resonance Qs of around 1,000, which is achievable. Therefore, a Hertz-like experiment is feasible. Is there another slide, Tim? Oh, yes, here's the bibliography in case anybody is interested. The first one I mentioned is by Zhang et al. It's a recent PhysRev letter entitled Search for Spin-Dependent Gravitational Interactions at Earth Range. The second is Bornhill et al. The senior author is Michael Tobar in Australia, and they worked on ultra-high cooperativity interactions between magnons and resonant photons in a Higgs sphere. This was published in PhysRev Applied in 2014. And finally, there's a paper I wrote a long time ago in honor of my old teacher, John Wheeler, which is entitled Conceptual Tensions Between Quantum Mechanics and General Relativity. Are there experimental consequences? And I think the answer, as I hope I've demonstrated in this talk, is yes, with this Hertz-like experiment. Okay, with that, I think I'll stop and ask for questions. Okay, Tim.
Okay, wonderful. Ray, thank you so much. So let me do this. I want everybody, you know what? I'm going to put everybody up here. And let me see. I'm going to put Jeremy up. Guys, please put your hands together and give Dr. Raymond Chiao an enormous hand. Sir, thank you so much. Thank you so much. And, you know, if you want, I can leave you guys up for now, or if you want, I can take you out of the stream. So let's do questions. Do any of you guys have questions for him? Let me add Michael in as well. Okay.
Yeah, Tim, I have a couple.
Yeah, go for it.
Thank you, Dr. Chiao, for your presentation. I was taking notes, so it's insightful. It's Michael and I had talked about the Higgs spheres a little bit, and some as it pertains to some of my research. And there was a paper at the end that I'm going to have to look up. Question number one is costs of the experiment setup. Have you looked into the superconductors and sourcing the spheres? And the second question is, how does frame dragging affect this? It was in the section when you were talking about how the gravitational waves Earth is transparent, but Gravity Probe B shows that there's frame dragging a little bit. So I'd expect that a transmitted wave might get twisted, or you'd have some aiming issues, or maybe not because of entanglement. So was cost of the experiment, and have you thought about how frame dragging affects?
Okay, well, let me answer your first question first. I think, well, let's put it this way. I got a startup grant at the University of California in Merced when they opened about 2006. and that helped me set up dilution refrigerators, and I bought 2 of them in anticipation for the Hertzsprung experiment, and that those refrigerators cost at that time around $500,000 each. So that's but they are now in the lab of Jay Sharping, my colleague at UC Merced. So that's the answer. And using these millikelvin refrigerators, one can levitate these egg spheres, and that makes them free bodies so that they are not damped by any kinds of heating motions, and so it gives makes the system a very high quality spin resonance system, I believe, but we have to show that. My colleague down in Australia, Michael Tobar, also has dilution refrigerators, and he has also done experiments on egg spheres, as I showed. And I think that we are maybe able to do either the experiment either here in California or in Australia, and on a shoestring budget, I think, maybe on the order of $500,000. I don't say. Now, your second question. Could you repeat your second question?
Yeah. Have you thought about frame dragging and how it might affect?
I have. Yes, I have thought about frame dragging, but I know of the gravity Pro B experiments that were done at Stanford, and the frame dragging effect is really, really tiny effect, and it's because of the weakness of gravity. The Newton's constant, capital G, is a very tiny constant to begin with, and frame dragging involves, I think, as I recall, some powers of the speed of light in the denominator, so it's a really small effect. Whereas the effect that I'm claiming or proposing is a huge effect, because I am not talking about using Newton's constant G to couple to gravity, but I'm talking about using the gyromagnetic ratio of the electron itself to couple to space-time, that is, to inertial space. The reason for that is that spin, as I say, is a kind of gyroscope, and therefore there's a direct coupling between space-time or inertial space and spin, and so I'm making use of that coupling, direct coupling, using not Newton's constant or Einstein's constant capital G, kappa. Kappa is also extremely tiny, but rather I'm using a huge constant to advantage, and that is using the gyromagnetic ratio gamma, which allows a much larger coupling to these effects. Does that answer your question? I'm sorry, how do you pronounce your name?
Aiden. So
Aiden, okay.
Yeah, so Aiden Schaefer. But yes, that does. I'll have to research the gyromagnetic ratio information.
Wonderful. Aiden, thank you so much. Thank you so much. Yeah, and Raymond, again, thank you as well. We have about 8 minutes left until Dr. Knuth's presentation. So let me go to Michael Perot next. Michael? And then I'll go to Jack after that, because I know Jack has a question.
Thank you so much, Raymond. That's an excellent discussion. So is the entanglement between the 2 electrons in your model required for this effect?
Oh, yes, absolutely. The whole effect is based on entangled states or correlated motions, okay? for example, in a spin triplet state where the two electron spins are vertical, then they will tilt together or away from each other like this when the gravitational wave comes by. And this correlated motion is essential to this whole effect. Yes.
So as a follow-up, then you're planning then to entangle the Higgs spheres in a similar way?
Yeah. Well, the Higgs spheres will be prepared in an entangled state by magnetizing them in the same direction. Okay, so that you have lots and lots of spin triplets. That is, electron pairs are all pointing in the same direction on the average in the two Higgs spheres.
I mean, if that room temperature superconductor pans out that people have been talking about online, would that substantially decrease the cost of this experiment?
That's an excellent question. I'm still trying to learn about the recent room temperature superconductors. I wrote an earlier paper on using superconductors as mirrors for gravitational waves, and but without a source and a detector for gravitational waves and microwave frequencies, there was no way to show or demonstrate that. But now that we have this practical, I think, method for producing microwave gravitational waves, maybe we can do a test where we can show that superconductors, in particular these room temperature superconductors, could be used as mirrors for gravitational waves. This is important because then we can make telescopes for these gravitational wave telescopes at microwave frequencies. That if we combine the ferromagnet idea with the superconductors idea.
So, and then the superconductors as mirrors to gravitational waves is due to the quadrupole moment of the Cooper pairs, right?
Well, it's a long story. Can I refer you to our many papers have been written on this? And I hope that, well, I need to learn more about this room temperature superconductors. Does anybody here, well, there's been a lot of skepticism expressed on the web for the recent results, but does anybody know what the status right now is of room temperature superconductor LK99?
We have at least one paper claiming a replication of it. I'm not so certain. We're trying to make it in my lab as well. I have one other quick question though before.
Michael, I only have a couple of
very
minutes.
Very brief. And
okay.
Also Raymond seems to have dropped. Oh, okay, cool. He's back. Very brief. Would it be possible to calculate sort of a wattage equivalent for Earth's gravitational field, assuming that the gravitostatic field is some sort of coupling with these similar states within the Earth at large? Is it possible to calculate in a similar way for gravitostatic fields what some wattage equivalent would be to cancel equal out the forces?
Oh, that's an excellent question. I would need to think about that, Michael. I don't know the answer, but it is true that Earth is ferromagnetic because of its iron core, and so one has to think about that. That's a good question. I don't know the answer to it.
Well, on that note, let me go to Jack really quick,
Okay, so, well, Michael actually asked some of the questions I was going to ask. So what happens if in your, not the mirror, but in your detector, with the spins, if it's a condensate of many electron pairs, in like a glob of coherent state, will that enhance the transduction between electromagnetic waves and gravity waves?
That's a really good question, Jack. I believe so. The answer is, I think, yes, because
I think so.
Coherence is a very important idea, as you know, and that I refer you to the paper of my colleague Michael Tobar of Australia, which introduces a notion of cooperativity in the Ig spheres, and I refer you to his paper on that.
Okay,
subject.
if you could very quickly, because I know he wants to move on. I've been approached by several very large money sources. So there's going to be a lot of money coming in. And so if you could send me a proposal for what experiments you would like to do and emphasize the applications to like Navy submarines, things like that, then I'll pass it on to the several.
Oh, that'd be wonderful, because I've been having a terrible time raising money for my research.
Yeah. So please send me as much detail as possible, and I will pass it on to them. It's at least 3 separate groups, major. We don't need government money. We don't need government money.
Okay. Oh, I see. Okay. Oh,
Wonderful.
wow. Oh, well,
Wonderful.
that's wonderful news.
Well,
Yeah.
On that note, we are at the top of the hour. Thank you to everyone, and Dr. Chiao, thank you. It is I've been following your work for over 20 years. It is truly an honor to have you speak with us. And yes, as Donis is saying, Jack Sarfati is also a legend. We have several legends with us. So on that, let's give one more applause to Dr. Raymond Chiao. Sir, now that you are familiar with StreamYard, hopefully we can invite you back in the future. And again, thank you so much. So what I'm going to do now is remove everybody else from the studio. I'm just going to take them off air, and we're going to go to Dr. Kevin Knuth. And let me see. Kevin, welcome, sir. And let me add your slideshow to the stream. I will unmute you. And so for anyone who is not familiar, I should introduce you quickly. Professor of physics at the University of Albany, over 2 decades of experience in machine learning algorithms for a wide variety of applications. Editor of the peer review open access journal Entropy, and published the landmark paper in 2019, Estimating Flight Characteristics of Anomalous Unidentified Aerial Vehicles. So, Kevin, you may not want to admit this or be aware of this, but you have become one of the primary spokespeople for UAP physics. And every time you do something in public, it goes absolutely insane. People love it. So thank you so much, sir, for presenting for us today.
Well, thank you so much for having me. I really appreciate it. It's a pleasure to be here.
Yep. And I believe you can use the back and forth button on the slide deck, and hopefully everything should work pretty seamlessly.
Okay, I see the button. All right, great. Thank you so much. Great. So I'm going to talk about the evidence that we have that does suggest that some UAPs are advanced non-human craft. This has been, of course, this has been in the news lately. And this is the big question that people have been asking for 80 years now. And we've had evidence for 80 years now. And we do know something about UFOs or UAPs. And I'm going to spend some time talking about that. The trick is you have to do some research and some thinking, both of which people don't want to do when confronted with this topic. So what am I going to do in this talk? First, I'm going to discuss some of the nuances amongst UAP hypotheses. I'm going to outline the process of statistical hypothesis testing and talk about how we go about deciding one hypothesis over another. And I'm going to highlight some of the difficulties that we have in supporting extraordinary hypotheses. This turns out to be very challenging, and I'll point out some of these challenges. And in doing so, I'll present some strategies on how we can better handle extraordinary hypotheses. And then I'm going to present evidence that some UAPs could be non-human craft. I'm not going to prove that they are. We don't have that much. We don't have that kind of scientific evidence yet to make such strong statements. But I'm going to argue that the non-human craft hypothesis should be embraced by the scientific community as a significant and rational possibility. This is not a crazy thing to think this is actually a pretty reasonable thing to think, especially given the information that we have at hand. So what are UAP? That's always the first question that I'm asked. The answer is we don't. Quick answer, we don't really know, but it's more nuanced than that. The phrase or the acronym UAP now stands for something like this: the Unidentified Aerospace Undersea Phenomena. This came from I think one of the reports from Congress. And there's some difficulties with this. Two of the words are ambiguous. Unidentified is rather ambiguous, as there's the term phenomena. And the fact that, in part, these are ambiguous because we don't know much about these objects yet, or phenomena yet. But the other problem is that this then is horribly misused to suggest that we don't know anything about these things, which is not at all true. We do know some things about UAPs. So we're going to dive into that. Now, UAPs are a class of phenomena. They're not a single thing, and that's one of the problems. I'm often asked, how do UAPs propel themselves? Well, they don't all propel themselves, and they don't necessarily have the same type of propulsion. That's like asking how a car propels itself. Well, there's diesel cars and gasoline cars and electric cars, and there could very well be, even if we consider the subset of UAP that turn out to be some kind of technology, we can't assume that it's the same type of technology that's driving the propulsion in all of these cases. Nor do we want to assume that at a theoretical discovery that would possibly explain on how some UAP might propel themselves, we don't want to assume that that is the way to do it. Think of it this way. There could be multiple ways to do this, multiple ways to propel yourself. And in fact, we want to, even if we do happen to find the theoretical basis on how some UAP propel themselves, we want to keep searching because we would maybe like to do better than they do. Let's think big. So let's do that. So they're not a single thing, and in fact, I have two here that appear to be different. This picture from Pine Bush, New York. These lights they're like Heselden lights. They appear to be like the Heselden lights. They don't appear to be craft of any kind. And the one in red from Vancouver, that is, as far as I can tell, that appears to be a seagull. I'm an avid bird watcher, and I've given descriptions of this in my talks before. So not all UAPs are the same thing, and some can be identified. So what does it mean to be identified or unidentified? This is another sticky point. Identification is observer dependent, and it's not binary. There are degrees of identification. I'm going to give a simple example here. Here's an unidentified flying object that I took a photo of. Can you identify it? Well, let's see, your least favorite science popularizer who would very possibly say, and has said, it could be anything. No, it can't be anything. That is ridiculous and wrong. It can't be anything. You can narrow down what is. You can rule out hypotheses. And in fact, in this way, you can do better. Can you identify it? Some might say it's a bird. So has it been identified? Well, some would say yes. Others would say no. I'm a bird watcher, so I would not be happy with just knowing that it's a bird. You might say it's an eagle. Great. A bald eagle, which would happen to be wrong. But you might be able to be a little more careful and say it's an eagle of the genus Haliaetus. Or you might recognize this to be an African fishing eagle, which it actually is. So identification depends on the observer on what level of identification you want it to be. If you happen to be one of these eagles, and you might want to actually identify the individual rather than just identifying the species. So there's an African fishing eagle. Similarly, we have a similar problem with the objects encountered during the 2004 Nimitz case. You cannot say that it could be anything. We can do better than that. In fact, the pilots did identify it to some degree as an object, as a craft, and as a tic-tac. So you have to really then consider in what sense is it unidentified. The fact that we don't really know what these tic-tac things are means that you might want to have a more precise identification, and that's absolutely fine. But it's not completely unidentified, and it can't be anything. So there are multiple hypotheses that we can pose for UAPs. This is a pretty thorough breakdown of mutually exclusive and exhaustive hypotheses. They're exhaustive mainly because I threw in these catch-alls that are in pink, the unknown non-physical hypothesis. So I break it down into physical phenomena, non-physical phenomena. The physical phenomena could be artificial or natural. And by including unknown catch-all hypotheses, you basically have constructed this to be mutually exclusive and exhaustive. I'm going to run through what some of these phenomena look like, or hypotheses look like. Natural phenomena, they could be animals. I've seen pictures of bats purported to be UFOs. Stars, planets, comets, meteors, clouds, mirages, sundogs, swamp gas, ball lightning, earthquake lights, and so on. Many possibilities here. Artificial phenomena could be human constructed objects that are misidentified: airplanes, balloons, drones, missiles, satellites, space debris. More interesting are the advanced human tech, Wakanda hypothesis, secret or friendly government tech, advanced adversarial tech, advanced corporate tech. By Wakanda hypothesis, I'm referring to the idea that you could have a country that is much more advanced than the rest, and then it's just not known. We could have non-human technology, and in fact, I didn't put on this list what I had on the previous slide. Way back here, I have under artificial, I have non-contemporary human tech. That is, as Jack's noting in the private chat, is actually could be from time travelers, and I do mention that in here as a possibility. The extraterrestrial hypothesis, some of these could be automated probes, remote-controlled craft or probes, piloted craft, or they could be von Neumann probes, which might even go as far as being artificial organisms. Some of these things could be non-human tech from non-humans from Earth. We have other hypotheses here that I'm just going to throw up in a different class because I ran out of room. But we could have time travelers, extra-dimensional travelers. There's been many other hypotheses made. And of course, we can have falsehoods. You can have hoaxes, pranks, and exaggerations. And you can have errors of multiple kinds. You can have delusions, mistakes, equipment malfunction, and equipment miscalibration. So there's many possibilities to consider here. So it's important to remember that UAPs are a class of phenomena, not a single type of thing. The taxa are unknown, although it's been suggested that that we have knowledge of several different types at this point. But what that means is that multiple hypotheses are likely to be found to be correct in different cases. Moreover, we should expect some confusion resulting from similar but different phenomena. This is a conflation of hypotheses. And this is common when we don't know much about a thing. It's very easy to see two things that look similar and think that they're the same type of thing. And this was discussed by Dr. Jacob Hawks Misra in his Lumina talk in February. So now, of course, we always run into this difficulty. The extraordinary claims require extraordinary evidence. And let's break this down a little bit. Firstly, this is ambiguous. What do you mean by an extraordinary claim? And what do you mean by extraordinary evidence? This is, again, horribly misused to shut down any rational discourse and the scientific study of UFOs. But we can beat through this. In science, we basically rule out hypotheses. However, in practice, you're dealing with uncertainties, and typically you test one hypothesis against another. We call this statistical model testing. And I'm not going to go through all of the details here. I had several slides in a previous talk, but I'm only including this one because I have lots of other cool things to talk about. Here on the left side of the equation, I'm comparing the probability of an extraordinary hypothesis given data and prior information to the probability of a more mundane model, which I just call M, a prosaic model. So if the extraordinary hypothesis turns out to be more probable, then that ratio is going to be greater than 1. Now, using the sum and product rules of probability theory, you can break this into a few factors. The first ratio here is it's a ratio of prior probabilities of the two models. It's what you know about the extraordinary hypothesis before you have any data, the probability that you believe that that's true without data, and the probability that you believe the prosaic or mundane hypothesis is true without data. So what do we mean by an extraordinary claim? An extraordinary claim is a claim such that the probability for that extraordinary claim is very small. So I'm using this Greek letter epsilon to be a very small number. So then those ratios typically very small for an extraordinary claim. Now the next factor is another ratio, which are a ratio of likelihoods of the data given the model. So we have the probability of the data given the extraordinary hypothesis in prior information compared to the probability of the data given the mundane model in your prior information. And so for the left side to be much greater than 1, the ratio of likelihoods is going to have to be a very large number, which I'm writing as 1 over a very small number. And that's what we mean by extraordinary evidence. So an extraordinary claim which has a very low prior probability is going to need extraordinary evidence which has a very, very high likelihood to be that extraordinary hypothesis. This is why people constantly insist on having a smoking gun evidence. And I've often wondered what would that look like. I suspect that you could have a UFO land in Times Square and you'd have to drag a living alien off of it, kicking and screaming on live television, and people still wouldn't want to believe it. So we find that the evidence that's required in these situations when the extraordinary hypothesis is considered of a very low probability is almost unreasonable. So Sagan's aphorism has been stated many times before, much earlier. This is a very nice statement by David Hume, which sums it up. And he says that no testimony is sufficient to establish a miracle unless the testimony be of such a kind that its falsehood would be more miraculous than the fact which it endeavors to establish. So basically, the extraordinary hypothesis is going to need the likelihood that the extraordinary hypothesis isn't true would have to be more miraculous than the extraordinary hypothesis itself. So for an extraordinary hypothesis that's deemed sufficiently improbable with a very small probability of being true, there's almost no amount of data that will make the extraordinary hypothesis more probable than the hypothesis that the data are in error. And we see this all the time. And we've now named this in another paper that I've written. We call this denial of the anomaly. So when scientists encounter an anomaly that goes against their concepts of what they believe to be true about physics, they just say, well, the data has to be wrong. Just summarily dismiss all of the data, which is not rational thinking. You can't just summarily dismiss a pile of data. You have to actually look at it and come up with reasons why you should dismiss it. So in the case where we don't expect to have smoking gun evidence, how do we handle studying UAPs? First, so this is a recommended strategy. First, reduce the probability of error. We need multiple independent, disparate pieces of evidence modeled after what we call multi-messenger astronomy, many different instruments and imaging modalities, multiple observation points, and multiple independent groups. This basically breaks the problem into multiple independent problems and gives you more power. Also, you can divide and conquer the extraordinary hypothesis and break it into smaller hypotheses that deal with just aspects of what you're studying that are less controversial. That means that the probability that aspect is probable is much greater than epsilon, and you have a better chance of proving that aspect is true. And once you've done that, you basically prove the extraordinary hypothesis in pieces again. And then the last strategy is to remain agnostic with respect to the hypotheses. You study the characteristics of what you're studying. You look at phenomenology, and you study the implications for the set of hypotheses. So this is the approach we're going to take. So what kind of characteristics do we have? Well, let's start with the 5 observables from the ATIP program. We have positive lift, sudden or instantaneous acceleration. It's not really instantaneous. It is just faster than you can measure. Hypersonic velocity without signatures, transmedium travel, and low observability or cloaking. Those are the 5 observables. And already those are suggesting, we'll break these down, but clearly these are already suggesting non-human tech. So how extraordinary really is the non-human tech hypothesis? Let's revise our priors a little bit. Charles Fort, born on August 6, 1874 in Albany, New York. Tomorrow will be his 149th birthday, and he's from Albany, where I am right now, which is interesting. He wrote one of the first books talking about UFOs in the Book of the Damned, and he wrote an editorial for the New York Times where he said, and my slide button is covering that up. On September 5th, 1926, he wrote, "It is not the conventional or respectable thing upon this earth to believe in visitors from other worlds. Most of us could watch them a week and declare that they were something else, and likely enough make things disagreeable for anybody who thought otherwise." So there we go. 100 years ago, he was already suggesting this hypothesis. Well before Roswell or Trinity. 1947 was, as we know, was the year that UFOs entered at least America's social consciousness. We had the purported crash in Roswell. We had the sightings by Kenneth Arnold and those in Puget Sound. There was actually a lot more going on. 1947 was pretty remarkable. This is a histogram of daily UFO sightings from the summer of 1947 from Ted Blecher. And you can see there's this 2-week period that peaks at the end of June and beginning of July, which overlaps Kenneth Arnold's sighting, which happened right at the end of June. And this is really pretty remarkable. If you just fit this to a Gaussian here, you find that the that peak is about 21 sigma above background. That's to detect a particle in particle physics, they have very stringent restrictions. You need 8 sigma. Oh, this is 21 sigma. What the heck happened during those 2 weeks? This wasn't just, now, of course, to evaluate whether this is social hysteria, I'd need to be a sociologist. I'm not a sociologist, so somebody would have to look at that. But I don't think that's the case, because we have lists of what the other sightings were. And they're pretty remarkable. There was a lot going on during those 2 weeks. You had 2 crashes in New Mexico, Roswell and the San Agustin Plains crash, all within that 2-week period. July 3rd, you had the landing of 8 large objects with 10 witnesses in Idaho. July 4th, you had 35 objects in 3 formations, which 60 people in Twin Falls, Idaho saw. There's a lone disk in the sky witnessed by 200 people in Spokane, Washington. This is all July 4th. 2 groups of disks, an entire United Airlines crew along the Idaho-Oregon border witnessed those. You got disks over Portland, Oregon with dozens of police and people. Air-to-air sightings with 2 pilots in California and Idaho. A photo taken by Coast Guardsmen in Washington. Disk over Lake Pontchartrain in New Orleans. 20 disks over Port Huron, Michigan with multiple witnesses. I'm only listing a few of the sightings here. You can see how many there were on those days. You're talking about 160 sightings. July 5th, you've got a propeller-shaped object witnessed by 2 TWA pilots in Ohio. July 6th, the B-26 pilot and crew observe a disk pacing off its left wing over Clay Center, Kansas. Hynek labeled this as astronomical. You've got a landing near Tempe, Arizona, and a landing near Pocatello, Idaho. This is remarkable. What happened in July of 1947? I would love to know, and maybe this needs to be looked at more carefully someday. But something happened. Something important happened. And it changed things. It changed the fact that UFOs became part of America's consciousness. And during that week, the last of the 2 weeks, you had ridicule and ridiculous explanations begin and continue to this day. This is when the ridicule all started up. And the question really is, why was the extraterrestrial hypothesis deemed to be so silly? If you think about it, 1947 is 10 years before Sputnik was launched. So we didn't even know space travel was possible at this point. Some scientists knew it was possible or figured it was, but this was not conventional wisdom. We also didn't know what the other planets in our solar system were actually like. We knew about their atmospheres through spectroscopy, but we didn't know anything about their surfaces. And we also didn't know that there were other planets around other stars until the early 1990s. So we were in a state of extreme ignorance about what the universe is like in 1947. And so the extraterrestrial hypothesis was deemed to be silly. At this point, we're much more knowledgeable about things. And I don't think that the extraterrestrial hypothesis should be silly at all. So we're going to look at some of these characteristics and look at the implications that they have for the set of hypotheses. And I mentioned this already. So I'm going to talk briefly about sudden and instantaneous acceleration and hypersonic velocity without signatures. In the paper that I wrote with Robert Powell and Peter Reale from SCU in 2019, we studied a number of cases, and especially in the Nimitz case, when we have the reports from Kevin Day, who watched on radar these objects dropping from 28,000 feet to sea level in 0.78 seconds. You can estimate, if you estimate the accelerations, you come up with numbers about 5,000 Gs. 5,000 Gs is crazy. And maximum speeds approaching Mach 60. So this is about 45,000 miles an hour. Now, to put this in perspective, 45,000 miles an hour is about as fast as the New Horizons probe flying to Pluto is going, or that flew to Pluto is now traveling. So I often chastise people who say, why does everybody think these are spacecraft? Well, the reason is simple, because they go as fast as spacecraft go. We're familiar with how fast jets go, and you can tell when something's going faster than a jet airplane. And most people can tell this, so it's obvious. What's more shocking is computing the power. So once you know the acceleration, we can compute the power. Power is the force times velocity, which you can break down as the mass times the acceleration squared times the time. And the power to accelerate the tic-tac at 5,400 Gs to complete that maneuver in 0.78 seconds comes out to be about 1,000 gigawatts. That is more than 10 times the total nuclear output of the United States. I'm going to say that again, because that really needs to sink into people's heads. We did make some assumptions here. The mass of the things were estimated to be about as big as an F-18. F-18 is something like 14,500 kilograms in mass. We took the mass in this calculation to be 1/10 of that mass. So we dropped it an order of magnitude. So we're being conservative here. And this conservative estimate comes out to be 1,000 gigawatts, which is more than 10 times the total nuclear output of the United States. Why would anyone think that this is human tech? Oh, they were probably just balloons. No. Look at those numbers. Do the math. Now, it's not clear how, we can go back here. It's not clear how one would do this. And it's very possible, as Dr. Sarfati's noted, that it could be that these things are using some kind of warp drive or some kind of technology that performs these maneuvers with much lower power, and that's possible. There's some reason to believe that's not the case. And in some cases, some examples of UAPs, remember, they're not all the same thing. But I'll point that out in a future slide. Now, this is nothing new. This should not be a surprise to anybody who's been paying attention since the 1940s. Hermann Oberth, who's the German father of modern rocketry, he was the mentor to Wernher von Braun. He gave a talk about unflying saucers in 1954. And he writes, their speed is sometimes very high. 19 kilometers a second has been measured. By the way, that's Mach 55 or 42,500 miles an hour. With wireless measuring instruments, radar, accelerations are so high that no man could stand it. He said, if there would be only 3 or 4 measurements, I would not rely upon them. I would wait for further measurements. But there is existing more than 50 such radar measurements of these objects traveling at very high speeds. This has been known since the 1950s. So to suggest that this could be Russian or Chinese tech is not reasonable, because they've been seen since the 1950s and been observed with these flight characteristics since the 50s. Another example, radar observations at Minot Air Force Base in 1968. There were 2 glowing UFOs observed at Minot Air Force Base in North Dakota, which supports nuclear ICBMs. At 3 a.m., an approaching B-52H was alerted to watch for bright glowing UFOs. During a 180-degree turnaround, both ground and B-52 radar systems detected an object maintaining a 3 miles distance from the airplane and following its descent rate. Within one 3-second sweep of the radar, the UFO closed 2 miles distance, positioning itself only a mile away from the airplane, pacing it for 20 miles. The plane banked and flew over the UFO, which was egg-shaped and glowing like molten lava. you can estimate the acceleration in this case. Claude Power did so in a paper that he wrote in, what's the year? I'm thinking it's 2005. Yep, that's correct. I'm having trouble seeing because my slide advance buttons are overlaid on part of my slide. So he estimated the acceleration to be 209 Gs with a top speed of Mach 12, or 15,000 kilometers per hour. The JAL 1628 case, in which you had 747 followed by a large UFO estimated to be the size of an aircraft carrier for approximately 50 minutes. We summarized this case, just summarized the behavior of the object and used that to get a ballpark for the accelerations. However, Dr. Combe obtained and more carefully analyzed the radar data of the UFO's motion. And he found, in his book, he published that he analyzed 11 jumps made by the UFO across the path of the 747. And 3 of these jumps had accelerations exceeding 9,000 Gs, with top speeds of Mach 350, which comes out to about 269,000 miles an hour in the air without sonic booms. So this really does suggest something extraordinary. The warp drive idea is on the table, of course. To put this in perspective, at 269,000 miles an hour, the UFO could reach the moon in 53 minutes. So all this histrionics of our 300-foot rockets with nuclear bombs amount of fuel just roaring into space and taking 3 days to get to the moon, this object could have done it in 53 minutes without a lot of drama. Amazing. So we've got hypersonic velocity without signatures. There are no booms or fireballs. These accelerations are on the order of thousands of Gs. They've been tracked at hypersonic speeds, ranging from Mach 12 up to Mach 60 and even Mach 350. So again, amazing speeds. There is no energy deposition when decelerating or stopping. These are all clues as to how these things are working, as have been noted in the chapter that's continually running here. The 2004 Nimitz drop maneuver should have deposited at least 4 times 10 to the 11th joules of energy, which is about 100 tons of TNT. You've got to get rid of this energy of motion. That energy has to go somewhere. That's something like, I think we estimated something like 250 cruise missiles going off simultaneously. That's not observed. So something else is happening. Now, this is very anomalous. This goes against our typical knowledge of physics. And what is then typically assumed is that the data all has to be in error. Just most scientists will just summarily dismiss all of the data. Well, know what you're dismissing before you jump on that bandwagon. You should be looking at the data. We have radar data of some of these cases, and you can estimate these speeds and accelerations pretty reasonably. Herman Oberth, back in the 1950s, did the same apparently with 50 radar data sets and came to the same conclusions. So this has been known for a long time. So extremely high acceleration speeds and power rule out natural phenomena as well as advanced human tech. Moreover, the high acceleration is consistent with spacecraft. If you plot a ship's speed in the vertical axis versus time under a constant acceleration, at 100 G acceleration, you can get to 90% the speed of light in a week. That's a nice spaceship. 1,000 Gs, which is still 5 times less than what we measured in the Nimitz encounter, and 10 times less than what we measured, what Dr. Quampi measured in the JAL encounter, you can get to 90% the speed of light in 17 hours, less than a day. This puts the whole galaxy within reach, considering time dilation. So, and if you are operating something like warp drive, then even better. So these are not, so as I put in the paper, as we wrote in the paper that we published in 2019, we said these are not only does the Tic Tacs have the characteristics of spacecraft, but they have the characteristics of exceptional spacecraft. And unfortunately, Kirkpatrick from Arrow stated to Senator Gillibrand in May during a hearing that there have been no papers published suggesting that this is non-human tech. That is simply not true. James Safadi points out there is no time dilation with warp drive. That's exactly why I said that if you're using warp drive, even better. If you aren't using warp drive and you're just flying relativistically, the galaxy is still within reach because of time dilation. But if you are using warp drive, you can get home in time for dinner, which your family will appreciate. So again, extremely high accelerations and speeds favors the non-contemporary human tech hypothesis. I should make this bigger here. This is an older slide. Now, this is an interesting one that in putting a paper together on this topic, I wasn't aware of this. Luminosity. There have always been a few photos of UFOs that always puzzled me, and I just thought, that has to be fake. That's just weird. Here are 3 of them. Some UAP are extremely luminous, so much though that many of the photographs are difficult to imagine and interpret. So here on the left, you can see there's a bright ellipsoidal shape on the right-hand side of the frame. This photo was taken in the Canadian Rockies in Alberta by a Royal Canadian Air Force pilot in 1956. The center one was taken at the Salem, Massachusetts Air Station in 1952, and the one on the right was taken at Holloman Air Force Development Center in New Mexico in 1957. All of these objects are extremely luminous, and I'll be honest, I always thought that they were just weird and probably not realistic. Instead, I now think that that's wrong and that we can learn something from these. Now, Dr. Bruce Maccabee studied the 1956 Royal Canadian Air Force photograph, and Dr. Jacques Vallée summarized and published these results. Again, you can use a variant of the camera equation to estimate the luminous power of the object. And if you actually have the photograph, you can go and microscopically count the grains to figure out what the exposure level was and use information such as the shutter time, the f-stop, and so on to estimate the luminous power. So there's a few things in this equation. This exponential up at the top takes into account the optical thickness of the atmosphere and the angle at which you're viewing. This T is a transmission coefficient through the camera to account for loss in the camera, and this cosine beta to the 4th is a camera effect from being off center. So the object is off center, and the brightness of an object, I don't know which term would be best to use there. The terms used in optics are confusing at best. So the brightness of objects basically falls out as a cosine of the angle, this angle beta to the 4th power. So objects near the periphery are actually dimmer than this. So if you were to photograph a flat field with your camera, a flat field being a perfectly uniform brightness object, you would see that the camera image would drop off and dim near the edges. And that's where that term comes from. So taking this all into account, you can estimate the luminous power of this object. Dr. Maccabee measured the exposure level be something on the order of 10 to the minus fourth joules per centimeter squared. The shutter time was estimated to be about 125th of a second. And that gives you a radiance of about 2 watts per steradian per centimeter squared. And then once you have an estimate of the distance between you and the object, or the observer and the object, which was possible here because they knew where the cloud level was, the luminous power output was estimated to be between 2,500 and 30,000 megawatts. There should be gasping in the audience at this point. Thousands of megawatts of luminous power. What is going on here? This is amazing. This again is on the order of a nuclear power plant. So you need a nuclear power plant to basically put out the light that this thing's making. And that's it. It's astonishing. And that's why these things look strange. Good question from Dr. Sarfati. How come there's no heat? Oh, there is. There's some other cases. There's a case that Jacques Vallée was telling me about just 2 weeks ago. I met with him, and he was telling me about a case in Arkansas where a physics professor was driving down the highway and saw an object in the forest that was extremely bright. And it washed out his headlights. And using that, he estimated the brightness of the object to be about 500 megawatts. And he probably rightfully decided, I don't want to go this way, and turned the car around. His family was in the back and drove the other way, took a different way home. Later, that site was investigated, and the landing site was found in a clearing in the woods. The trees were scorched and basically charcoaled, presumably from the light from this object, because it was just the sides of the trees facing the clearing were basically turned into the charcoal. And so it really does look like it was the light from this thing was actually just burning the trees. Really remarkable. So other estimates that Jacques Vallée published give you ranges from tens of kilowatts to 500 megawatts. These powers are on the order of a nuclear power plant. And as in the case of their maneuvers are, what did I say, 10 times more than the nuclear power output of the United States. So the engineer really ought to ask, what is the purpose of emitting hundreds to thousands of megawatts of light? Why would you need to do that? The only thing I can think, I don't see any necessity, I don't see any utility in that. Maybe if somebody else does, I would like to know. But what I would guess is that the light very possibly is a byproduct of something else that they're doing, possibly the propulsion system. It's been noted that these things sometimes change color when they're accelerating, and so possibly the light is a byproduct of the propulsion system. But then you have to ask yourself the question that it's shocking that wasting megawatts of power in light as a byproduct is somehow an acceptable loss. This means that they're operating with power levels that are just way beyond anything we're capable of. And that's what makes me wonder about the idea that the warp drive is low energy. Like, if we're putting out thousands of megawatts of light power as a byproduct, then the warping of space probably isn't being done with low energies. But again, there are different types of craft, and these craft could be using different propulsion systems, and they could be working in different ways. So there might be multiple mechanisms for propulsion and multiple types of byproducts and so on. So again, we have more evidence that this is non-human tech. Here's another characteristic, transmedium travel. I can't run a video because I had to upload a PDF, but this is from the Aguadilla UAP. It basically flies out over the ocean and then drops into the water. The people at SCU did an analysis of this and show that the UAP barely slows down. It enters the water at a speed just over 100 miles an hour and drops down to about 85 miles an hour. So it's not a very significant change of speed. And this, again, argues for non-human tech. Now, it's important, extremely important, to not just focus on UFOs since 2004. I think that there's a lot of political reason to do this because of cover-ups that people might get in trouble for. But there's a lot of information out there. And to learn, we have to look at all the information. So let's do that. Transmedium travel of UFOs have been observed and recorded for over 140 years. Here are some sightings at sea. May 15th, 1875, in the Persian Gulf, the ship full tour saw two large spinning wheels, 40 in the air, 40 meters in diameter. You have in March of 1887, the Dutch ship Barkentine witnessed two strange objects fall into the sea. November of 1887 in Newfoundland, you have an object emerging from the water, hovering near the ship, and then speeding into the sky. This has been going on a very long time. This is not a 20th century myth or legend, as some people have called it. These things have been observed for centuries. And this, again, rules out both natural phenomena and human tech. Skeptics often ask, why are there never any physical traces of these things? Well, there are. I'm going to speed through a bit of this because I'm running low on time. It's a long talk, a lot to talk about. So we have a few prominent landings. The farm outside of Delphus, Kansas, where a UFO hovered above the ground, leaving physical chemical traces. Westall High School in Melbourne, where many students and a teacher witnessed a UFO land near the schoolyard. South Korea, two UFOs observed to land near a school in 1973. And then there are some reports made in Kometa, where you had one case of very strong, what appear to be very strong electric fields, where the grass all stood up on end as the object took off. And you can estimate the electric fields in this case. So here the Delphus landing is probably one of the most famous in 1971. A large object with blue, red, and orange glowing surface was hovering above the ground, and there was this bright glow between the object and the ground. The object passed over the shed and took off, and left traces in the soil. This was extensively studied by Dr. Iro Farouk. Here's a photograph of the landing site. I have a few more photographs. Irma Johnson ran and got a Polaroid 104 camera and took this picture. It was like a crystallized crust on the soil, and the soil had an unusual odor. And when you touched it, it produced a sensation similar to an anesthetic, which had some persistence. So this was the photograph the night of in 1971 in the upper left. Just below that is the next day, a photograph taken by police officers 10 hours later. And then again, on the photograph on the right was taken by Ted Phillips from MUFON in December, about 5 weeks later. There's also snow in this picture, so it's the ring material and the snow is a bit conflated in the picture. So the ring material was extremely hydrophobic, extending to a depth of 14 inches. It contained oxalic acid as well as higher amounts of potassium, copper, and manganese. And the possibly accounting for some of the chemoluminosity. And so we have chemical traces that have been studied and published, again pointing to non-human tech. Westall schoolyard landing. You had approximately 200 students and teachers witnessed 1 to 3 silver discs fly over the school and land in a patch of trees just beyond the school property. 3 girls went over to the fence to find the UFO. About 40 minutes later, Army and Air Force personnel arrived and cordoned off the area. One of the teachers, Mr. Greenwood, snuck into the area to see military personnel with equipment around the landing circles. So here's where we go a bit further. And some skeptical scientists are going to maybe balk at this, but we have to look at all the information. And it stands to reason that if some UAPs are advanced non-human craft, then it stands to reason that the possibility exists that some may have encountered this non-human intelligence. Numerous reliable accounts suggest that this has indeed occurred, and these accounts give additional credence to the hypothesis. You can look down here to see this. All right, good. So here's some purported encounters with non-human intelligence associated with UAPs. We have the Bawaiian mission UFO encounters in Papua New Guinea, where you've got 40 people witness a UFO with 4 men standing on an exterior deck. The Socorro landing in New Mexico, where Sergeant Zamora witnessed a craft with 2 small people, and the Ariel School landing and encounter in Zimbabwe, with about 60 children witness at least 1 craft and interact with the entities. This sighting in New Guinea is interesting because it happened over several days, and one of the observations lasted for about 4 hours. This isn't something that you just mistakenly see quickly. The thing hovered there for 4 hours. That's hard to blow off. I'm just going to go over these rather quickly because I'm running out of time here. The Socorro, New Mexico landing by Lonnie Zamora, which most of you are familiar with. Dr. Kumbi, in his limited talk, did a careful analysis of the ground impressions and estimated the mass of the UAP to be on the order of about 1,700 kilograms, and the masses of the bipedal beings to be on the order of 41 kilograms, basically typical of an 11-year-old boy. So the footprints are consistent with what Lonnie Zamora reported. And then, of course, you have the Ariel School with 60 children. You have impressions in the grass where the craft landed, which were photographed by investigator Gunter Hofer. And drawings from the children, which are, again, interesting and compelling. So this is a nice quote, an interesting quote from Emma Christensen, one of the children. There's a picture of Emma in the lower right with her drawing in the upper right. And she said, you have to see it to believe it. If somebody's a staunch believer that it is not, how is me telling them my experience going to change what they think? It will change what they think about me. It's not going to change what they think about the universe, and I don't need that. But with 60 of us all saying it together, that will change what that one person thinks about the universe. So we have all these hypotheses, which we've pretty much ruled out a number of these except for the non-human technology one. The evidence really does rule out the other hypotheses pretty easily, to the point where you have to admit this is obvious. If you look at it, it's obvious. The problem is that most people have their heads in the sand, don't want to look. So, in conclusion, UAPs are a class of phenomena apparently varied and complex. We should expect some confusion and conflation of similar yet different phenomena. We need many examples of independent data sets with multiple instruments. We really can't ignore witness testimony, but you have to handle it with care. Use some common sense. We cannot ignore witness accounts of high strangeness. These are all important clues as to what's going on here, and these phenomena are strange. Some UAP are partially identified by witnesses as non-human craft. This is supported by extreme accelerations in speed without signature, supported by extreme observed power, both maneuvers and luminosity, and supported by multimedia travel, witnessed many times for over a century. The scientific community must accept that the non-human extraterrestrial hypotheses are not unreasonable. Of course, more evidence is needed, especially if you want to understand them in some detail. I claim that the non-human tech hypothesis is not just possible, but probable. And that's an important thing to recognize. And last, with us all saying it together, that will change what that one person thinks about the universe. So thank you very much. There's a bibliography for anybody who ever wants to claim that this stuff has never been published. Oh, yes, of course. They're not all peer-reviewed papers. This one is. Look, peer review it yourself. Get your brain work. Use your brain, so it isn't peer reviewed. You can still read it and you can still think. I have a really hard time with scientists who are unwilling to think. I have a lot of disdain for that, and it's problematic. So this whole it's not peer reviewed, so I'm not going to look at it. That's bullshit. Get your head out of your butt and read the paper and think. Use your brain. You can evaluate this. And if you're not able to, you can probably find a friend who can. So there we go. Now you know how I feel about things. Thank you very much.
Wonderful. Kevin, thank you so much. Thank you so much. So everybody, what I'm going to do is I want to put everybody up here. I'm going to put Jack. I'll put, let me see, Dr. Ansbro, Jared Yates, Gary Voorhees. And guys, let's do this. Everybody, please put your hands together and give Dr. Kevin Knuth an enormous applause. Okay, and sorry, we're getting background noise from a couple of them. Okay, so I guess one thing I wanted to ask guys was, I guess we should probably take a vote. Do you guys want to do a Q&A? We are at the top of the hour. We're at the end of Dr. Knuth's presentation. Yeah, Jared is, okay. So maybe the eyes, maybe do like half an hour, if that's okay. Kevin, if you're open to it.
Yeah, I can do that.
Okay, it's entirely up to you, sir. But I again, it is an honor and a pleasure.
I'm pleased to be here. Thank you.
And let me.
Yeah, why not discuss this? It's important to discuss these things, and these things are confusing. They're very confusing because there's a lot of unexpected.
There are, and we have some panel
it's hard
members.
to get your head around it.
Okay, so I'm clearing out our studio a little bit. And let me see. Okay, we have some panel members that are trying to come in. So I had to clear at least one person. We have one more who should be joining us. And again, my apologies. Okay. So, yeah, we're clearing things out a little bit. And the person who's going to come in, Gary Stevenson, I guess, is trying to join. Gary, give it another try if you're watching. So let's do this, guys. Let's do Q&A. Who wants to go first? With Jack, go for it, sir.
Oh, you're muted.
Oh, yeah. Sorry.
Can you hear me? There has to be something wrong with this, this camera thing you show with the 30,000 megawatts, because how can you have 30,000 megawatts being radiated into the atmosphere, over what period of time? How many joules is that?
It's a crazy amount of energy. Yeah, I agree.
Yeah. So,
I mean, this is the difficulty, though, right? Avi Loeb and Shankar Patrick would say the same thing about these things barreling through the atmosphere at 45,000 miles an hour. You should be having fireballs.
That we understand. That's warp drive explains that.
Right. But now we have another thing to explain. I
agree. I don't know.
So this luminosity, they are. I mean, the reports are consistent with this in that they're extremely bright. People get their eyes injured and they have injuries to their vision.
It can't be that bright. It can't be as bright as you calculate. So there's something wrong. I don't know what's wrong. I don't.
Yeah, I don't either. Yeah. Right. I mean, the estimate was from 6,000 to 30,000, but that's a factor of 5. That's not enough. Yeah. You need to. Yeah. That's still a lot of energy.
That's a problem that has to be dealt with. That's thanks. I didn't know about that. I can tell you a couple of things. I was involved with a man. He unfortunately he recently died, but he worked with his father was an associate of Kevin Arnold. And he was a child that is up in Utah, I guess, and he was actually present when Kenneth Arnold landed and had seen the 7 sources and was telling his father about what he had just seen. So he was a direct witness to that.
Oh, that's cool. That's amazing.
Okay.
Okay.
I think there are some physical effects that are really hard to understand here. And then there are some of the high strangeness effects are also equally bizarre, or more bizarre. And we have a lot to learn, I think. This is a lot of discoveries here.
Okay. And we have a couple. Yeah, there we go. Okay. Sorry about that. And yeah, we have a lot of folks in the studio. We have a lot going on right now. Here, let me put Bernie back in. Sorry. It's the blessing and the curse of StreamYard. I love
I
this
don't
platform.
need to be here though if you need extra space. I'm just observing and soaking it all in. It's excellent.
Okay. Well, thank you, Bernie. Thank you. And Bernie is actually one of our media partners. He has his own channel. We are streaming on his channel as well as Jeremy Reese channel. So who else has questions? I think Jared does. Go for it, sir.
Excellent presentation, Dr. Knuth. Very exciting.
Thank you, Jared.
You talked a lot about the different energies that we're seeing here. I was wondering, do you see any way that we could achieve these kind of energy densities without antimatter?
I don't know. I think we have a lot to learn here, and it looks like Jack has got something to say. He might have some ideas.
I have a model based on Einstein's general relativity, and if you communicate with me, I'll send you the math, which we don't need a lot of energy at all. No, I'm not talking about this luminosity thing. That's an anomaly. I don't know about that. But I claim the Tic Tac, everything the Navy is seeing, you can do with very small amounts of energy, and we're very close on being able to reverse engineer that ourselves in the laboratory.
Could you provide an order of magnitude for that energy?
Well, it's say like a Tesla battery, like the battery in a Tesla car, like that.
Because I remember Ricardo Storti doing some calculations for me, and he was showing that in order to get any kind of metric engineering, you would need something on the order of minimum 0.5 gigawatt, if not much. Well,
much more. You would need more than that. That's the whole problem that Ray Chiao actually showed, but he showed K. The K, Einstein's K, is like a 1/10 to the 43 newtons. That's very weak. The problem is, the idea is that you have to increase the magnitude of that coupling in Einstein's equation by many powers of 10. So what I'm claiming is that the U.S. Navy, the 5 observables, for example, that Kevin gave, that is smoking gun evidence that such a technology is operational. That doesn't mean we know how to do it, but it's operational. And in the same way, for example, 1942, 41, everybody knows that a nuclear bomb is possible. Ever since Lisa Meitner in Berlin, I guess 1936, they all knew it was possible. And but to convert that fundamental physics understanding into an operational technology, that was the Manhattan Project. And of course, Hitler tried to get Heisenberg to do it, and they failed. So that's the point I want to make. Claiming we understand in principle, theoretically, mathematically, it's very easy to make a mathematical model to explain why you don't need a lot of energy to understand what the Navy is reporting, what Commander Fravor is reporting, for example. You don't need a lot of energy in principle, but how to actually do it, that's the problem.
Well, and if I could jump in really quick, I'm not sure if you guys are familiar with Jared, but Jared does impeccable research. And he did a presentation on the TR3B where he did research into all the fundamentals, and it was amazing. So he would actually probably be a good resource, to collaborate with in the future. I'll just put that out there for you. So,
okay.
I got a question for you, Jack.
Yeah. Oh, go ahead. Go ahead.
Oh, Gary.
Right,
and welcome, sir.
Hey, thank you. Can you guys hear me okay?
Yes.
Yeah.
Okay. So, Jack, you say you could use the amount of power that would be like in a Tesla battery for a Tesla car, I'm assuming, right?
Yeah.
All right.
Yes.
So how could you possibly achieve that if there's even if there's the mass of the object itself would have to be almost non-existent for you to use that little power?
No,
So
mass. No, that's misconception. That's not physics. That's not real physics.
No, I'm not a physicist. That's why I'm asking, because I know it's directly
the mass
proportional.
doesn't.
You're
The mass
moving
doesn't.
a
Mass does
physical
not
object
matter.
25
Okay.
plus.
No. See, because you don't understand warp drive. So you're thinking of an object moving through the air. You're only thinking in
Pretty
terms
sure
of
we don't,
conventional.
as humans, understand warp drive. We understand the
Local
fundamentals of it.
physics, local trans, like your local dimension physics have nothing to do with the higher dimensional. Once you're in warp, it's like, everything's out.
No, that's not true either. You don't know.
Yeah. If it's okay, let's let Jack answer, because
Yeah. No, this is standard general relativity physics. What you're thinking is, and this is the big barrier that most people cannot wrap their heads around because they don't understand physics deeply enough, is that it's not an object moving through the air. It's not an object moving through a fixed space. It's the control of the space around the object by the object. Okay, so it's totally different. And it turns out the mass, it's what's called geodesic motion. But so because of the equivalence principle, the mass of the ship doesn't matter at all if you can control the gravity field around the ship. The mass doesn't matter. It's called the equivalence principle. Now, Ray Chiao pointed out that in quantum mechanics, there may be a violation, but this is still classical level stuff, and that's what we see. I'm just going on the basis of when Kevin said the 5 observables, So whenever you hear of things like some people have talked about inertial mass reduction, that's total nonsense. It's bogus. It's bad physics. Has nothing. As soon as they're still thinking about reducing the inertial mass, which you can't do because of energy conservation. If you lower the mass by a little bit, you have a nuclear explosion. Like, what is it? The atomic bomb, the Hiroshima bomb, was like 0.5% of mass was converted into energy, and the uranium, very tiny. So
that energy has to go somewhere if you're going to lower it.
Yeah. So all that stuff about changing mass is complete nonsense. It's bad physics. The people who say it don't know what they're talking about. That's it.
If I can interject for a moment, Jack, you had said something the other day that stuck with me, and you were talking about FTL drives. And I think that there's a comparison here. What you'd said is nothing can exceed the speed of light, right, in a vacuum, but you don't have to exceed the speed of light in a vacuum. Space itself is moving.
Yeah.
Right.
Now I do have some very beautiful pictures of how that works, and it's due to Roger Penrose. Okay, Roger Penrose. He got a Nobel Prize, with Hawking, and I actually worked with Roger. I was with Roger back in 1971 at Birkbeck College, University of London. But Roger Penrose explains you have to know what a light cone is, and Roger has an intuitive picture, sort of like a Feynman diagram, but for relativity, where you have to have imagine these light cones, and what curvature is, it tips the light cone. It's like the ship has a light cone, and what curvature does, it tips the orientation of the light cone relative to the space outside. See, and all that relativity has to do is you imagine a little world line inside the light cone. It's hard to explain in some words, but with a picture's worth 1,000 words here. But let's put it this way: if you set up another talk at another occasion where we can show the pictures I'm talking about, everybody will get it right away.
Yeah, I'll set that up, Jack. I'll set that up.
Yeah. So it just has to do with Roger Penrose's picture of curvature as the tipping of light cones. And once you have that, then everything clears up. So unfortunately, we're not set up to show the pictures. Or can you?
Yeah.
Can you show the picture? Can you?
Well, I think it would take we'd kind of go off track.
Yeah, it would take
but let's try and get you. We'll get you scheduled, and you can walk through the light cones and the physics.
Yeah.
So in the meantime, let me go back to questions for Kevin though. And,
Okay.
and again, anybody who has questions, and I know there are a lot of comments in chat there. But does anybody in the panel here have questions for Kevin?
Let me see if I can.
Jared, go for it again, sir.
I just have one more for Dr. Knuth. I'm not sure if you're familiar at all with Mike Gamble's work. He's a retired research and development director of Boeing. He has a very interesting idea regarding the Schumann resonances and how there might be some correlation there between gravity and the Schumann resonances, indicating some kind of electromagnetic thing. I see Jack.
No, that's ridiculous. I can tell you. No, that's silly. That's silly. I'm sorry, but that's silly. These tic tacs have nothing to do with Schumann resonances. What is a Schumann? Is it like 10 hertz? How big? What is it? It's a magnetic.
So with the different modes of the Schumann resonances, he shows how they correlate to the different Lagrange points. It's at least worth giving it a look before dismissing.
I don't think it. Okay, the Schumann.
No?
You're talking about some kind of large scale. It's a magnet. What is it? A magnetic frequency? Is electromagnetic frequency?
The RF resonant cavity of the Earth. Extends inward beneath the crust as well as outward beyond the atmosphere.
How could that affect what the 5 observables? How could that affect what Kevin was showing us? There's no connection. It's
I'm just showing he has shown a correlation between certain Lagrange points and different modes of the Schumann resonances that at a minimum is worth at least taking a look into.
No, but how? Why? I don't understand. What's the connection? What's the connection with the 5 observables?
That might be something to send over. That might be something to send over offline. I'll connect you guys.
I would only guess that it has something to do with the change in the refractive index of the vacuum at these certain points because it has.
Say it again.
I can only guess, and this is just me, an amateur, guessing that it might have something to do with the change in the refractive index of the vacuum at these different points because there is an increased energy density at these resonant nodes.
No. Okay. Now you said you're an amateur. Don't try to do physics, okay? Because it makes you sound very stupid. I'm sorry to a physicist.
Well,
okay.
Let's go. Yeah, let's try and get it back on track. Yeah. Actually, if I could put in a question from chat, someone was asking, and I think Kevin and potentially Jack may both have ideas. And again, I want to bring this back to Kevin. So I have been hearing a lot about Faraday rings, and someone has been asking about those in chat. People have taken photographs through polarized lenses that show Faraday rings, which I believe are produced by high magnetic fields, right?
Yeah.
Now, but I guess one thought would be, and again, I don't want to convolute this more, could those potentially be a byproduct of a warp drive as well, right?
Well, that's a good question. I'm not sure about the warp drive answer, but I can say some things about the Faraday rings. So basically, the light in the sky is polarized to some degree. So typically 90 degrees away from the sun. So you look at the sun, and then 90 degrees from that, the light coming from the sky is polarized. So if you've got a UFO up there and you then take so the polarized light from the background of the sky is going to pass the UFO. There's a magnetic field there, and the magnetic field is going to rotate so the light is oscillating like this, right? And it's a transverse wave. So it's oscillating like this, but the magnetic field is going to rotate the polarization. So it's going to drift and change its rotation. So now if you've got a polarized lens, then you're going to see bands where the light has rotated 90 degrees, it's going to be dark. Where it hasn't, it's going to be brighter, and so on. So you're going to get these rings around the object, and that's observed in some cases. So that allows you to calculate the strength of the magnetic field. So if you just do the calculations without looking at, so if you take an image where you've got Faraday rings, you should be able to figure out the strength of the magnetic field in that case. If you just do the calculations to see how much magnetic field you need to be able to get rings some distance out from an object, the numbers come out to be something like, with magnetic dipole moments on the order of 10 to the 11th amp meter squared. So around 10 to the 11th to 10 to the 13th amp meter squared. So that gives you the magnetic dipole moments around the UAP. So these are huge magnetic fields too that are observed. And the same thing with electric fields. There are enormous electric fields observed that can basically short out electrical equipment. So you're looking at huge voltages there as well. So these are, again, other clues as to how these things are operating, and it's not clear to me exactly what's going on.
Yeah, well, there can be, as I do agree, there can be several modes of propulsion here. They could have some kind of more conventional propulsion when they're not doing warp drive.
Right.
Which would be, some kind of magnetohydrodynamic thing or something.
And that appears to be the case. Oh, I'm sorry. It appears to be the case when they're taking off as well, because you have, the Socorro craft basically used something like a rocket engine to blast itself up, 20, 30 feet above the surface and then just zoomed off. And that's happened in other cases. There was a case in France where the craft lifted up, but it apparently used a very strong electric field.
Yeah, what's that noise?
And then it took off. So they appear to use different mechanisms to get away from the ground. And then once there's some distance from the ground, then it's like they can use this other kind of drive, which is spectacular, which could be the warp drive. Yeah.
And we have about 10 minutes left. If I could ask another one, I believe I saw this earlier in chat, and this has been something that I've seen references to. So it started out, our traditional UFO or UAP flies through the air, and presumably they fly through space as well.
It doesn't fly through the air. As soon as you say
hold on, but I'm just as in
but that's the problem. See, people can't. That's everybody stumbles on that.
Yeah, but Jack, that's only assuming that it is a warp drive. So I mean, it doesn't necessarily have to be a warp drive.
Well,
so
I claim it has to be a warp drive. Nothing else can explain.
No, just to you, it has to be a warp drive. That's how you make it understandable.
Who's talking? Who's it? Gary?
No, it's scary. Well, guys, hold on just a moment. Hold on, Jack. Let me mute you out for just a sec. Okay. So they move through air, right? They've been spotted moving through air. They move through water. The water is more new, right? And that's something that Congress has talked about. It came out of the military sightings. I have also seen speculation and photos of UAP that are embedded in the ground. They crashed, but the way that they crashed, it almost looks like they moved through ground. Have you heard anything about that? Do you know if they are capable of moving through the ground? And I know I'm not expressing that.
I have asked that question of people who might know, and I've always been told that they don't have any knowledge of them moving through solids.
I would just like to say that that's the perfect sort of thing to tie it back to what Sarfati was saying with it moving space-time together, that theoretically it should be able to go solid, liquid, or gas or plasma, essentially.
Yeah, Bernie, I would agree. I would agree with you. And I had seen photos. These were Paul Murat had these, and they were from Russia, and they showed UAP that looked like they were discs, and they were embedded in the ground. Now, it's entirely possible they were faked, right? But what was interesting was the way that they were embedded into the ground. It almost looked like their drive unit failed while they were trying to go through it, if that makes sense. It didn't look like they fell. It looked like they were embedded, as if something turned off when they were trying to enter it. So Yeah, that's the only reason
That's
I mentioned that.
interesting. Yeah.
Tim, just
Yeah.
to add that, also there's the Popocatépetl volcano in Mexico that's highly active for UFOs flying into it, and occasionally it looks like they fly straight down into the mouth of it. But there's some really good videos of it, of Tic Tacs flying into the side of the thing, just straight through the rock. For some of that transmedium travel, instead of just flying into water, without a splash, without anything, yeah, okay, maybe there's some little cool stuff there. But to fly straight through rock, that feels to me like it requires a completely different understanding of how to phase through matter.
Well, and potentially, and this would go to Jack. And again, Jack, I'm sorry for cutting you off earlier. This would go to Jack's thought, but if the warp drive makes the medium that it's in almost irrelevant, perhaps they could go through a solid.
I agree with Kevin on this. I don't see how you could really go through solid. I can see going through water. I don't really see how that could. I mean, it's a long shot.
And again, I will plead ignorance. This is just
I mean, we have machines that bore tunnels. I mean, but so maybe that it could be that they have some kind of additional technology. So it's just like machines that make tunnels. Those big screws. It's just mechanical.
It could be like a cloak's wall or something. They're just flying through the cloak or something instead of actually into the physical matter. That would make
The chat is recommending like the Philadelphia experiment style fused sort of metals, almost like the Hutchinson effect, kind of. I guess if it were
maybe okay. Let me tell. I can tell you something about that actually. When back about 23 years ago, this guy Joe Firmage made a lot of money and funded us. It was Bernie Hayes, Hal Putoff, me, and a bunch of people, and we gave a couple of $1 million to a defense contractor in Huntington Beach, and the guy from their board of directors came up. This was in San Francisco. The board of directors guy came up, and there was this man, very eminent. He was like, at the time, this is 20 years ago, he was like in his 80s. Okay. And he was a high level, like a Bohemian Grove type guy. Okay. A waspy, aristocratic guy. And he claims he was there. He claims he was there he was a witness to the Philadelphia Project. And he claims it was real. It really happened. So, and I also have other information from a guy in the CIA that I know. So there is something. So I don't. And also even Jacques Vallée wrote something about the Philadelphia Project. But I do have a credible witness who was on the board of directors of this company, major guy, who claims he was actually present. He was a naval officer in World War II, and it really happened. So that's all.
Okay. Well, thank you. Okay, so yes, we will give Jack his own show. I see Kevin laughing. And again, Jack, it is wonderful to have you on. You are a wealth of information. But let me go back to questions for Kevin. Does anyone else have? We have about 4 minutes left until the bottom of the hour. And again,
one quick little one. Sorry, at the very end of today's video or stream, can I play a video of these plasma orb UAP?
Potentially, in the open discussion. Bernie, why don't we come back to that?
Kevin, how many of these plasma ball lightning style UAP encounters do you have?
Yeah, we'll do that, and then we'll come to Dr. Ansbro. Dr. Ansbro, I see your hand up. So in just a moment, Kevin, Bernie was asking about ball lightning UAP.
Right.
Style.
Those like the Heselden lights or what are seen in Pine Bush, New York. Yeah, I don't know much about them, and I don't know how the frequency of occurrences compares with UFOs or what appear to be craft. So these are all open questions. I think we have a lot to learn about all of these phenomena, and there are several other phenomena that don't appear to be structured craft that are equally interesting. So
yeah. Okay, well, let me go to Dr. Ansbro, who has been patiently waiting. Yeaman, sir?
He doesn't hear you.
Nope, he's
Oh,
muted.
no, he was muted. I
Sorry, this is just for Kevin Knuth. Unfortunately, I didn't hear your presentation, but I took note of what you mentioned there about the Faraday ring. You're probably aware that Lee Stanford got recordings there back in the 1980s of Faraday rings, and an analysis was done by Petit in France, who specializes in looking at the hydrodynamics. I can't recall what the results were for that, but just pass it on to you, Kevin, in case there's any contact with Petit.
Yeah, I think he wrote a paper on Faraday rings, and he also included information about compass behavior, I think, in that paper, and talked about swirling patterns in the grass at landing sites. I think that was another example. But thank you very much. Yes.
Oh, okay. And Jared, did you have another question, sir?
I just have one more question regarding the Faraday rings. So recently, those calculations, 10 to the 11th Tesla, those are coming from Ray Stanford's fix, right? Well,
no, the calculations I was doing were those were from just doing the mathematics on how strong would the dipole moment have to be so that you would see Faraday rings around an object. Yeah.
So where I was going with that was the electric field. Shouldn't the electric field, if it's 3 megavolt or 300 megavolts around these crafts, shouldn't that also be affecting the Verdet constant for calculating these Faraday rings?
That's a good question. Yes, that's a good point. How does the electric field affect the Verdet constant? Yeah, I don't actually know. So, and it's probable. I was looking into this at one point, and it was hard to get the Verdet constant for some of the gases. Right? That's hard to get. So, I'm guessing it's not known how the electric field is going to mess with that.
So if that's
a good point.
If they have these extremely strong electric fields, it's possible that those magnetic fields aren't nearly so insane, because if you're above 10 to the 9th Tesla, you're already starting to get over the Schwinger limit. And it's obvious, pretty obvious, that they're not getting over that limit for these Faraday rings, because we should see antimatter gamma rays coming off of it then. Not seeing that. So it's got to be at least below 10 to the 9th.
Oh, that's possible. Yeah. Yeah, that's a good point. Thank you. Yeah, these things are really remarkable, and it's complicated. It's not all that simple, and you get the luminosity that Jack was pointing out. That's really shocking. That shouldn't be able to happen, and it's not clear what's going on. And I was talking about the warp drives. That's interesting because there's a case of a large underwater UAP that followed a frigate in New Zealand. Oh, yeah. Basically closed a 25 kilometer distance in 30 seconds. So you've got an underwater speed of something like 3,000 miles an hour, but they were measuring that with sonar. So how does sonar work? Well, basically you've got a pressure wave in the water. A pressure wave comes from molecules banging into each other, right? So the molecules were having to hit this object. So the object's moving, so it's confusing. The object's moving through water like it doesn't affect the water at all.
That's
affected by the water. But at the same time, the pressure wave from the sonar is interacting with the object. So what's actually happening? It's really not clear.
Okay.
It's confusing.
Yeah. Well, guys, we're at the bottom of the hour. So why don't we do this? Everyone, again, Kevin, it has been a true pleasure and an honor having you with us.
Let's give great fun. Thank you so much. It's been great fun to talk with all of you too. This is wonderful.
Yeah, thank you so much.
Am I clapping? I'm clapping for you.
No, okay. Well, so now let's do. We promised the audience a panel discussion just to get, and all of you gentlemen are welcome to, and I'll bring Michael back in as well. You are all welcome to participate in this if you want. Let me start with Gary Stephenson, because Gary actually has an appointment. So in terms of the congressional hearings,
I have to leave, so I will see you.
Oh, okay. Kevin, thank you so much again,
Thank you so
sir.
much. Thank you all. Thank you.
Okay. So, in terms of impressions on the congressional hearings, again, as a panel discussion, let me start with Gary because I know you're on a limited schedule. Gary, can you share with us your thoughts on the testimony with Ryan Graves, David Grush, and David Fravor? How do you think that affects the narrative? How do you think that may affect our community and this research going forward? And just any general thoughts and impressions you might have.
Yeah, I mean, I don't know any of the witnesses personally, but they all seemed very credible to me. The pilots, of course, fighter pilots for quite some time. And David Grush seems to have a lot of intelligence credentials. And so he's obviously not briefed into anything like, the crash retrieval program per se. He seems to have firsthand, or I should say secondhand knowledge of it, because he's received from people with firsthand knowledge some information about it. So it's a little tricky to establish that traceability until he's able to talk about those contacts in an open forum. But it was enough for Schumer to sponsor an amendment to Senate Bill 2226. The amendment went into the congressional record on 7/13, and it's essentially to do a UAP records review. So they're asking for all UAP records from every conceivable agency, and it's a pretty. Some of the language in that amendment is pretty stunning. So I think Congress is taking it very seriously and moving forward accordingly.
Oh, wonderful, wonderful. Well, Gary, thank you. Let me go to Gary Voorhees next, and let me see. Okay, and again, my apologies. I am still learning StreamYard a little bit. Okay, and Gary, what are your thoughts, sir?
Well, I think it's a positive step forward. I'm all for what Ryan Graves is saying. Flight safety. We really need to take this way more serious and bring it to the public, because of just the simple fact that it's not just a private military thing. So we should be. Every university in the United States should have a division devoted just to studying what's going on, anomalous events within our atmosphere, whether they're wet weather, whether they're completely explainable, balloons, mylar, but we need to know what every dang thing in our entire atmosphere is and why it's happening, so that we can have flight safety amongst our pilots, especially our military pilots that are, ripping around in supersonic jets. As for Grouch, he has an amazing pedigree. So I have to say, I will suspend disbelief for the moment and wait until see what happens. And of course, Fravor. I mean, he's an absolutely phenomenal representation of us guys that were there in 2004 and witnessed the Tic Tac event. So I was very happy to see him there testifying about this. So. Other than that, I mean, that's been my opinion on the entire thing. I mean, it doesn't really matter what information came out. It's just a matter of what happens from here. So let's see what happens with this, congressional panel that's supposed to come together. Let's see where it goes. Let's see if, more funding comes in the way of helping, organizations study these things in a scientific manner, and I'm happy. And it was the first time I was actually kind of satisfied with a hearing. It wasn't just a lot of jargon and a couple of sound bites.
Well, Gary, if it's okay to ask, so you have UAP Expeditions. I see the UAPX shirt on now. And for anyone who doesn't know, and I don't think there are many of them out there, you were a part of the original 2004 Nimitz encounters, right? So
Yes, sir.
You have so much history and current engagement with this. So do you feel like the congressional hearings are is that helping your cause with what you're doing with UAPX? And has it changed kind of the plans of the company, or are you just pushing forward with your existing agenda?
Well, through this whole thing, I've always told my guys we're playing the long game because we want to do serious science. It's going to take years to propagate the amount of data to say what's normal and what's not normal. So that being said, there is no we'll find out what happens tomorrow. It's let's find out what happens when we accumulate 10 years worth of actual
Well,
good
that's
scientific data.
Okay.
You know, so it didn't change our plans, but what it did do is give us hope that, you know, we might get a government grant if we underwrite a grant to do UAP research. You know, I just had a student come to us just recently doing her dissertation and wants to interview our scientist about the UAP phenomenon. So for our dissertation to actually be able to be allowed, you know, for their PhD on this subject is amazing. So I hope there's more of that, especially within the collegiate community.
Well, thank you. So let me see how I'm getting a little bit better at this. Let me go to Dr. Ansbro next. Dr. Ansbro, can you tell me, and let me see, I'll take your mute off. What are your thoughts on the congressional hearings? Again, you have an amazing career of work studying this phenomena. Do you see this as a move forward? I know that you're in the UK, so you probably have a slightly different perspective.
Just to correct you, I'm actually in Ireland, Republic of Ireland.
Oh.
It's next door, next island. Cautiously optimistic about the hearings. I'm familiar with historically of other hearings back in the past, particularly probably was the last hearing in 1968 where the senior scientist at the time was Professor James McDonald. As I said, I'm cautiously optimistic about the whole thing. I'm just hoping for the best that everything does come out eventually. So that's all right. Taking it
Wonderful. And do you have anything else to add, or should I go to? Let me see. I could go to Jack next, I think.
No, nothing else to add.
Okay. So let me go to Jack next.
Yeah, what is that? Is that a dog? I hear it like a dog.
Okay. No, it's a little bit of feedback, and I'm trying to kind of juggle that on my end. My apologies.
Okay, I was just going to address myself to Gary. Thank him for his service on this. So he must be working with Kevin Day, I imagine. I'm in touch with Kevin Day, and I mean, good luck to you. You know, looking for the 10 years of data. We don't need that. And good luck finding a government grant. We don't need that either. There's plenty of private money out there. In fact, there's lots of private money out there.
And maybe that's something we could pursue.
This will not be done with government grants. It's going to be done pretty quickly now, I'm pretty sure, with private money in the next 2 or 3 years. And, it's always good to get data. Nothing wrong with that. But we have enough theoretical understanding to actually, do this in a very short amount of time. Is my opinion. I could be wrong, but money is not going to be the obstacle. I'm pretty sure of that, on the basis of things that have happened in the last couple of weeks.
Well, Jack, if I could ask, do you see the hearings as a benefit to the science, or does this take us back towards kind of the cultural?
Well, the hearings are benefits in the sense that people people with the hedge funds in New York are now ready to throw in plenty of money. So in that sense, it's been good. But we don't need the government. And of course, the other thing is that the Russians, it's very important to realize that the Russians are going ahead with my particular theory. They invited me to Moscow. They wanted me to come to Moscow in July, to actually fly to Moscow during the Ukraine war. Of course, I didn't go. So the Russians take my approach very, very seriously. And we can just assume that I was invited to Moscow State Physics Department, to lecture on, quote, my vision of warp drive. So so there's an actual arms race going on right now, and we have to assume the Russians are running with the ball, no matter what happens here. And so that I'll take questions. Any questions about that?
Wonderful. So let me see. So I think those were our panel invitees. So let me go back to. Okay, I'm going to go back to group layout here. Do you guys want to have discussion? Do you guys want to have Q&A? Or again, we have probably about half an hour for this segment. We've probably got about 15 minutes left. Does anyone else have anything they'd like to share? I would love to hear, and I'm positive everyone who is part of this conference would love to hear all of your guys' thoughts on where things are going now, because the narrative, this is just my feeling, but it seemed like we were looking at tic tacs, we were looking at collecting data, right? We were looking at very rigorous, stringent things until this June. And it seems like David Grush has changed that narrative for good or bad. I'm not sure which, but
There's one thing that David Grush said, and he said there was 4 different methodologies for these things to work. Methodology is the wrong word in that sentence, but 4 different types, 4 different ways to skin a cat. It would be neat. Sometimes I know he watches these, but if we could get that, like a disc is not doing the same thing as a tic tac, is not doing the same thing as like a platform that people can stand on. Some of these field, the energies, the particle emissions that come out of high energy movements would be lethal to outside observers. So we know they're using something different than, say, like the sport model when it does like flip, takes off instantly, or so that's the only thing that I would it would be neat to have a clarification on.
Okay. Well, and hopefully Grush does. Again, he indicated, from what I understand, he has attended APEC in the past. He's also attended the Scientific Coalition for UAP Studies. He's gone to their conferences as well. I believe he went to those in person a couple of years ago. So he has definitely been following what's in the community, and my hope is just that's helped him better understand whatever he has been able to find in presenting to Congress. Sorry. So does anyone else have any thoughts they'd want to share?
Well, I just want to repeat, the Congress is almost irrelevant now. It's irrelevant. What are they going to do? They're going to put it, because they're restricted by bureaucracy and by budgets and this and that. The point is, you have to understand, private money is investing in this. The private corporations, they do things much more efficiently than the government does.
And Jack, that might be something. Maybe we could. That probably wouldn't be this conference, but maybe that would be something to broach another time, because that seems like it would be a giant change to the.
All I can say is there is a giant change already, and of course, I can't say too much detail about it. But the point is, forget the Congress. It doesn't matter what the Congress thinks. I mean, it does matter, but it doesn't matter because things are forging ahead no matter. Anyway, it's capitalism. The private money they're banging on my door to give me money. Okay, basically.
The one thing I have to say about the private money, though, is that private money tends to come with a lot of strings. Government money does come with it too.
That's true.
And unfortunately, I've even had to turn down some pretty hefty private money just due to the heavy strings that they wanted to impose.
Yeah, well, that is a problem. But that's the problem. That's why I have that is a problem.
Well, and I guess I would say, and again, I'm moderating, so I shouldn't interject too much of my thoughts. But this would go to Gary's aspect of it. One of the things that I've been very, very interested in is measuring devices. And Jack, this probably wouldn't be as important because you're actually working on reverse engineering, right? But for what Gary is doing in terms of capturing data, that's been a passion project for me. Also, is like, what kind of information can we pick up?
Well, that's what Abbey Loeb. That's what the Project Galileo was all about, right? I mean, the project, and also, that's so they're doing that. I mean, it's fine. I mean, it's excellent to collect data. I personally don't. We have plenty of data. We understand how these things are operating, pretty much.
Yeah. So, a lot of that's just it. Again, I would view that as kind of a support capacity, right? It's helping to support better understanding.
The more data they get, that's fine. But the point is, the problem with these people, like people like Gary, they're not physicists, so they don't really understand how to interpret the data.
No, I'm not a physicist, but the 3 physicists that I have working with me are physicists. So
who are they?
Kevin Knuth, Matthew Shadagas.
Oh, Kevin. Kevin has an understanding.
And Dr. Cecilia Levy. They're all physicists.
I don't know them, but Kevin understands pretty much now the warp drive. I can see from what he's saying. He understands. That's good. All right.
But when it comes down to it, you know, we want to know what it is. These are. If you reverse engineer everything, I'm on board. I'm happy. I'm not even angry.
We know.
Happy. All but right. When it comes down to it, you know,
the
things that we saw in 2004, I want it on my front yard. I want to fly one of them. I want to know exactly what it is, study it, and figure out how we can utilize this technology.
Well,
that's the ultimate goal. So if you get there first, my hat off to you.
Yeah, that's what we're doing. That's exactly what we're doing. Good.
Well, so, and let me ask, so Dr. Ansbro or Gary, do you guys have any additional thoughts on this, on where things might be going? Do you have any expectations on what we might see in the next few months in terms of this story? I have heard rumors that we may hear more between September and Thanksgiving. I don't know if there's any truth to that or not, but.
No, I've not heard that particular rumor, Tim. And Jack is right in the sense that Congress moves very slow. I mean, when you look at the bill, it's attached to the Defense Authorization Act for 2024. So they don't even start to ponder the records review until sometime in 2024.
Yeah,
and then they give the review committee until 2030 before they wrap up. So it's like it's going to be a 6-year ongoing slog. Yeah. And meanwhile, life moves on.
Yeah, and also don't forget the Russians. The Russians are very motivated because of the military. They want to convert this into weaponry, and they're under stress right now. So the Russians are going to run with this thing.
It's very possible they have more motivation than we do. That's
of course they have. I know they
Personally,
do.
I wouldn't deal with anything to do with the Russians right now.
Yeah, I know firsthand they do because they wanted me to fly to Moscow. For Christ's sake. So what does that tell you?
Well, Dr. Ansbro,
right here.
Dr. Ansbro, do you have any additional thoughts about what we might see in the next few months? Is there anything you anticipate?
I agree with Jack. Actually, I think the politics needs to be sidetracked to how should I put it, private investment in this area. That's work that I did for the last 30 years roughly in this area, including designing instrumentation for this as well. So for the future, I think it's all really for the public to be exposed to this, but for us scientists, we really have to get on with what we have to do, and I agree with Jack on that one.
I'm trying to remember, Dr. Ansbro. By the way, I'm going to be in London, and I will be in London shortly. Maybe we can. You're in Dublin?
No, in the wrong country.
You what?
Oh, yeah. I think he'd asked if you were in Dublin.
Yeah. Okay. Well, that's only like an hour's flight. Right? We should communicate. We're having a conference in Italy. And you might want to attend that conference in Italy at the end of October in Tuscany, in Cortona, Tuscany, near Florence. Because I remember now you gave very interesting. Well, I don't know what that noise is.
Oh, it's background. That's background noise.
All right. Okay. Well, why don't you put me in touch? Send me Dr. Ansbro's email, okay? And I'll get into them.
Yeah, absolutely. Yeah, I think it's Dr. Ansbro's mic. It could be because it's cross-channel communication, right? It's going halfway across the world, so that could be what's causing the issue. But yeah. Well, so we have about 9 minutes left until the top of the hour. But if you guys want,
if I may, something that I would like to see out of like the wheels or I don't know many metaphors for Washington D.C., but from our engineering conferences or engineering discussions with Falcon Space, I've pushed for the need to talk with the FAA Commercial Spaceflight Office or the CST office. Out of, again, this would be like going off of what Grush said, and that there's 4 different types of propulsion. Having that declassified or come out of Lockheed Martin, Raytheon, wherever, get, I guess, codified. So there'd be some sort of way of applying for an experimental license to fly one of these vehicles. And that's been my, when I was at UNM working on my degree there, I did fly over to DC and attend one of these CST meetings and met with, a couple space shuttle pilots and some FAA regulators. Ken Davidian was one of them. So, I went there as an experiencer from my times in Albuquerque and seeing the glowing dots over the nuclear weapons base. And my first experience involved optical cloaking. And so I was very sure of what I was, that there's something out there and that there's different physics, but I was hitting the fact that the education system at this time doesn't, we're stuck in a Newtonian mindset. So the regulators didn't have the language, the means of understanding or sharing in my experience, and the research that I'd done based off of seeing the vehicles. So that was the first issue. B, it was just, they were still more focused on what the needs of the public were. SpaceX at this time was just beginning to learn or do the retro or controlled propulsive landings. And so now that we've had these hearings, I think some of these people over in the FAA or, there should be some, I don't know, ease of discussion with them. And who was it? GZ, George Zamka, he was the pilot for the space shuttle on the STS-130. So he had actually, he was a naval aviator, and he referenced a couple, books, technical books that may have given him some understanding of it. But he was down for hearing the experiences that I'd had, and was very polite about it. But he said, "Yeah, right now we're focused on what the public needs and serving, the Commercial Space Flight Federation, Virgin Galactic, SpaceX, et cetera, et cetera."
Well, so Aiden, if I could, if I could kind of paraphrase, actually, I think you're touching on a really important point. Maybe whole of government isn't the right word, but definitely better intergovernmental cooperation between agencies. If Congress is, if they are officially saying this is real, which is what they've been saying so far, then other agencies should start to pay attention to that and take action as well. And I think NASA has, but the FAA, that's an excellent point that you're making, right?
Yeah. Well,
it's commercial space flight. I mean, there's all these companies that were a lot of new space companies, right? NASA's old space, and then you have new space, which started with the DCX, the Delta Clipper experiment. And then that segued into all this bloom of small launch vehicles that are out there. Now we're beginning to see companies Axiom, which is old space NASA re-imaging itself into new space. Suffredini, I believe, he was a former space station director. And then, so he's evolved this company of Axiom. And so you're going to get people up there on orbit. They're seeing some of these vehicles, and there needs to be a way of communicating the 5 observables and, making humanity evolve. So yeah, it's, I don't know, it's blending a different market segment with our esoteric physics and knowledge of things that glow when they fly. And it's a juggling match.
I think that, I would like to see this go to both, so in terms of what Gary is doing with UAPX, definitely grants. I would love to see grants for research, data collection, understanding what, where, how, why, right? All those basic questions that we're still trying to understand. And then as far as what Jack was talking about, if private investment is going to get involved with startups, it would be wonderful to see Congress and the various agencies that are involved with that start to support those the way that they've supported New Space, right? Like SpaceX would be definitely Blue Origin. There are hundreds of companies doing satellites, right? So there's already a model there from the New Space industry. So it would be wonderful to see support for this as well. And again, I know I'm overstepping a little bit as a moderator, but one of the things that I've always felt is you have these waves of innovation, right? And we've seen that with computers. And it seems like this kind of propulsion follows. I mean, just offhand, I've always thought that you had rockets. Rockets are what we've used. Now we have more innovations with rockets. I would imagine at some point they'll be experimenting with fusion drives. We're already seeing ion drives for space propulsion. This is a little bit further down the pipe, right? But this should fit into those innovation pipelines. That would be my hope in terms of society. Yeah, I see Jack shaking his head.
Yeah, it's all irrelevant. All that. I mean, fine, let them do it. It's all irrelevant. But once you have the gravity control, all that, it's all obsolete technology. It's only good for if you very limited use. It's not good for getting to the stars. It's not even good for getting to Mars or the moon. I mean, it's obsolete technology. I wouldn't spend a penny on it, on any of those topics. Not any, and that's what that's what I'm telling Wall Street.
Yeah, we need to spend some money on the room temperature superconductor. That's what we need to spend.
Definitely. If that works, for sure.
And on that note, guys, we are just about at the top of the hour. So let me thank everyone. Since Michael has started talking, I want to send things over to Michael, because Michael is actually going to talk to us about the room temperature superconductor. Oh, yeah. So let me mute everybody out. I'll remove him from the studio. And then let me go over to lab discussion with Michael. But first, let's. I want to give you all a hand. Everyone who is watching on YouTube, please give our panel discussion a hand, gentlemen. Thank you all. Thank you all. And
thank you, Tim.
I hope it hasn't been too chaotic. I'm still getting used to StreamYard, so managing things is always a little tricky. But okay. So I'm going to remove everybody out of the studio. And Mr. Perrone, lab updates. And I think Aiden has some stuff too in a bit. And then Mark Sokol is actually out today. He said he's like, you got to deal with Michael. He's like, I'm not even going to be here. He's like, leave me alone. So Michael, you are our hope, our only hope, Obi-Wan. And you're muted also.
Thank you. So, right. So what do we got with the superconductor? So brief update on, so I mentioned this already in a discussion with you. If anyone wants to go take a look at that on Tim Ventura's channel, that was fairly thorough. Some things I would have liked to discuss there that I can mention here. The hydride superconductors are still very interesting to a lot of people. I have a good feeling about ammonium nonohydridorenate, if anyone wants to look at that in terms of a hydride-based superconductor, and maybe lithium doping that. And then the other one was ammonium dodecaborate, but that's less likely because the rhenium really helps here. But yeah, in terms of hydride superconductors, that's still a very active area of research. And the reason is because with hydride compounds, in principle, you can have a very good Cooper pair-like coupling since the hydrogens are ultralight. And with metallic hydrogen, the idea was that you'd have an extremely high speed of sound, and therefore the coupling could be stronger. In terms of the lab stuff, the furnace is still running. I have two experiments in there at the moment. Our first, the thing about the paper, the superconductor paper that was released, I guess a little over a week ago now, they don't really specify the amounts you're supposed to add. So there's two possible meanings that they could have had. The final composition is an oxypyro. What's it? What was the mineral's name? It's on my other. That's not it. My bad about the delay. Trying to oxypyromorphite. That's it. So they like everyone's talking about lanternite, but they're using lanternite as a precursor and to supply the lead in the final compound. But the final compound is really just a heavily copper doped oxypyromorphite. So the final material, everyone keeps calling it lanternite, but lanternite's technically the precursor material, and oxypyromorphite is the final actual superconductor. So I mean, I was getting annoyed about that technicality on the online, seeing everyone say it's lanternite. No, it's doped oxypyromorphite. And speaking of oxypyromorphite, so pyromorphite tends to form really nice crystals, but vanadium, lead vanadate, forms better crystals. So I'm wondering if that will be easier to recrystallize, take shorter amounts of time to cook. And then vanadium oxide is much less volatile than the phosphorus oxide. So you should be able to just mix all of the components in the ratios that you actually want and just heat it up and cook it. So it should be a lot easier to make this sort of material. So here's hoping. I've already crushed up a bunch of, I'll clean that up in a minute. A bunch of vanadinite, and yeah. So that it's actually really easy to take apart vanadinite. You just cook it with sodium carbonate, and then you get sodium metavanadate and lead carbonate, and you can put the lead carbonate back in, and then you make ammonium metavanadate, and you mix the amounts you want, and then you add copper carbonate or copper hydroxide or something. So that's what I'm trying next. The original recipe we tried, we added so based on the paper, they meant two things. So, or there are two things they could have meant, I mean. They could have meant use 10% copper to start with, or measure an amount of copper phosphide that will give you the amount of phosphorus that you need for the actual compound, the superconducting compound. So the stoichiometry is such that if you add just copper phosphide, like they were saying, you either get an excess of copper or an excess of phosphate, or not enough phosphate to form. So our first test, we just added 10% copper, and then there was almost no phosphorus, and we almost had no material at the end of the firing. And the material we did have was steel. It was still optically clear. It wasn't like a gray ceramic like they were saying. So now what we're trying is we're putting in a large excess of copper just to make sure, because it's copper 3 phosphide, so that'll form one phosphate group when it oxidizes in the environment in there. But then you have a bunch of extra copper left over. So we're going to see what that does. I think that's probably what they meant in the paper, because the first one didn't work. It's not even superconducting, not even close. So now we're trying the other recipe. We have the original in there just in case further baking improves its properties. It causes the copper to diffuse in. So we'll see. And I need to clean up some vanadium dust in a minute here. But yeah, the vanadium, I think, vanadinite forms much better crystals in general than pyrophosphite. What's the name of it? Yeah, pyromorphite. Yeah, so here's hoping that recipe with the vanadium instead of phosphorus will do the trick. Aside from that, I mean, it's not too exciting right now. I mean, I'm just waiting for the furnace to finish up and cooking up a few different recipes that come to mind. In general, there is a large group of minerals that have this same structure, and I'm sure there will be a lot of interest in heavily doped. So they're called apatite. They're actually the same material that teeth are made of. Calcium phosphate hydroxide is a standard apatite. So, I mean, there's like a couple hundred different minerals that have that same molecular structure. And yeah, there's going to be a lot of research in the coming months to explore that space and heavily dope those types of minerals because of that molecular structure. When you heavily dope it, you have this you can have this contraction effect, which with the lattice-induced strain that we're looking for. So, I mean, the search space is a lot larger than I thought. However, the patent, they were pretty clever with the patent. I think they pretty much just looked at natural apatite minerals and they took as a list of materials for their patent all of the elements that frequently form those sorts of crystal structures. So I don't think we'll get. I don't think anyone's getting around that patent that way. The only thing I can think of is if people can find ways of different ways of processing the superconductor to make improved physical properties or to make it more convenient to use. For example, making wire out of it. As I mentioned on the other interview, you're basically forming crystals the same way they would naturally form in the earth. So, like, you're melting this thing into a blob, and it forms crystals. And a lot of the crystals in there are not the superconducting phase. So we're gonna have to extract the superconducting phase and maybe even put it under SEM to really figure out what the optimal composition is for it. Most likely, I would say. So, yeah, I mean, the race is on. I'm not sure what else. I mean, yeah, we can come back to this more towards like after the open discussions, maybe, or something, because I'm still waiting for the furnace. Yeah.
What wonderful, wonderful, Michael. Thank you. You know what? Let me bring Aiden in because I know Aiden has been doing work as well. Aiden, and let me see, Michael. I'll take you out for just a moment. Okay, and Aiden, you have been doing work as well, right? Now, in your
Correct.
case, and I see Jared as well. Oh, Jared disappeared. You have been doing work on metallurgy, right?
Right. So this is it's a laminated billet. I'm holding magnesium and zinc, and I can go through the process, but it's in pursuit of arts parts and trying to understand that little fragment of hull material. My hypothesis is that the structuring within it is probably not probably, but it is quantum tunneling of a mother pattern caused by, well, protons like to do movement, so it's got to be the strong nuclear force, the power systems. So you have this really interesting pattern that's developed in there. But going back to the metallurgy, this is it oxidizes, but I did make it in a controlled environment. I've done a couple drop tests. It's welded. So order of operation was to get the metal, magnesium sheets, and zinc foil, get some fine grained sandpaper, and you hit the magnesium until it's shiny, and then immediately get it into isopropyl alcohol. Stage the magnesium chunks in the isopropyl alcohol, do the same process to the zinc. And then we use something called a Torx block, which was these, you can see this imprint here, and it was 2 pieces of stainless steel that we drilled and tapped and cranked down, so there was a pre-applied pressure. So magnesium, zinc. I think we have 3 layers of zinc and 4 layers of magnesium. in there. From there, it went into a steel bag that we'd filled with argon and kept it upside down. We let the alcohol evaporate off a little and folded it. Yeah, the New Jersey steel barons right down the street from Falcon Space have the right type of tools for doing lamination. They do Damascus. So this has been a couple nights of teaching the guys physics and getting some of the lingo out of the lab and seeing what they understand about nuclear physics and electrodynamics and the standard model. And blacksmiths tend to be fairly clever, but so it's been a little bit of market development. Right. Back to production. So I played around with the melting temperature of zinc. We had a programmable oven. We got it up to about 800 degrees. Let it sit there and soak the first night for about an hour. Took it out. So the Torx block should have done something. Once the zinc goes through its phase transition of being liquid to wet to liquid, that's what you got to be careful with because it'll just come out. So we're keeping the temperature down to 800 degrees. That's the stainless steel is soaking a lot of heat, and apparently maybe the first weld held, but on the second night, pulled it up, heated it up. Actually, this was done yesterday afternoon. It took about 8 minutes, not second night, but got the oven up to temperature. We put the bag in, had it opened on this time, and then we had a hydraulic press, and just for good measure, pulled it out and ran it through the hydraulic press a couple times, and it's laminated. Monday night, probably cut it again in half, polish it, clean up the edges, and stick it through a roller and see if we can start to get a film or a foil. And then while working with these guys, I found that there's a company, Niagara Steelworks, probably near Niagara Falls, and they have the ability to basically do the same thing with aluminum and steel. Had a Friday afternoon discussion with one of the VPs about this, and I said, yeah, sure, if we could do like a 50-pound order, you guys do some of the precursors, figure out how to safely use the material, find operating temperatures for the equipment up there. And so they may be able to run sheets, I guess 12 inches by 48. I'll have to go check my notes. They're in a different notebook, but slightly bigger sheets. And hopefully we'll be able to roll out some dishes, and Mark can play around with acoustics and electrodynamics and see if we get anything that shows significant weight loss. One of the better experiments for weight loss has been like, the resonating chamber with a horn underneath. And so we were getting an interference, positive interference, and it showed a lot of weight loss. My takeaway from that experiment was that larger shapes of these saucer-shaped vehicles should have a lower operating frequency and be a bit easier on the ears. The smaller vehicles have a higher operating frequency and probably scream. So the shape and topology. Anyway, Tim, that's my update. The guys are down the street are loving learning about the UFO physics, and Falcon Space is, we're trying to develop a supply chain and a little bit of market awareness of our esoteric exotic physics.
Yeah, well, Eden, thank you. Thank you so much. Thank you for presenting that. It's wonderful to see your work progressing. It's absolutely wonderful. Let me go to Jared. Yeah, I'm not sure if Jared wants to talk about it, but Jared is working. Jared, would you want to talk about your upcoming trip to visit Ray Stanford? I think no? Are there any other updates you would want to present on? Oh, you lost your mic. Okay. You know what? We don't have audio for you. It's okay. It's okay. We will come back to it another time. So just for everyone who is watching, because we've got close to 200 people. So Jared and Charles Crawford are actually planning a trip to visit Ray Stanford. Ray Stanford ran Project Starlight, and he has hundreds or thousands of photographs, I believe, video. This dates back decades, right? He did decades of research, and they have been communicating closely with him. So I'm excited. I'm overjoyed about that because they're going to be picking up so much data. Most of this has never seen the light of day. He said bad Wi-Fi. Okay. That's okay. We have our code word for the day. Bad Wi-Fi. So yeah, Jared, I am overjoyed and thrilled. I mean, and again, people who have come to APEC have seen your presentations, your TR3B presentations. Both of them were immaculate, outstanding, brilliant. I mean, and the way that you wove together threads in the history and the connections that you made were just tremendous. So, with Ray Stanford, I can only imagine what you guys will come back with there. And that's just one of the many projects that you're working on, but that was the one that came out to me. So in terms of lab updates, let me see. So I'll take Jared out for a moment. I have a lab update also. I'm not a builder like you guys are. And this is not propulsion related. I want to do an unboxing for the Global Consciousness Project 2.0 random number generator. So this is different than the other ones. For anybody who has followed my channel, that is an area that I have an interest in, and I'll kind of walk you through it in a moment. But so I'm going to open this thing up. This is what it comes with. So it has a little registration card. I'll just set that down. It has a paper talking about HeartMath. HeartMath is a third-party company that manufactured these. And the reason is the Global Consciousness Project, they're not really hardware manufacturers. They're doing scientific and data analysis. So HeartMath made it. And I'll hold this up there. They also make biofeedback machines. If you're interested, you can visit their website. Just Google heartmath.com. There is a little Conakit board, and the great moment of excitement here, I'll move this over, is the GCP random number generator. And I'm actually going to be taking some photos of this and putting these up on, I'll put these up on social media as well. I'm trying to promote this a little bit. So what this device is, it has 6 reverse biased Zener diodes. The breakdown of those diodes is controlled by a completely random quantum process. And what was found over the last 25 plus years was the output of those Zener diodes changes, which changes random numbers that are generated as a result by news headlines affecting what you would call the collective subconscious of the entire world. And so they have run up to 50 of these devices. This was, I believe, Roger Nelson and a growing team. This came out of the Princeton Egg Project. I believe that was the original name. And so Global Consciousness Project is basically running these random number generators. What they found is large things that focus the concentration of large groups of people, such as September 11th would be a news item like this. Also positive things like Christmas and holidays. These change the output of random number generators. I am not sure why. I know that many people have theories about why that might be. I don't have a good one. And to my knowledge, GCP probably doesn't have a good one either. They're more focused on the data and the correlations. So one of the things that of course is a question is, well, how much does it change it? It changes it many, many orders of magnitude beyond statistical predictions. So there's something absolutely going on. And again, scientifically speaking, to the best of my knowledge, I'm not sure if anybody exactly knows, but this is the GCP device. Let me see. I'll try and get a good photo of it there. It's got a little power supply. It has a little Ethernet cord to plug it in. Basically, you plug this thing in, it connects to their database and recording metric, and those lights light up, and it basically just sends them data. So this thing, I'm going to be taking some promo photos of it. That's my lab update, and I will let you guys know how that goes. Although what I would suggest is if you want to learn more, I believe it's gcp2.net or .com. look up Global Consciousness Project. And again, I will show you the front of the box. This is the Global Consciousness Project 2.0. Just Google that and you can find out more. So they have lots and lots and lots of statistical information up already, correlation studies, again, 25 years of research. And they have had several PhD scientists work on this, as well as mathematicians. This is not something this is not armchair physics. This is real science. And so it is moving forward. Not related to APEC, not propulsion related that I'm aware of, but that is my lab update for the day. Okay, so let me see. I see Bernie with a hand up.
I just wanted to say that quantum, consciousness and psychic stuff, that actually might be the key to the propulsion of these craft, right?
If I could add a couple of quick things. When I purchased this, it was not free. It cost some money. They had said that they still have units they are trying to place. So again, anybody who's interested, go to their website, Google Global Consciousness Project. It's GCP 2.0. You can buy them online. I'm not getting into the details of that, but what I should say is that the quality of it looks outstanding. It's incredibly well built for being something that's so custom. I mean, it's just a scientific device. I'm really impressed. I'm very impressed. It's incredibly well built. What I should mention is if people are like, well, how do I get one of these? Because I want to know about psychic stuff. The beauty of it is you don't have to, actually. There are a few people, myself included. I think Gary Stevenson has one. A few people are running these number generators. The data that they produce is not local to me. It's global data. So if you just go to their website, you can get the results of this without having to spend a penny. And that's what I'd recommend. I would recommend that anybody who's interested, go to their website and look at the data they've already got online.
And then you can compare the data to someone else on the world and see if your guys' consciousness, influences it even more. And gives,
if I could be mistaken here. I could be mistaken. I believe there are minor differences between the devices in terms of output, but I don't think it's local. So again, there's no benefit to having one. It's more of just having the data in general. It's one of those things, right? Like you don't need to have a Google data center to
right.
benefit from
By
it.
me having the data and then like comparing it with it sort of thing. It's like we're both influencing it just as much in the actual experiment and how it works, right?
Yeah. It's exciting and it's interesting. And all of this is, what do they call it? Frontier science. It's just
no longer fringe. It's frontier because Pandora's box has been UAP'd out the door. And
yes, well, you can't call it fringe if it's in Congress now, right? That's the other thing. So, I mean, now
and Pentagon said it's so it must be so.
Yes, that's right. We're just waiting for Roland Emmerich. Independence Day 3.
No aliens blowing us up, though. I like them preventing us from blowing each other up.
Well, no, who knows? Maybe ID3. Maybe that's like Will Smith testifying, right? And which is truly terrifying. I mean, the first one was scary, but like Will Smith in front of a congressional hearing for 3 hours. He's drinking water to try and stay awake. He's chugging coffee. It's
as long as it doesn't devolve into like the Corey no good fiasco, and like we got to have the balance and the real out there's, and more people coming to APEC and bringing the disclosure out. And I'm gonna back away and hopefully encourage others like Jack to get back up here and tell their stories. And thanks for having me.
Well, guys, let's go to open discussion. I will bring. Let me see. I'm going to bring everybody in here. And let me see. It true to I was going to say true to Jeremy form, because I think that Jeremy says he said throw that link out there. So you know what I'm going to do? I'm going to throw our link out there. Anybody who wants to join, just again be polite and respectful. You know, all of that kind of stuff. That way we don't have to boot anybody. But anybody who wants to join the stream for open discussion, that is our StreamYard link. No guarantees. We've only got 3 or 4 spots left. But I think John Brandenburg.
Yeah, where did he go? He popped up early. I was like, oh, Brandenburg.
He wanted to do a presentation and then he disappeared.
Well,
John.
at least we saw him briefly.
Tim, one
Jared
other
is
thing,
there. He goes.
Yeah, my audio is working again. Tim, one other thing I can add to that consciousness project device. When I looked up the schematic for it, it looks like it's using like a dual random number generator or a single random number generator with like a filter on it. Because I was a little concerned at first that like noise might affect this thing and corrupt even with a large scale data set like it's getting with, you know, hundreds of thousands of devices or something, that it might mess it up. But I gotta say, I was really impressed with all that they were able to pack into such a small and relatively cheap device for a couple $100.
Well, here, let me take it out here, and I'll hold this thing. I'll hold this thing up. So that's, you can see it's very thin. If I understand correctly, this is basically kind of like a Raspberry Pi. That's probably the best way to visualize it. Very thin. It's basically just a board with a little processor. It's just enough to connect to the internet and give them the results of these random numbers. So
it's a digital Bagua.
It's filtering out all the temperature. It's filtering out like electromagnetic disturbances. It's filtering out everything, which is really reassuring if they're trying to measure the consciousness field, because the consciousness field, you know, may have, you know, leaks into these other things, but you're trying to just measure this one thing. And through all their filters that they have on it, it seems to be pretty daggum good, especially with some of the data that's come out from it. Like you were saying, September 11th and Christmas. I think the World Cup is another big one where like you can see like the divergence from the median is like crazy high.
yeah, well, and my thought, and I'll probably make enemies saying this, but all of us have had. Oops, let me see. Studio is full. There are 10 people in the
I'll
studio.
hop out for a minute, so let someone.
Oh,
else
okay.
For a minute.
Yeah. So all of us have had experiences, right, that we can't explain. I think every single one of us has in our life, you know, and psychology explains some of those, but not all of them. And it doesn't attempt to explain all of them. And those explanations don't always wash, right? Like, so a good example is, we fit past data to match our current experience, right? So, okay, let's say I have a dream about something and then I have an experience that's similar. Well, psychology would suggest that my brain is changing that dream, my memory of it, to fit the experience, you know. Now, maybe sometimes that happens. It probably does. But there are other times when it's too specific, right? And I've had that happen. I'm like, no, my brain couldn't be changing that because the outcome of that experience wouldn't have been the same and it wouldn't make sense. So I think all of us know that there's more there. The problem has been after, I mean, thousands and thousands of years, right? We don't really know much more about it than we started with. So, so stuff like GCP, it just provides more data, more insight, and maybe it won't solve it, but it's at least a step down that road, you know. The same thing as what Gary's doing, right? Gary, what you're doing to UAPX, it's just one step at a time further down that road.
And we actually included a random number generator in our first expedition. It was very inconclusive because, unfortunately, the bad thing with random number generators, it's only an over time thing that's going to tell you whether there's an anomaly. And then, of course, we had some issues with the person that was supposed to actually interpret the data. You know, but they've moved on from our company at this point. So, but gladly they moved on. We actually decided after that we weren't going to go with the Zener diode version anymore, and that we were going to go with a nuclear one.
Okay. So you're actually looking at nuclear breakdown now. So you're still looking at a random number generator, but it's based on nuclear effects?
Yeah, it basically uses a radioactive decay as an entropy source rather than.
Do you know which
using
element?
I'm going to leave that to the Matthew and Cecilia, our local radiation experts. If they need me to solder up a board, I can do that. I'm basically just a glorified technician. I mean, I can't even talk in the same chat as like Jack and Kevin and those guys. So.
Well, and that's Gary. That's nothing to be ashamed of. I'm in the same boat, right? It's everyone has different strengths, and well, I mean, one of the things I'm going to seem Panglossy in saying this, but one of the things that I've seen over the last couple of years is not only do we have a community forming, but it's coming together, right? And people are collaborating and communicating. And there are lots of personality clashes. I mean, this is a community that's full of independent thinkers, and they all have their own approach and their own opinions. But when you look at that larger picture, it's really encouraging. It's amazing. I mean, you have people who are all going different directions, but they're able to collaborate and communicate and work together too. So I'm just overjoyed, and I have been.
Hey, Tim, this is Clay. I'm sorry I don't have my camera working.
Oh, okay. What's going on, Clay?
I just want to say, hey man, it's been a while. I've listened in on the YouTube end and not logged in since you updated your format. But man, I just want to say while it's all live here, thank you, man, because you are such a gentleman, and you have such a great demeanor, and your ability to interact and communicate with all these different folks that you were just talking about, and just keep your cool and be so such a gentleman, so polite, such a great person. I don't want to sound like I'm not trying to pick up on you, but I'm just a wonderful person, man, and I thank you for that.
Well,
and
thank
you don't get
Clay.
enough
Thank you for saying
clapping
that.
enough, so I just want to put it right there, man. Seriously.
Well,
and I'll
no,
get out of the way.
Thank you. I appreciate your saying that. I do my best, and we have lots of we have unexpected stuff too, right? Like today with Ray, when he uploaded the PowerPoint and the stuff didn't appear, I was like, that's not supposed to happen. So we've had lots of weird little things, but
you can tone it down, buddy. But the truth is, you're the focal point. You're the guy that brings all this together, and you just do a great job of it. And I just thank you for doing this. So that's it.
Thank you.
That's all.
Yeah.
Thanks, man.
Again, I'm just I'm just moderating. It's I try and redirect everything back to the brilliant people actually doing the work. That's it. I mean, and to be honest, I
don't sell yourself too short, Tim. If you notice, I hadn't been doing too many interviews lately. I mean, I dodged you how long?
Well, and Gary, I would love to have you back on the next couple of weeks as well.
Just know I wasn't dodging you on purpose. It's been very busy.
Not at all.
I've had a lot of actually, I got real sick for a while, so I wasn't even answering my emails. It frustrated everybody in the company.
Well, and a lot of what I've been doing is email and phone calls and scheduling and stuff like that. And just what I can share, because I do communicate with a ton of different people. Everyone is really busy. And that's one thing. And I've seen this in the community. Someone will send an email to someone else and they won't hear back. And they're like, oh, this person doesn't like me or whatever. And I've done that in the past. It's like, oh, they must be pissed. They must be this. They must be that. And what I've had so many times happen is they'll just reach out later and they'll say, oh, I was busy. I was, as you mentioned, you were ill, right? They just missed it, whatever. And so,
yeah, you can never know what's really going on. Cause like a lot of, we decided to kind of go a little bit under the radar for a while, just work on our projects, work on our developments. We're developing our standalone deployment systems and stuff like that. So, we needed to really focus on our work for a while and not really worry about social media, and because it was just kind of getting a little wily out there, especially with the Twitterverse, and I mean that stuff's can just rub you raw. So, we needed the break.
Yeah. Oh, I'm getting a request for. Let me see. I'm getting a request for Jeremy Reese, the alien scientist himself, who is. Let me see. Michael, is he hiding with you?
No. girlfriend stuff was going on, so it's
okay.
Life
neat.
and family.
Yeah, basically. Yeah, exactly. Like Tim was just saying. Anyway, like people are busy sometimes.
Yeah.
Anyway, I turned off the furnace. We will see what result we get in however long it takes to cool down, which could be.
Hey, Drew.
Vacuum furnace.
I don't want to crosstalk, but I was curious what Drew was doing, or how you been, Drew? You got anything?
There was just a comment there. Let me put this one back up. We're entering a new frame of consciousness. Physics is over as we knew it. And again, I'm going to sound Panglossy in saying this, and I want to be careful so that I don't name names. We'll just say that I talked to someone, now retired general, we'll just say a former general at the top of the Pentagon who retired. And I asked him about UFOs, and we had done some interviews related to other stuff, not UFO stuff. And so one thing I should mention is throughout the military, both active duty as well as retired, there are so many people who are interested in these phenomena, and they still feel a stigma that they can't talk about them. And that's changing, but it's there because I have a lot of contacts. I have many who believe in it and can't talk about it. And that's fine. They'll, at some point, I'm hoping they'll feel comfortable enough, but it's not my place to pressure them. But this particular individual, I did ask him offhand, and he surprised me. He said in previous command, he said, again, I'm trying to be careful not to be too specific. He had said in a previous command, he was in Iraq, and he saw things that he couldn't explain. And he said people under his command that he trusted implicitly saw things that they couldn't explain and told him. And he said, so I believe. And he said, but he's like, I'm at the end of my career now. And so this goes back to what Candidate's comment was, physics as we now know it is over. What he was saying to me was, it's up to your generation. It's up to that younger generation to take what we have and move forward with it. And that's you guys right there. That's you guys, as well as the people in the audience, and that's from someone that I respect, but that stuck with me because what he was saying was, it's there. I don't know, but I'm not in a place in my life, but you guys are. Run with it.
Hey, Tim, can I just
it's allowed to be disruptive technology now that it's confirmed, and disruptive technology is being encouraged instead of suppressed like it has been for the last 100 years. Now it's like, hey, we're at this point, it's real, it's out there, we're saying it's there, but whoever can get it and make it work, well, maybe it does work.
Well, and we're all learning, right? And we're all learning together. And and then there's that other quote: "Science moves forward one funeral at a time." And that's unfortunate, but I've seen that too. There are people I've met scientists who are just like, I can't accept this, and I've met others who are struggling with it. And I do myself a little bit. It's like, okay, I can't. There are parts of this where I'm like, man, this doesn't make sense. But I'm like, but look, this is what the data says. I mean, what else could this possibly be?
Hey Tim, before we get to Drew's stuff, can I just ask Gary a question real quick? Really curious about this. Gary, have you by chance personally known anyone, possibly from the Nimitz encounter, but it could have been from anywhere else, and personally known anyone that has had Havana syndrome?
Well, yeah, but I don't know whether I can't really discuss who it was. I mean, I hate to be that guy, but it's just something told in confidence to me. So but I could just say yes. But Havana syndrome to me is too many wishy-washy symptoms under certain situations that you can't prove. It's just like Tim was just saying. It's like, I know that there's advanced technology running around this planet right now, just from what we witnessed in 2004. I have no idea what they are. So I'm straight on the fence with, I'm still on the fence with, what Gouch is saying. I won't really subscribe and truly believe until I see the results of his testimony coming to fruition and seeing these emerging technologies that were reverse engineered come into a public, or at least a history of what technologies are reverse engineered technologies that are already in the public. Because I mean, it could be as simple as, starting with, semiconductor electronics. Because I mean, we went from an analog electronic system to a huge jump of this doped material of having all these things on one small chip. That's a big jump to go from. And then you go from that to these micro miniature electronics, like in the first iPhones. I mean, that's a huge another jump. You know what I mean? So we have had these massive jumps, but then again, in the same respect, technology is exponentially going to increase no matter what. A better computer is going to build a better computer, going to build a better computer, and it's going to be an exponential process. So it's going to get to the point now where I feel like the emergent AI is going to build a better AI, which is going to build a better computer, which is going to build different technologies that we never even thought of, because it's thinking in a very abstract way of just, it doesn't care what's possible, what's not possible, and then it just makes it possible through an innate understanding that only an AI can have. So we're about to have another. I mean, and well, not even like Skynet. I mean, it could be completely inert. I mean, they can keep the AI without becoming completely conscious. I mean, we don't even know if it ever will become conscious. It just will understand more and more. So we just, as humans, we always, project our own consciousness onto anything that seems as though it may be conscious. So they may not be conscious. It's just, they may be just so complicated that they're able to actually just figure out what you want to hear from them. I mean, and they could just stay benign the entire time forever. But
I would prefer that almost, I think.
No, me too. I mean, this is my fairy tale. So it's like you said, Tim, just stay on the fence with the stuff that you really just don't know, or it can't be proven. I mean, I'm not a physicist. I'm not anything. That's why I have physicists that work with me. So, but I do know technology. I do know engineering. I do know a lot of things in that realm. So from that standpoint, I can't wait to see what AI comes up with, because I hope for the day where it does take over all of the work and we have nothing but time to create. That's why you're content creators are becoming so wealthy right now. Because I mean, the normal jobs are going away, so people are trying to figure out ways to make money just with creation. So all of a sudden you now see content creators exploding all over the place, and it's not going to end. It's just going to be a endless cycle of what's entertaining now.
Well, Gary, it goes beyond that. I mean,
I know, but I'm trying to keep it at a certain level.
Yeah, if you get advanced enough technology, then you have actual post scarcity where you can opt out of the main economy and not have problems surviving. Like, you can make a system with, like, if you in principle, if you have a machine that produces your food and
I'm getting background noise.
Yeah, I don't know. It's not on my end. Where's that? Anyway,
okay.
Yeah, if you have a device that produces food, energy, it has shelter, maybe it self-replicates, you can give one to your neighbor, then you've satisfied all of Maslow's hierarchy of needs with, or at least the lower rungs of it, just with a technology that's distributed and completely decentralized. And at that point, you only have the higher rungs of Maslow's hierarchies of needs to think about, and that changes things.
But things have to change a lot, especially within our political structures and hierarchies throughout all of the world, before we're able to move on to something like that. Well, there's a lot of people that are going to have to let go before they let the lower masses have anything other than what they need, and just a little bit more. I mean,
Well, and if I could jump in, one of the things that I've been following is there are no guarantees, but it genuinely looks like the human race is looking at a population crash in the next 100 years. And they're saying that it could be up to a tenfold reduction in people. And that's actually, a lot of people get scared. Economists get scared
But
about this.
Elon Musk says it should be the exact opposite, and we should have a 10x implosion if we do the AI.
He's being optimistic.
Yeah.
Well,
AI
the
gives
thing
us
is,
more time to enjoy ourselves.
I'm a supporter of reduced. So when I broke into the tech industry, it wasn't the beginning, but it was close to the beginning. I worked in Redmond during the .com boom, and there was a surplus of jobs compared to people. And this is basic microeconomics. I studied this in college, and it was like as simple as it gets. It's the more of something you have, whatever that is, the more you have of something, the less each unit is valued. The less you have, the more each unit is valued. When I was in Redmond, people who were like McDonald's level employees were getting paid way over what they would have made otherwise. And they had amazing benefits, and they had stuff like work from home, work remotely, right? And people with skills and training were making 2 to 3 times inflation adjusted what they were now. It was insane. And the reason was because companies were competing for people. So if we live in a world where people are scarce and AI has to take a lot of that burden, we could see something like that for everyone. And that would be wonderful, where people are more valued and AI just does the grunt work. So.
Tim, just to add to that declining population thing, if people aren't aware of it, there's been some good studies that come out where it shows over the last 50 years, sperm counts across the planet have dropped by 50%. Just sperm counts. That's not including other birth defects, other miscarriage type things, right? So when you look at like this population collapse thing, it's not necessarily just economic. It's also because there's a lot of pollutants that have made their way into the water streams. I think PETG or one
it
of
could be
one
that
of the,
most of our food's fake too.
Yeah, there's a lot of chemicals.
PFAS.
But even the untouched tribes, though, have been affected by this, and that's how they were able to find it was in the water systems, as well as finding it down in Antarctica. The chemicals we've been using in like tens of thousands of products across the planet have made their ways into the water streams and made their ways into our genes enough that it's causing these major defects in reproduction rates, which is very concerning when you look at the ability of humans to like even support themselves, because you need like what 1.8 kids per couple or 2.1 or something like that.
So the one of the studies that I saw, and this would go counter, and I'm not being negative about your point. People can't afford kids anymore, Matt. Matt, you have an absolute point. I have a child. I can't afford her, but
people can't afford anything anymore.
Yeah, I know. But so I saw it was a lengthy article by a researcher who was in rural India, and he was talking about interviewing. They were doing reproductive stuff, and they noticed that women are having fewer children. And he was trying to make the connection. He's like, "How is this happening?" And in this article, he wrote about these women sitting on a bench waiting to be interviewed, and they were all fidgeting. Right, every now and then you'd see one of them fidget. And he was like, "What is this? This happened a few years ago." And finally, one of these women does this fidget, and she pulls out her smartphone. But this is rural India, right? So these are not wealthy. These are like just typical average person anywhere on the face of the planet. And the conclusion that he drew was women's education, which leads to lower birth rates, it can't be controlled anymore, right? Like the local village can't tell the woman you need to have 20 kids because that woman can go on her smartphone and read about reproductive health. She can read about economics, and she can learn how birth control works. And so he was saying that by putting this knowledge into the hands of rural populations, it allows them to better make decisions for themselves, and they're choosing to have fewer children. So
careful, Tim. It sounds like you're saying smart women are the problem.
I know.
Well, honestly, I just think higher education across the board is causing it.
Yeah.
I mean, look at just normal everyday kids right now. My daughter's 4 years old, and she can use a tablet. When I was 4 years old, I was eating rocks and throwing dirt I mean, my daughter's already starting to do arithmetic and things like that at 4. So as the general IQ goes up, birth rates are going to go down, because I mean, I know I only have 2 kids, and I end up having one of my kids later in life, and we weren't even planning on having kids. So, so I know a lot of, people that just don't have a lot of kids. I think the only people that are still having a lot of kids are the hardcore Christians, and the hardcore religious folks that are still not using birth control, and that's about it.
Well, is it this is a propulsion conference? I don't know. Drew, I'd asked
Yes,
if you had
we're going
any,
off track a little bit, but
yeah.
Let's not turn the 50% of the biological population against us and keep the one.
I don't know how we got so off track.
Lulu, do you have any comments on that? We do have
just waiting.
Right, get a little more.
Just waiting.
Let's hear what Drew has to say.
I believe it was to the daughter thing before we. So my daughter the other day, I'm not sure what to make of this. She says, I want you to buy me a book at Barnes and Noble, and I think it was Seneca, right? The ancient Roman philosopher, and it took a moment. I'm like, really, and so I bought it for her, and it was the right thing. She'd read about it, so she's had me read that to her as a bedtime story, which is horrifying. I mean, it's so boring, but. And I was like, where did you learn about this book? And she's like, TikTok. I was like, that just blows my mind.
That's like
I don't know if that's good or bad.
Amazing outcome you could have ever hoped for in like this universe, I think.
How does that happen? How does TikTok lead to classical Roman philosophy? I'm like,
it doesn't.
No clue, but at least
you're wanting a book,
making a TikTok.
a book from TikTok.
I know. I mean, maybe if there was a monkey juggling it, then I could see that on TikTok. But so I don't know.
TikTok was Chinese Communist Party.
There's hope for humanity.
Yeah, it's spyware.
Or
I don't have social engineering.
I want to hear Drew.
Social engineering.
Yeah. I've removed it from all of our platforms.
Well, let's go to let me see, Mr. Andrew.
Hello.
Andrew, go for it.
Yes.
You have an update for us. Why don't I spotlight you?
Okay. First thing I ask is this whole format thing new? The whatever it is, YouTube version of it? Because
yes.
Okay.
Yes.
Okay. It took me an hour just to figure out how to even talk, and I'm glad I'm online. So
there we go. Okay. Solo layout.
Hi.
Now we can see you.
First off, just want to real quick. These technological bounces and all this miracle things that we've reverse engineered aliens or whatever. Guys, you're not giving any credit to the dudes who spend their lives like Schottky, who spent 40 years inventing the transistor. Okay? Oh, yeah. You're thinking that, Velcro came from an alien spaceship. That guy spent 27 years inventing Velcro. Literally. Okay, so let's give a little credit where it's due. You got bored engineers like me spending 20, 30, 40 years of their lives coming up with something cool, and then, boom, somebody grabs it, they slap it on a lunch pail, and next thing you know, it's Jurassic Park. So that's all I'm going to say about that. My rant is over. But I would like to present something real quick, because I've had a great week. So if you don't mind, I'm going to share.
So what do you have for us, sir?
I'm going to throw it up on the screen if I can figure out how to do it. Screen sharing works.
Okay.
At the very bottom.
Yeah, you can screen share.
Share screen. I don't know what I'm doing.
It's going to ask you to select a tab or upload a file.
Oh, okay. There it is. So there's the window, and the window I want to look at is this one, and share that one.
Yeah, Drew, to answer your question, we did. There you go.
Yes. Okay.
We're using StreamYard now.
That looks like SNR there.
What now?
Looks like a good signal to noise ratio.
Yes, except that's not a signal noise ratio. That's just a running tab over a course of about 2 minutes, I guess, maybe a minute and a half. This week was really cool. I have replicated my 30+% thrust to weight ratio. I don't know, 5, 6, 7, 8, 9 times. Different units, different slightly tweaks on the assembly, slight tweaks on the materials. Found a material I like best. Tried to go thin until it blew up, and punched holes in it and stuff. But this is a real typical example. Sadly, it doesn't have the. Anyhow, I had a whole bunch of really cool numbers and things right down here. But anyhow, I've invented just kind of an internal matrix or metrics for myself. And basically, I take the efficiency of the particular thruster and divide by whatever voltage it took to get there. And since I'm operating in the north of 30% range, I'm discovering that my thrusters are operating at about the same quantum efficiency, pretty much all the way up through the voltage ranges. So that's kind of cool. So like at 5,000 volts, they're operating at say 3.1 on this little metrics thing I created, and then at 10,000 volts, they're making a whole lot more thrust, but they're still operating at about the same efficiency rate. So that's kind of cool. My genius Charlie, Dr. Charles, he's the number cruncher. I just give him the data. So this is a typical example of I don't know if you can see it. Can you see it? Yeah, here we go. So this is the thruster on, and it's on at about, this was something in the range of 10,000 volts or so, I think. And then turn it off, turn the power off, and then this particular one is facing so that the load cell is seeing a negative load because it's working up against gravity. So it basically bleeds off over the course of about 60 seconds, comes back up to basically 0. And if you take the delta between here and here, I think it's something around 1,500 micronewtons, so about 1.5 millinewtons. Just to give you an idea, when we're down here with full power on, this thing is drawing 5 microwatts, 10 microwatts. It's something stupid like that. And we could have, I don't know, 100 times this much, and it would still be drawing 5 microwatts because it's electrostatic. So overall, the project's going great. I have replicated my own success, I don't know, like I said, 5, 6, 7, 8, 9 times. And we have locked the design, and we are now headed for large scale, what I call scale up. So basically, a couple of years ago, I stopped and wanted to refine the system. But I was up to 5 millinewtons with a stack a couple of years ago, but it weighed about a kilogram. Now I'm going to be doing, I'll be probably I'll probably doing 5 millinewtons on about 3 grams. About 3, it's about a half a gram per millinewton of propulsion. So it goes up pretty quick. So I'm headed toward making my first Newton class thruster. It'll weigh something in the range of about a half a kilogram. With the housing and everything, it'll probably weigh about 3/4 of a kilogram. So I'm very excited about that, and I'm now dreaming about soft landings on the moon, because 30% thrust to weight ratio is more than sufficient to carry the weight of everything that isn't propulsion. So soft landings on the moon are a serious possibility. So that's what's going on here in sunny Florida.
All right, cool.
Now I will stop presenting.
I'm glad there's something cool going on in sunny Florida, because all I'm getting is heat and mosquitoes.
Yeah.
Wait, are you in Florida, Gary? I thought you were in California.
Nope. I'm in Florida, right near the villages. Central Florida.
Up there in Lady Lake or Leesburg.
Yeah,
that
area.
Yeah, I know it well.
So Drew, that's looking like you're getting for a couple milliwatts, you're getting a couple at least 1 millinewton for a couple milliwatts.
Microwatts.
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 So like a newton per kilowatt.
Like a newton per milliwatt.
Are you getting any? So you're getting leakage current in there?
Yeah, that's basically what I'm seeing. Well, the power. It's just leaking around the edges. Because I'm only at like, I don't know, about 6 to the -6 torr. So that's enough to make plasma at the voltage that I'm playing at. Plus, I'm not real, I'm not real serious about cleaning everything, and I write with Sharpie markers, which have carbon in them. So yeah, I get a lot of flashover, and then I get a lot of trash. So yeah.
I mean,
yeah,
so
Since I got an environment question. I studied the LADEE NASA mission, and they determined when they crashed it and had the orbiter that there's a very subtle sulfur atmosphere on the moon. You got to look up the mission, the data from the LADEE, LADEE, Lunar Dust Environment Explorer, I believe. But I think it is sulfur that is around the moon. So is that going to affect the propulsion?
I believe there's also
sort of
ozone and hydrogen. Sorry to interrupt, but
there's closer down to the surface, but there's
helium,
an extended
hydrogen,
atmosphere around.
Yeah, it's
the moon
like
that's predominantly
10 to the
sulfur.
minus 8th. Okay, let's be realistic. It's 10 to the minus 8, 10 to the minus 9 on the backside. There ain't no way
there
around
was a new study that NASA had that like the front side was exposed to like this extended atmosphere connected from Earth on a certain amount of it that had like a whole bunch of ozone.
Occasionally,
What if I did a story? So one of the things that's interesting is helium-3, and you can use that for nuclear fusion, and that's captured in the lunar regolith by basically it just comes out of the sun, right? But the regolith is the small particulate matter, so it captures it. You've got that, and then the other thing is captured solar hydrogen, and then I believe it's oxides also. And one of the things NASA was talking about was literally just baking lunar regolith. You could make rocket fuel that way, and you could also extract helium-3 for fusion. So, in a weird sort of way, the moon is covered with water. You just have to heat it up enough.
Yeah, don't care so much about rocket fuel anymore. But you're right. There's lots of stuff up there on the moon that's worth it. My dream is to get rid of chemical rocketry, replace it with our propulsion system, obviously, and do soft landings on the moon without kicking up dust. I don't know what y'all know about the lunar landers, the next generation of lunar landers, but they're big. They're like 40, 50 metric ton monsters. And they're rocket engines, they're retro rockets, whatever they plan on coming down on. The energy coming out of those things is more than enough to put that moon dust, that regolith dust, which by the way is just
into
cracked
orbit.
glass. It puts it into lunar orbit, and it's going to come right back around about 90 minutes later, 80 minutes later, just to come visit you to see what's going on. So that ain't no joke. That is a serious problem, and I don't know. SpaceX has some dream about the rocket engines being on the top, and Blue Origin has some dream about paving the moon or some nonsense. I don't know. I'm gonna avoid it all. I'm gonna land without any discharge. So
no, that's good. I'm a moon fan. I'll out myself here. I'm a lunar exploration fan, which makes me like one of the few these days. Yeah,
okay.
Moon first.
You're gonna like this. Hang on. You ready?
People think I'm crazy for saying that, but
this is not ready for prime time, guys. But y'all gonna see it first. Okay. This is a pitch that I'm putting together. I don't know where my camera is. See lander. See little rover. Little rover lives on top of lander. So when I land, little rover comes off. Astronauts go into the rover. They go roving around into craters, into lava tubes, into whatever they want to do. And they go, whatever, have a picnic lunch out there on the other side of the moon. And then they come home and they all get into the, the thing where they, hang out. And then when it's time to go home, they take their little rover and fly it back up on top because it's all got the same propulsion system, and everybody flies home. And if you have a bad day and there's something wrong with your main propulsion thing, you fly home in your emergency life raft. So it'll be the second chance on the moon.
Drew, you've had some really long test times, right? What's the longest test time you've had?
You mean to run the engine? A couple of weeks. We've left it running a week or two.
Nice. Hey, what do you want to talk about the materials or anything? We got all sorts of materials we could help out with over here. We can center boron nitride for you if you want.
I buy my stuff off of Amazon.
Yeah, well, boron nitride is that's as good as diamond in terms of dielectric breakdown strength.
Yeah, I don't use any of that.
So it's,
and now I'm not actually gonna talk about the actual materials of it, because we're actually filing another chunk of the patent next week, and I got Ivo out there, and I don't want to give them any ammunition.
Yeah.
Which, by the way,
do.
they're knocking off our patent. I just want everybody to know that.
huh?
They're claiming it's some other nonsense. I don't know. They commune with the aliens or something. But they're knocking off our patent, and they're going to wish they hadn't. But no, I actually have a buddy that grows diamond. And
oh, cool.
And
through electrolysis.
Nah, he does it in that weird thing where you grow it in a vacuum chamber, and you put in whatever it is. What is it? Natural gas or something, I guess. Methane. He puts in methane and he runs a plasma and he grows it one little molecule at a time or something. And it takes him forever. But he actually grows diamond he can make whatever he said, an 8-inch by 8-inch sheet, however thick he wants, however long that takes.
Oh,
but
interesting.
anyhow, he offered me a little tiny piece of diamond, and I'm like, that's nice, but it's useless to me.
That's
because,
awesome material.
My test articles are,
Possibility
whatever. They're 4 inches square.
Yeah,
So
we can center a piece of boron nitride. It's machinable.
you can't make it light enough. It doesn't matter.
It's
read
2 gigavolt per meter. So now you're
it
getting.
doesn't matter. You can't make it light enough.
I read a long time ago. I read about putting diamond coatings on plastic, and I don't remember.
I'd love to see any information you got on that, because we can't find it.
Quantum foam stuff. You do the lattice diamond shell on the outside. You have that quantum foam stuff made up in the inside.
Yeah, unfortunately, I live in the real world, so I actually have to work with stuff I can lay my paws on.
Well, this
all this stuff you talk about, you guys talk about some great stuff.
Within like 2 to 3 years. That's the key.
Okay. So what I had read about could be the process you'd talked about. It might be the natural gas process. I don't think so. I think
it's 800 degrees C is the problem. There's very little plastic that can handle that.
If I remember right, they were 3D printing with a weak electron beam. Basically, you just arc onto the surface, and the electrons created a thin coating of diamond over plastic. That might be something to look at.
That'd be really cool.
Maybe,
but unfortunately, there's an endless number of rabbit holes to go down, and I'm busy trying to create a real future. I mean, I want to get into space before I die.
Well, based on the patent, didn't this go up with the square of the voltage in terms of the forces that's being applied?
Sort of, yeah.
So the higher the voltage, the better. So you would want like boron nitride, ideally, because you're going to get like whatever the weight is, you're going to get the square of the voltage.
What's the thinnest you can make the boron nitride, Michael?
I mean, I can make almost any geometry he might need. Yeah, I mean,
really,
yeah.
But how thin? I mean, my test articles they're half a gram. It's 10 square inches or 0.006 square meters.
Talking about
10 square inches, and you can be able to coat some. And I still got to have a base material.
All right. So if we're talking about 10 kilovolts, what if we went up to 50 kilovolts? Then you're talking about 25x more.
The problem is you can't handle 50 kilovolts in a vacuum chamber. The pressure, you'd have to be 10 to the minus 8.
Boron nitride, you surround it with boron nitride. It has the dielectric breakdown.
It's going to arc around the edges. It's not going to go through the damn thing. It's going to go around the edges.
You put the power supply in the boron nitride. I don't know. I'm just thinking now.
That's the problem. Is you're just spitting out really great ideas, but the reality of it is you can't get above about 15 kV with as close and as small as this stuff is. It just arcs around the edges.
So you build it bigger, you get more thrust out of it.
It's still going to arc around the edges. There still has to be an edge to whatever it is.
But boron nitride, literally 6 gigavolts per meter. You're 50 kilovolts, fine.
It doesn't matter what it is. If it doesn't work, it doesn't matter.
He's saying it goes around the edges. I had to seal edges when I was doing tests like that.
It'll work.
To seal the edges.
What'd you seal them with?
We'll have to build it, Michael, if you want to.
Plastic.
Get over through this.
Yeah, so did I. Yeah, I seal them with 2, but a lot of the plastics, it doesn't matter. They're still conductive. Every plastic is conductive. Even the really good stuff.
So if what you might have had was again, when you're high voltage, you get all sorts of stuff, sweat from your hands if you're using any kind of a plastic.
Oh yeah.
So
I know.
Make sure
I've
use
been
rubber
down
gloves.
the whole thing. I mean, my forte is precision cleaning, so I know what I have to do. I just, getting lazy.
Yeah, I know what you're talking about. It'll ionize.
Just, it ionizes the atmosphere. Just right around the
goes
side.
around the edges.
Right around the edges. And I'm
yeah.
using Delrin as a frame support because, you can cut it with a laser, and, I go through 30 of these things a week. So it's real tough. I actually just today we cut the hole in the middle a little bit bigger so that it's a little tougher for that stupid thing to arc around the edge. But, I'm happy with 30%, 32, 34%.
Well, it's arcing
I
around
hit 36 the other day, but
so
I'm happy where I am.
Is it embedded in epoxy or something? Because why is it arcing around the edge unless it's
because it's a stack. He has a stack of discs, and it goes from one edge. Even if the stacks are asymmetrical, right? The problem is that they're so close together that
they're a mil apart,
sideways, and go around.
But then you would want that's interesting.
Each layer should be in epoxy. Each layer.
It's too heavy.
Too heavy and too thick.
And besides, the epoxy is only good to about 15,000 volts. It blows right through the epoxy.
Well, that's why I'm saying boron nitride. That'll go up.
So Mike, what basically what Andrew is building is kind of a version of a gravity capacitor, right?
I know. But why is weight a factor here? Because of the solid dielectric. Why is weight?
Because you have lots of layers. We have lots of layers. You have many layers.
Experimentation purposes. Okay.
Yeah,
you got to build. You got to build stuff that gets off the ground. So if it weighs, if it weighs 10
size,
pounds,
weight,
well, I mean, I've seen air dielectrics coming right off the ground. They're using a flyback generator to run it.
Yeah. Okay. I live in my world, and in my
there's
world,
there's no solid dielectric there. It's air is the dielectric though.
Shouldn't there
air
be
is a terrible dielectric?
I agree.
It's terrible. It's not even bad. It's terrible. It turns into plasma at about 8,000 volts.
It's a great idea.
Shouldn't there be some geometries that would help that though, if it's thicker at the edges?
No, air is a bad dielectric. It's just not you can't get stability that way.
Yes, there are many geometries that would help this. I've tried them all. I've been at this for 19 years. I'm now where I am. I've chosen the materials, and I gave an update on it, guys. I'm at 30% quantum efficiency, and I'm operating in the
Wait, so how do you
world? Y'all realize what I'm saying? Microwatts. This is going to be milliwatts per newton of thrust.
How do you
milliwatts?
How do you calculate quantum efficiency when it's using electrostatic field? Because isn't that usually with like?
I'm misusing the word. Okay, basically I just say, hey, what's the thing weigh? It's how much thrust does it make divided by the acceleration of the Earth, whatever. So let's say it makes I don't know 1.5. Let's say because my typical one makes about 1.5 milligrams. No, I'm sorry, 1.5. Trying to get the right words. Millinewtons. I make about 1.5 millinewtons. You divide by 9.8, and that gives you the milligrams of thrust that it would be making. And you divide that by how much the thing weighs, and you get basically the percent that the Earth's of the Earth's lift. So if the thing weighs a half a gram, and it makes, let's say it weighs a gram. Just keep the math simple. If it makes a tenth of a gram of thrust, and it weighs a gram, it's a 10% efficient thing. It can lift 10% of its own body weight.
All right, so you're trying to maximize thrust to weight ratio because aerospace applications.
Yes.
Okay.
There is no other application. You always want to maximize thrust to weight ratio.
Well, boats, I don't know, other propulsion systems for other things.
It's still, you have a 10,000 pound engine that puts out 50 pounds of thrust. It's worthless.
I think these would probably outclass boat engines.
They're going to outclass everything.
Even at 10% if the thrust to weight efficiency.
Dude, these are going to outclass ion engines.
Well, my only question for you, Andrew, is
for boats and things on Earth, you could get rid of some thrust weight efficiency in order to.
Yeah, we'll get there eventually.
In order to ruggedize it, make sure there's no losses on the electrostatics, etc.
It's in a sealed box. There's not going to be any losses.
Well, I mean, you could spread it out a little so you can use the epoxy or boron nitride or whatever, and then use
Again,
it.
nothing that you've said has worked. I've tried it all.
Probably.
Tried it
Maybe
all.
boron nitride is not.
For
It
aerospace.
doesn't have enough impedance to it. You know?
Okay.
Boron
Whatever.
nitride is
I've tried
not
it all.
enough impedance. You need something with more impedance.
Impedance
Something
has
more with more
has nothing
impedance
to
than
do with
boron
conversation.
nitride.
What do you say?
Better insulator.
Oh, dielectric breakdown, maybe you mean.
Boron nitride is just not a good enough insulator. That's just it.
What?
You need a better
boron
insulator.
nitride's like the best insulator. Like besides diamond.
Maybe there's something better out there. It may be the best insulator that we know of.
Fair. Diamond and boron nitride are the best we know of, I would say.
Yeah.
Yeah.
Well,
you can't do it with diamonds because.
So Drew, thank you for the thank you for the update.
Very
and then, cool. So we did miss John Brandenburg, I think, unless he makes a last minute appearance.
Well, I could try opening the oven. It's still a little bit hot.
Yeah, easy bake. You're gonna pop open easy bake for us.
We'll see. It's still a little early. I don't know. Maybe Tim. Maybe we should do like an update tomorrow on that or something.
Okay. Grandma's chocolate chip
but
superconductors.
we're here right now.
I know. You know what? I could really go for some chocolate chip superconductors right now.
Right,
Michael?
Maybe even a sneak peek. You don't have to open it. Just a little peeky poo.
Before Michael runs off.
Has anyone else noticed that there's some people out there talking about this stuff being some kind of diamagnetic and not actually superconducting?
It's both.
Oh, okay. 'Cause I don't really know that much about superconductors, but these guys are saying it's standing up on its edge and it's doing little dances
no, it's supposed
and
to
stuff.
do both.
Yeah,
They're
they're
one of the
real worried that this
characteristics.
might just be one and not the other. But I got great hope for this. I don't know exactly what it's going to do. For
What
universe,
Michael
sounds
mentioned,
cool.
Michael read up on the crystal growth. So I think the problem is basically this is what he described, and it makes sense. What he was saying is when you bake this stuff, it doesn't form a homogeneous superconductor. Basically, you've got a couple of compounds. You have superconducting crystals in a semiconducting, and so the problem is
charge through it as it crystallizes.
Yeah, there's a lot of crap that you have to separate out from it to get your superconducting crystals. And so you're going to have mixed results because various people aren't going to know that or pay attention. And so they're going to be testing the wrong thing. That was what he suggested.
The nanocrystal lattice is very important as it forms. That's the key to whether you'll have success or complete failure with such things.
Yeah. So superconductors are perfect diamagnets, and that's actually because the magnetic field induces a voltage in them, and that voltage doesn't self-quench because there's no resistance. So a superconductor should stand up on edge. And again, Michael talked about this. Michael, remember you were saying that it was too heavy to levitate like YBCO because it's more dense, but it should stand up on edge at least.
Yeah, well, it is very dense. YBCO is kind of dense too. I mean, it's yttrium and copper, and yttrium's not so bad, but
it's sintered. It's sintered into a looser configuration, right? Lead is like lead.
You can have a solid block of YBCO, but yeah, I mean it is more dense, I would say, than YBCO, and also the transition the transition to the superconducting state happens basically from 127 to 0 Celsius. So like it's a very wide, it's not fully exhibiting the Meissner effect even around room temperature, I would say. So like you still have to cool it down more. I mean, I can talk about some of the other stuff I was working on today. I got these so we've been waiting for some alumina crucibles in the mail so we can do the proper replication for this for like a week. So I just went ahead and made some myself. This is basically geopolymer. It's a very fine ground silica powder plus sodium silicate plus aluminum hydroxide. And then I can take this, I just ultrasonic, I put it between two plastic cups, ultrasonicated it, and then I'll toss this in the oven next time I open it and bake this. and it'll turn mostly to alumina, and then this should be good for putting the superconductor in next round, and it's a lot bigger than what I have currently anyway. But yeah, it's fun stuff. You can try making that one at home. It's nothing crazy. Just water glass and aluminum hydroxide. But yeah, I mean, we're trying to like get the most out of each like run, because the runs are like 10 hours. So we're testing a few different things. So we had only graphite crucibles at the start of the week. So what we were doing is we coated the graphite crucibles with hexagonal boron nitride. Unfortunately, at temperature, it seems that the boron nitride does eventually fall off of the carbon, and then you have a reducing atmosphere, and we ruined one sample that way. So can't use graphite crucibles at all, it seems, unfortunately. And yeah, the reducing atmosphere just pulls the lead out of the stuff, and then you don't have enough lead to get the superconductor. And yeah, the alumina should work. We also had a small crucible made out of silicon carbide, so that's currently in the oven. We're seeing if that will work. Hopefully it does. And silicon carbide is also slightly reducing. So what I did was I blowtorched it till it was like bright red hot, and that basically coats the silicon carbide with a little layer of silicon dioxide, just quartz. So hopefully that will be enough to prevent the silicon carbide from reducing the lead out of the thing. It's not as good of a reducing agent as graphite at high temperatures, so we'll see. I don't think anyone's tried to make this stuff in a silicon carbide crucible, but that would be good to know, because that expands the range of things that you could make the superconductor in. And yeah, I mean, once I get these alumina crucibles fired, this should do the trick. That should work. But yeah, where were we before that? Oh yeah, so different conditions. So yeah, we're trying a whole bunch of different recipes that are similar to the original superconductor to see if we can get better performance. And also, I suspect that it may be possible to use certain solvents to dissolve the superconductor and reprecipitate it in the same crystal form. So maybe even just dissolve it and then supersaturate the solution, and then throw some seed crystals in there and make like rock candy superconductors this way. We'll see. Anyways, yeah, cool stuff, Andrew. I look forward to seeing those.
Yeah, that spot where you just run out of things to say.
Yeah, yeah.
Hey,
well,
Michael.
gentlemen, before you guys go on. Thanks for having me. I do got a dip. My dinner's gonna get too cold.
Thanks for joining.
Yeah, take it easy and good luck on all your experiments. It's super interesting.
Thanks for joining, Gary.
Have a good night.
Night, Gary.
Jim, you still there? And
hey, Michael.
Yeah.
In your interview with Tim, you mentioned how there might be some kind of solvent that would be really useful for separating out the superconducting grains from the substrate. Have you looked any more into that?
Oh, that should be simple enough to let. Oh, yeah. Well, I mean, yes, there are solvents. I don't know how much I want to say right now, because that process may be very patentable and lucrative. Yeah, there are solvents that can dissolve even lead sulfate.
Wow.
And actually, yeah, you could probably look them up on Google Scholar anyway. But oh, Jared, you're muted.
Are you going to save any of the current sample you're making to see if you can test different solvents on it and
Yep,
try to get that?
Of course.
Nice.
Yeah. Anyway,
last question for you.
StreamYard running on Tim's computer or Jeremy's? I've been kind of.
It's on Tim's, Jeremy's, as well as my own.
Oh, that's good. That's good because I wasn't sure. I mean, on this computer, this is currently Jeremy's computer, so I wasn't sure where to go to check if it was running properly on YouTube. I hope it's been running properly.
Yeah, it's still live on Alt Propulsion, Alien Scientist, my Burn Eye channel, and my Crypto Alchemist channel.
Sometimes people complain about the sound being weird.
Okay.
So Mike, how much mass of superconductor do you think you're going to be making in this as an estimate?
Oh, so the first sample was 1 gram. The second sample, we figured, well, if we're going to take all this time to make the thing, we'll try 10 grams.
Yeah, guys, let me break in for just a sec. So John Brandenburg just called me, and he is going to actually do a presentation for us.
Hey, cool.
He'll be here in just a moment. And
excellent. That should give us enough time to get the superconductor out of the oven.
Okay. Yeah, go for it. Okay, there we go. Sorry, it disconnected my earbuds. So yeah, I'm just waiting for John to enter the studio. And he's going to
before John pops in, one last thing is today we built a horizontal pendulum and made we could destroy the unit, but we made it swing 10 millimeters before it shorted out.
Nice.
So that was kind of cool. First time we actually saw something move with the new design.
Have you tried putting 2 of them on a torsion pendulum and spinning them?
Yes.
Does it? Yeah. Does that work? I mean, because if it's actually doing propulsion, then it should just keep accelerating. Whereas if it's just electrostatics, then it'll just align like a compass with whatever direction the most parasitic capacitance is in, right?
Yes. Yes. Yes, to everything you just said.
All right. Okay. Yeah, that's the good way to test it, I would imagine.
And I do not see John, but he is. I think he's trying to email me a file.
We're way past worrying about whether this is real or not. We're into.
That's good. So you're just optimizing.
We're looking to go to the moon.
Yeah, that's awesome.
I can't wait for the aliens to come down and show us how to do it for real. Although I got to tell you, man, I've been watching that Skinwalker Ranch thing. I am very intrigued with that quarter-second time that they lost a quarter-second of time in their data. I cannot figure out. Now they might just be scamming that. I don't know because. I don't put anything past the company that makes that program. I've had some dealings with them. But...
Hey, Drew. So I know NASA has a really good drop test center that's like full vacuum. Have you looked into testing inside that if you have like a compact testable unit of some kind?
Good idea.
No, I'm not going to have anything to do with NASA.
So to the questions about Jeremy, there were a couple in chat. Yeah, so Mark Sokol is not always here. Jeremy is not always here. I'm probably the only person who's always here because I'm moderating.
Tim is the most.
Mark said he was in Israel this week.
Yeah, Mark's back. Because he has family.
Oh, is he? Good.
Yeah,
good.
He has family there, so he went to visit his family, and then Jeremy's up with Michael. So.
Yep. I forgot there was one more test we're running. So the lanarkite takes a long time to make. So we tossed just the lead oxide, lead sulfate, and the copper phosphide all together to see if we can just avoid having to make the lanarkite initially and just see if it gets the right result at the end. So we're trying that too, because I don't see why lanarkite wouldn't form in the intermediate period unless the copper phosphide ruins that. And even if if the lanarkite doesn't form, then we should still see the copper phosphide pyromorphite material form. I mean, I don't see why the melts shouldn't crystallize into that as long as there's some lead sulfate to nucleate the crystallization, because otherwise you're going to get a glass. Actually, that's one thing we tried also. We mixed everything. We lead, copper, phosphide, copper phosphate, lead oxide, and lead phosphate. And that mixture just made glass. It made a phosphate glass, basically. So the sulfate nucleates crystal growth. In this case, it's some sort of fluxing agent, and it's a catalyst for getting the crystal structure right. Otherwise, you just get a glass. Anyway, that's actually that's probably a very helpful hint for other researchers trying to replicate this. Anyway, I'll stop.
Hey, Michael, one additional thing for it. You mentioned that the citations are going off of a lot of geophysicals and geological type of research. Do you think there's any possibility that any trace amounts of this exist somewhere in the crust?
You would need a place where sulfose salt minerals are exposed to the surface. So, and hydrothermally, it would be tricky to form. So basically, the apatite structure is like a metamorphic thing, and so actually, yeah, you would need an area where you have a not very oxidizing, not very reducing environment, so pretty much hermetically sealed, where sulfose salt minerals are exposed to enough oxygen to react with it potentially, and basically, yeah, it's metamorphosis of hydrothermal activity. So you'd have a metamorphic region on previously hydrothermal areas, and that would be the best bet for finding something like this, because yeah.
So like vents on islands.
Yeah, maybe. Yeah, would be a good place if you want to go around with like a metal detector looking for room temperature superconductors. Yeah, that would be the place to go. Just careful for fumaroles and stuff and whatever else.
I still don't see what the. I mean, I get it. Room temperature superconductivity sounds like a really cool thing, but what's the use of it? Is there a super problem out there waiting for this to happen?
Well, at the moment it's only 200 milliamps, so anything that requires efficiency but low current could benefit from this. I think considering this is just the first of these apatite structure superconductors to be discovered, I imagine that there will be a lot of optimization on that chemistry. So assuming we can have a few amps of current at room temperature, then there's a lot of, like most like household hardware could use that. Transmission lines might be difficult. You would need a way to make large amounts of wire. And even then the amperages are, well, you could do high voltage DC maybe. No, the amperages are too high for that. Yeah, so not transmission lines probably. But yeah, any household electronics, you probably use this.
Okay, so this is going to show up in a chip before it shows up in an electric motor?
Most likely, I think. Oh, yeah, of course. If you can get well, so if you can turn it into wire, then yes, as a motor would be a good application.
Yeah.
So Michael, I had a really good application for this.
Okay.
So if you know how like sleep studies or other things where you're doing EEGs or
superconducting quantum interference devices. Yeah.
So if you got those squids, now all of a sudden you have a mobile MRI machine that can resolve brain waves at like the super fine scale. And if you have that, you have brain-computer interfaces to the nth degree, right? Forget about Elon Musk's whole brain chip thing. You don't need that anymore. Now you have just a hat that you wear.
Oh, now people have a whole new reason to wear tinfoil hats, eh?
Oh, yes. I've got a question for you. I have my monoatomic gold made from 24 karat gold. You can still see some yellow gold.
Yeah. I heard from Drew. Daniel was talking about.
I split it into two, and then I put this one out in the sun, and it turned purple, perfectly purple, except for the straight gold that's still at the bottom of it. And this is the exact same batch. Both was eroded from the 24 karat gold anode. And
that's probably a photocatalytic. That's probably a photocatalytic process on the surface of the monatomic gold species, whatever the chemical is. Gold nanoparticles are purple, so you're probably getting photocatalytic effects, which are generating gold nanoparticles on the surfaces of those, which then block subsequent light. So that's probably what's going on. We would love to take a look at a sample of that now that we understand what Daniel Foster was talking about, more about monatomics and Ormus and stuff. Actually, Bernie, I should come on your channel and let's go into a little more detail about the chemistry.
Definitely. Hey, Mike, do you know how to do silicon monoxide vapor deposition and silicon dioxide vapor deposition?
We don't have vapor depth here, but Mark has a vapor depth unit that you could do that
Yeah,
with.
I'm way ahead of Mark. I was hoping to find somebody that was ahead of me.
Why do you using that for the gap in your capacitor devices or something?
No, I was thinking about something else. Trying to up the resistive strength so I can go to a thinner plastic. I think about putting a couple of thousand atoms of silicon dioxide on there.
So you should take a look at the maybe I don't know exactly your design because you're not talking about it yet, but hopefully you will at some point because then I could help you optimize it better. But have you seen the process that Apple uses to anodize their phones? It's just a sulfuric acid bath within a certain concentration range, and then you just anodize aluminum, and it's a really nice, tough, durable coating, and it's like thick enough that you're not going to get like electrical contact through it.
Oh, that's interesting.
Yeah, that
I could aluminize the plastic
actually,
and then anodize it.
I tried something. Yeah, exactly. I tried.
Yeah, thank you. That's very clever.
Yeah,
I had not thought of that.
Yeah, that'll help you. Actually, I can give you. I have an example here of something I made that way.
And I'm still waiting for. Okay, so John is AWOL.
Maybe he thought it was a different day.
No, I just talked to him on the phone, but it's okay. We'll give him a few more minutes, and if not, I will pester him to present next time.
All right. Just trying to find this thing now.
Because I know anodized aluminum is a very good insulator. Very good because it's alumina. That's all it is.
Yep.
It's nano alumina.
Yeah.
Well, I make all sorts of that stuff, like the clear aluminum, the jelly aluminum, the crystal aluminum.
Yeah, so I didn't even finish the surface of this, but the surface finish you get just from having the aluminum oxide coating is really slick. It's not hard to get the surface looking very nice.
So what process is that? Is that a patented process or just a published one?
Yeah, that's patented. They have it. I think the patent's near expiring, if not expired. But yeah,
it's the Apple iPhone.
Yeah, just
anodizing process.
Yeah, exactly. And they have this. Yeah, it's very you can see the matte finish on this resembles the iPhones. I didn't even sand the surface of this. I just had it machined, and then I just directly did that, and it still came out real nice. Yeah. They just dialed in the right concentration of sulfuric acid or something, and then went with it. Yeah, it's good stuff. Yeah.
Thank you. That's an interesting idea.
I hope it works for you.
Hey Drew, sorry.
You can't really. Yeah, sure. Go ahead.
Sorry to jump around so much. I was curious about another aspect that you might have done for testing. Have you tried any form of vibrations, whether it's low frequency acoustic or even higher frequency radio acoustic vibrations of your sample while it's under test? Because the reason I ask that is if you vibrate it and you get those electrons moving vertically or horizontally at the same time with the proper Lamb wave mode, I'm just guessing it might be possible that you could induce some additional Lorentz forces into the thing that would increase your lift. You might be able to add basically a magnetic moment to the thing by vibrating the electrons with mechanical motion at the same time that you're just having that electrostatic force.
We have not done any of that because.
Sorry to interrupt. I have to take off, guys. Excellent episode today. If the other presentation happens, by all means, keep her screaming. And thank you, everybody, for all you're doing. I'll have to do follow-up outside of that as well, Michael.
Thanks, Bernie.
Yeah, Bernie, thank you. And again, I'm going to give it a few more minutes for John, and if not, I'm sure that we can push back until the next one. So
much love.
What about in regards to controlling the arcing? going on? What about surrounding the dielectric with a coil slightly energized to EMF controlling the arc?
No.
Eliminating it.
It's going to be a stack of thousands of sheets of this plastic.
Well, how thick can it possibly get? I mean, one coil will definitely cover that thickness, around it. And if you give it low voltage,
Why would a coil do anything? It's an electrostatic.
Well, it generates EMF
capacitor.
fields. It generates EMF fields, which can limit your, just like they do with plasma when they, control plasma in a fusion experiments. They use EMF fields to keep it from touching the glass, so it don't melt the glass. Same concept for the arc. You can control,
Well, the goal is not to have the plasma. Because if you have plasma, that means you're sucking up energy.
I never
you've gone from electrostatic to electromechanical or electromagnetic.
Yeah, no, that's not what I'm saying. I'm not saying having plasma at all. I'm saying in plasma experiments, they use an EMF field to control the plasma from touching the container.
That's because they have plasma.
Right.
The goal is not to have plasma.
You also have plasma. You also have plasma.
I only have plasma when the things
arcs are plasma.
You're missing the point. The only reason I have plasma is because I have a problem. The goal is to get a deep vacuum and not have plasma.
If you got high voltage arcing going on, you could use EMF fields to push them back in instead of just like they do with plasma.
No, I don't think so. But I'll think about it. The goal is to simply go deeper in the. I mean, I have a fairly small chamber. It's only it's only whatever it is, 24 by 48.
The article is no more than 2 inches square.
I have a stupid amount of pump on that thing, and it still takes 12 hours to pump it down. I just want to go play with my toys, so I just don't give it enough pumping time. I've been pumping all day. I'll probably let it pump all night again. And tomorrow morning, it'll be 4 times 10 to the minus 6. And I'll be able to do 15,000 volts with it. The problem is I want to change that thing out every day. So there just aren't enough hours in the day to change it out, pump it down, and play with it.
Have you thought of using like SF6 gas or something that doesn't ionize as easily?
I have. I actually have $3,000 worth of SF6 in a bottle. The problem with SF6 is it's great as long as you don't have an arc, but if you do pass an arc through it for any reason, you end up with fluorine.
Yep.
And fluorine is really bad for turbos.
So what you do in that case is, in the SF6 gas, you include a titanium wire that you heat, and then it captures the fluoride.
Yeah, you can do titanium sublimation.
Fluoride isn't great either, but yeah.
Yeah, none of that stuff is great for the turbos.
It's less bad than fluorine gas.
That actually isn't the future though. Once I get done with the vacuum testing and I lock the design and I lock all the other parameters and stuff, but the problem you run into is nobody believes you unless you run it in high vacuum.
Yep.
Because everybody thinks it's ion wind or it's, I don't know, any of the other 100 things it could be. So you have to run it in high vacuum in order just to make anybody believe you. It doesn't matter who they are. If they've ever heard of this field at all, then they've been poisoned by all the lunatics that are in it. And you have to go above and beyond. You have to go beyond extraordinary in order to get anybody even paying any attention to you. So we went to the extraordinary state. We operated 10 to the minus 6 vacuum, which is, an order of magnitude below anything that ion wind could even be remotely envisioned in. So right now we're just playing around in vacuum. But yeah, in the end, I think I'm probably going to end up with SF6 once I have a stack that I'm happy with, because the containment device, the box, I can print it on my printer. Not this printer, that's a toy, but I have a serious nylon carbon fiber printer outside. And, SF6 lets you pressurize at room temperature, or room temperature, room pressure. And then, when we get into space, we'll just vent. And then we'll just operate at, 10 to the minus 8 space. So that's the plan.
Just do me a favor and give this a shot. It's not expensive. It's a boron nitride mold release. You can
I know exactly what that is. Yeah.
Yeah, you can just coat your thing with this, See if the boron nitride like reduces the arcing. Just give it a shot. It's a cheap kind of thing. You just spray it on there. It's a thin layer, not heavy or anything.
All right.
Cool.
Man, you're just a source of great ideas.
Yeah. If I had more info about your device, I could.
Well, we need to hook up and.
Okay. Okay.
about
John is here.
Tim can get us in touch. Let's go to John.
Yeah. I definitely want to be in touch, Michael.
Okay.
Sure, you need to have Michael sign an NDA so it can help you.
I totally agree.
Okay, we have Mr. Brandenburg with us.
And get a cup of coffee, and I'll be set to go here in a second. Okay.
Okay.
By the way, how did the high temperature superconductor experiments? I'm sorry, I had to leave. Something unplanned happened.
It's still going. It's still in the oven. Haven't been able to take
still
it out.
in the oven.
Yeah.
Okay, you guys, listen carefully. Listen carefully. Try nickel. Take ordinary nickel, copper, nickel alloy, grind it up, make it into oxide. Try that.
Well, I saw the DFT simulation said nickel wouldn't work.
Ah, and you believe them.
All right, we'll try it.
No,
Thank you.
Nickel is nickel has some chemical similarities, believe it or not, to lead.
Mm-hmm.
And it's also the only other substance they've gotten to make a high temperature superconductor out of. It doesn't work as well as copper.
Mm-hmm.
But hey, I just got this brainstorm.
Have they gotten tin to work? Because that has +2 oxidation state.
Nickel even has +4 apparently.
Well, but that's not useful in this case because it has to occupy a +2 lead site.
Oh, okay. Well, anyway, if you got some time on your hands and want to try something crazy, I mean, the original.
Yeah, we're gonna run through. We're gonna run through everything in their patent for sure.
What?
And a few things that they. We'll check everything that they had on their patent and a few other things.
Okay. It's my understanding the original high temperature superconductor, which is, by the way, just improved copper, was done just kind of as a crazy experiment. They had no theory to, try it. They just tried something.
Huh.
So, and then it worked. And then they published it, and they had liquid nitrogen superconductor, which is liquid nitrogen is a hell of a lot cheaper than liquid helium. I'll tell you that.
Yep. The slow march of progress.
And I believe this lead thing is going to turn out to be real, but lead is heavy.
Yeah.
And also toxic. I just think nickel. Intuitively, by the way, I guess that if they mixed some silver with the original stuff, this was a long time ago, it would work, and it did. So, hey, my intuition is not bad on these things.
Yeah,
that's crazy ideas.
So I checked that too. I checked all of the atomic radii. I checked everything that would squeeze the lattice, and there's silver, cadmium, nickel, copper, tin. Yeah, basically all of those are in their patent.
Okay, now interestingly enough, lead makes a very good, cheap superconductor at liquid helium temperatures.
Mm-hmm.
Copper never would superconduct at reasonable even temperatures. But and of course, no one still knows how the lanthanum copper thing works. I've never seen a theory that made any sense. And so still a time to try crazy things.
Yep. Very true.
Especially if you got a nickel in your pocket.
And a furnace.
And a furnace. You got a nickel and a file.
Yeah, everyone who's got like borosilicate glass tubes should be blowtorching samples into them and vacuuming the air out of them and putting them in. Even if they have a normal furnace, everyone should be doing this. So everyone on this list.
It strikes me that the South Koreans tried something crazy and it worked.
Yeah.
The only problem is it's heavy. That's why the pictures of it levitating, part of it is always touching because it's heavy.
Yeah, I mean, it's a lead salt. It's to be.
It's a lead. It's
Yeah.
full of lead. I mean, that's not exactly what you want in power lines. You know what I mean?
Yeah, yeah.
So,
Okay.
well, anyway.
Well, so let's do this. So I'm going to.
So there's
so
my
guys,
helpful suggestion, and I'll tell
Thank
you
you.
the reason I did it.
we
is
will
'cause I
we
put
will
it
wrap
in a
things up
statistical
with
story.
Dr. John Brandenburg then.
John
So
was saying something at the end there. What was that, John?
The reason I want you to try it is I put it in my science fiction novel about the great AI singularity war,
Nice.
and it makes the asteroid belt a gold mine because they need all the nickel they can from the asteroid belt.
That's funny.
And so anyway, so it's the novel is called The War of the Singularity. I'll post it. But anyway, anyway, just try that crazy idea. That's a free idea and worth every penny.
All right.
It was in my science fiction novel, and a lot of other stuff in my novel will come true,
Nice.
including fusion power.
We'll try it.
Okay. Very good.
Okay.
Very good. Keep trying. Okay. Yeah. You got a nickel? Grind it up. Make it into oxide.
Well, maybe not debasing currency, but we have actual nickel around.
You might get in
Yeah.
trouble for that. You know.
Yeah.
Okay.
So
yeah. I
yeah,
guess
let
I'm
me.
ready, Tim.
Oh,
I'm
okay.
ready.
Okay.
You got my presentation, right?
Yeah. And
Okay.
let me see. I'm
Yeah,
going to put
Tim,
the
it's
presentation
an
up.
honor and
John,
pleasure.
can you may be able to, let me see. Is it going to give you the controls to use that slide? Move your mouse over it and see if it's giving you mouse controls.
Okay.
If you put your mouse
Doesn't
over it,
look
just
like it.
doesn't. Okay.
Getting no joy on this. Wait a minute. Nope. I'm pushing the it's a PDF, and I normally, you have to click on the
Yeah.
edge of the PDF. Next time I'll be better prepared. Anyway.
Oh no, that's okay. And yeah, okay.
Just imagine if this nickel thing turns out, Tim, you'll be famous, and so will this.
Let me remove myself. Oh, so I'm gonna remove myself from the studio now. You try to
okay.
You try to do it. Okay. Oops. And nope. Okay, I'm gonna remove my.
Okay. Now it looks like this thing will have to run with you. Can you advance it? Tim?
Yeah, sorry. Yeah, John.
Okay. Can I just say next slide? Will that be
absolutely?
Will that work?
Absolutely.
We'll be better set up next time. I'm sorry, this is done a little.
Oh no, that's okay.
A little
that's
bit
okay.
on
Yeah,
the fly.
just let me know when to do next slide, and we'll roll with that.
Okay. Yeah. Let's start with the just the cover slide.
Okay.
Go back one. Okay, I'm going to talk about something remarkably sad that I've discovered after many years of work. This is evidence for massive thermonuclear explosions on Mars in the past. This was the whole genesis of this was that I was working at Sandia National Labs, and guy was a nuclear weapons expert, was interested in my work on Mars because I was looking at a page in a scientific journal that had Mars isotopes. We'll get into that. Mars nuclear isotopes in the atmosphere. And he looked at the pictures and he suddenly turned to me and he said, "Somebody nuked them." He says, "That's nuclear weapon signature in the atmosphere." And then he looked really embarrassed, like, oh my God, I've said something I shouldn't have said, and excused himself. And we were actually in the library at Sandia Labs. It was an unclassified area, and he realized he had said something classified. And so he walked back into the classified area. He's just, and this happened occasionally. Sometimes people would just say things and then they realize, oh, I shouldn't be saying this in this area. So I never saw him again. But I've showed this to other nuclear weapons experts and they agree with me. So, or agree with his assessment. But this business is like Wall Street. Those who know can't say, and those who say can't really know. I had to find everything out from the open literature that I'm going to show you in this talk. So talk to you anyway. Here's okay, evidence for massive thermonuclear explosions on Mars in the past. Okay, next slide. Okay, everybody knows we live in a violent universe. The brightest of all time, gamma ray burster, probably sterilized most of the galaxy if it was in it. If there was anything alive in that galaxy, it's probably dead now, or has to recover. So the universe is both dangerous and beautiful. Next. Next slide. Okay, this is of course our planet. I want you to notice, by the way, this is a view of the Sahara. You can see the Kalahari deserts and also the Arabian desert. What color are they? They're bright red. Next. Next slide, please. Okay, and of course, this is Mars, which is the first Earth-like planet in the rest of the cosmos we can look at. And you'll notice it's bright red also. It turns out that is important for this discussion. So it's the first, it's the first Earth-like planet in the rest of the cosmos. It's Earth-like only in the most abstract sense of the word. It's more almost lunar because its atmosphere is so thin now. But it does have an atmosphere. It has polar caps. Next. This is what it looked like in the past, apparently. And by the way, I am the person who discovered the Mars ocean. You can check out the Wikipedia page, Mars Ocean Theory. I'm reference number 1. I gave the evidence for a Mars ocean in 1986 to a room full of Mars scientists. But I am known as a dangerous troublemaker on Mars, as you will see. So they don't give me any credit. But credit I can get from a bank. Anyway, next slide. This is what Mars used to look like. Okay, I have recently published an article that actually is revisiting an issue I raised 30 years ago. This type of meteorite is called CI carbonaceous chondrite. They're 4.5 billion years old. They're as old as the oldest meteorites from Mars they found now, as old as the Earth, in fact. They were formed in warm water. It's clay formed in warm water from lava, and it's 2% organic matter. So early Mars was like early Earth. It was warm, it was wet, and it was soaking in primordial soup. And that means if life began on Earth under those conditions, then empirically, who knows how, life probably in all likelihood began on early Mars, so that both Mars and Earth began their histories in this solar system as living planets. And this is the reference. It just came out last week. Next slide. So Mars was a living planet. The CI carbonaceous chondrites coming from Mars, they're 4.5 billion years old. Something happened on Mars in recent geologic time. We're talking like about 500 million years ago, somewhere between 300 and 500 million years ago. 300 million years ago was the great Permian extinction on Earth, but anyway, I published that in a refereed scientific journal out of Switzerland. The other scientific refereed scientific journal, by the way, with the CI for Mars, that's in a journal in Britain. American journals are very hostile to these ideas, and they won't publish them apparently. Anyway, here's the book. Death on Mars is something you can read about to read the whole history of this investigation and discovery. Next slide, please. Okay, I'm going to talk quickly about, I'm going to try and keep this to like 45 minutes. Mars, past and present. What destroyed Mars? Why is Mars so different than it used to be? Xenon is an inert gas that likes to stay in the atmosphere, and so it makes a wonderful tracer for the geochemical history of Mars. Krypton is another inert gas. Then there's nitrogen and argon isotopes. Then there's potassium and thorium. And then there's energy release estimates for what happened on Mars. A tremendous thermonuclear holocaust. And then I will summarize. Next. Okay, we know that Mars is covered with extinct water channels. Now, this area where this picture was taken is on the youngest part of Mars. That's where the ocean was also. You can tell the young parts of Mars because they don't have a lot of craters in them. But there's also water channels in the very old parts of Mars. So Mars apparently had liquid water on its surface for most of its geologic history. Next. Of course, this is what ancient Mars used to look like. Next. When the Mars polar lander landed, they landed on the old ocean bed. And they found water ice right under the surface. The soil also they found can support life. This idea there's some kind of toxic chromium in there, that's not true, apparently. You got to realize the people running Mars academia in this country are rock geologists. They don't want to find life on Mars. Mars would upset the whole apple cart. So soil is consistent in the northern part of Mars with it's salty clay, and it's consistent with an old ocean bed. So the old Martian hypothesis, Mars ocean hypothesis, and by old, I mean probably only 500 million years old. Next, it's confirmed. So what changed Mars from being an Earth-like planet to being its present deserty, kind of almost lunar desert state with its atmosphere only about 1% of the Earth atmosphere? Its old atmosphere, by the way, had to be close to atmospheric conditions on Earth. Otherwise, you couldn't have liquid water. And you couldn't have a greenhouse, CO2 greenhouse on Mars that would give you temperatures for liquid water. Next. Next slide. Okay, here's, by the way, Mars is accident prone. It's right next to the asteroid belt. By the way, here's the boundary between the old ocean bottom and the north of Mars. You can see heavily cratered, very rough terrain. And then suddenly, at just about the same elevation contour, it becomes really smooth and hardly any craters at all. That's how we know there was an old ocean there. And that's how we know that ocean lasted until most of Mars geologic history, because there's hardly any craters. Look at all the craters here, but the water, presence of an ocean, smoothed out all the craters, except for the very recent ones after it dried up. Next slide. Okay, Mars had a catastrophic climate change, possibly due to this Leo impact. The impact I showed you was as big as the one that wiped out the dinosaurs on Earth. Happened on a planet 1/2 the size. And we can tell from the rate of water channel formation on Mars that there was a big dip just about the same time as this Leo impact crater formed. However, Mars then, as you can see from the red line going up, recovered. So they found very recent in geologic time water channels on Mars. Probably, yes, like I said, only 300 million years ago. Mars was accident prone, but like Earth, recovered from various mass extinction events, especially the Chicxulub event. Mars recovered. Okay, next slide, please. Now, why did Mars die? This is by a picture, by the way, of one of the Shoemaker-Levy comet. It wasn't a comet, it was an asteroid impacting Jupiter. But it gives you the right, what probably it looked like from far away when Mars, whatever happened on Mars, happened. Next slide, please. Why did Mars die? The evidence from the isotopes is of massive nuclear events on Mars 180 million years ago. The evidence is that Mars xenon is different from every other major reservoir in the solar system. We've parachuted probes into the atmosphere of Jupiter. We have our own atmosphere we can sample. We have ground up meteorites. We have samples of the solar wind, and they all show xenon 129, one isotope of xenon, is almost identical in abundance to xenon 132. Those are the two most abundant things. But on Mars, different from every other major reservoir in the solar system, xenon 129 is 2.5 times the level of xenon 132. Also, there's a lot of krypton 80 in the Mars atmosphere and also trapped in the rocks. And this is formed by intense neutron bombardment. Not only that, argon 40 is formed by intense neutron bombardment of the potassium in the rocks. So there's other isotopic evidence, and then there's thorium potassium scars on Mars surface, two hot spots in the north where apparently something happened. Next slide. Okay, here's Mars xenon mass spectrum in isotopes. As you can see, it matches Earth very well, except the blue points are Earth. It matches Earth very well, except at xenon 129. So something created a whole bunch of xenon 129 all at once, apparently. And it created it recently in Mars history because the very most ancient rocks on Mars don't contain this xenon 129 excess. Next slide, please. Now, where do you get a bunch of xenon 129? Well, one clue is the meteorite Allende. Fell in Mexico in 1969. It's one of the most studied meteorites in science. It exploded in midair. Hundreds of fragments were recorded, and the rock is 1.456 billion years old and contains pre-solar grains, things that predate even the solar system. Next slide, please. And it has a big excess of xenon 129 too, but the rest of it kind of matches Earth or Mars. Now, what do they think happened to this meteorite that never has been to Mars, by the way? It was made of stuff that was formed from the original solar nebula and stayed that way with even pre-solar grains. Next slide, please. The isotopic evidence showed solar system condensed from supernova products. The solar system we live in now is the result of an explosion of a star, apparently. Supernova in the neighborhood. And the physics of supernova explosions makes a lot of all of the heavy elements that we have, like uranium and thorium, and it's characterized by what's called R process. R process, R for rapid, meaning rapid neutron bombardment of a lot of stuff. Next slide. Now, we have enough meteorites of the same type as El Yande to understand that Earth and Mars and the rest of the solar system formed out of this pre-solar stuff. And there was a spike in xenon-129 in this stuff, and it was because of the way it formed from supernova remnants. Now, on Earth and every place else in the solar system, there was a bunch of other stuff that decayed, like uranium and a substance called plutonium-244, which was discovered on Earth. And they decay and they make up the rest of they produce a lot of xenon-132. But you can see that our process, the process that occurs in a big supernova, creates all this xenon-129. Next slide, please. Okay, now, why do other people think that the xenon-129, this has puzzled people for half a century. They discovered this when they landed on Mars, the two Viking landers. They picked up the xenon-129 excess. Okay, the model is Mars lost an early atmosphere. It had a bunch of iodine-129, which decayed with a 16 million year half-life. The resulting xenon-129 outgases, forms a new thin layer. However, what's also supposed to happen, the other shoe that's supposed to drop, is plutonium-244, which has an 80 million year half-life. It decays after the iodine-129, together with some uranium and thorium isotopes, but also outgas, making xenon-132 and xenon-129 basically one. That's what you find on Earth. You find it on Jupiter. Things like this. You only find the xenon-129 excess on Mars as a planet. Next. Okay. Plutonium-244, when it decays, makes a lot of xenon-132. And so does the decay of like uranium and thorium and things like that. They don't make xenon-129. Next slide, please. So when did the xenon-129 excess appear? Apparently, in the oldest meteorites, like Chassigny and things like that from Mars. You can see here on this graph, and ALH 8401, another very ancient meteorite, and the very interior of the rock, there's no xenon-129 excess. It's roughly 1. It's only in the Mars atmosphere and in recent Mars rocks that have formed recently from lavas on Mars in geologic time that you get the xenon-129. So it was not there at the beginning. It happened later, much later in time on Mars. Next slide, please. Okay. Here's some nuclear processes like occur in like a natural nuclear reactor, which you could have on Mars. You had them on Earth. Those were on what's called slow process because they have to use on slow neutrons, moderated neutrons. The water slows down the neutrons, makes them more reactive. So as it turns out, when you run a natural nuclear reactor, you don't get any xenon-129 at all. You get very little. You see that where it's redlined. The ratio of xenon-129 produced to 132 produced is only 1/10. Xenon-132 is, of course, produced because it's a very favored nuclei, and it's 1-to-1. So next, that's S process, slow process, not a supernova. Here's a supernova. It produces a spike at Xenon-129. As you can see, it produces 1.5 times more Xenon-129 than 132. And on Mars, there's 2.5 times. So whatever happened on Mars resembled a supernova. But we know no supernova could have occurred on Mars in recent times. There wouldn't be a Mars planet left. There wouldn't be a solar system left. It was not a supernova. Well, what is the only other thing we know of that makes our process? Next. There are only 2 known R process physics events. There's supernovas, and then there is a hydrogen bomb going off. Believe it or not, they use pretty much the same physics. When we make a hydrogen bomb, we're basically emulating a supernova in physics. These are the only 2 known events that do this. So the only known thing that can cause that Xenon-129 excess on Mars is an enormous hydrogen bomb explosions. Next. Okay, when you have an R process explosion, a thermonuclear explosion, it also radiates a whole bunch of neutrons. This creates enhancements in what's called krypton 80, because krypton 80 is very favored to form when you get neutrons hitting bromine 79, which is in the rocks. They've calculated it took a neutron fluence of 10 to the 15th centimeters squared is required on Mars rock. They had to put rock in nuclear reactors on Earth to simulate the number of neutrons that they were hit with. Next. So the isotopes of krypton isotopes, like xenon isotopes, don't look like Earth at all on Mars. They look like the sun, which is a solar furnace. Next phase. Next. Okay. The major isotope of krypton is krypton 84, and when you measure the solar wind, even, or Earth, Mars has a lot more krypton 80 than, and krypton 82, another one formed by neutrons, than anything from either from Earth. Next. And the 2 anomalies correlate with each other. Whatever happened on Mars that created a lot of krypton 82, 83, and 80 also created a lot of krypton 84, which is a product of nuclear explosions. It also created the Xenon-129. Next. So other isotopes on Mars indicate intense neutron bombardment. Nitrogen-14 absorbs a neutron in the atmosphere and makes nitrogen-15. This was a terrible thing about the neutron bomb. If you set off a nuclear weapon, especially one that's enhanced to give more neutrons than anything else, it makes a lot of gamma rays. Okay, if you know where the thing happened in the sky, you can hide from the gamma rays. You can duck and cover, literally. However, the neutrons hit the nitrogen in our atmosphere, which is primarily nitrogen-14. They form nitrogen-15, and it emits a gamma ray, and the gamma ray comes out in every direction. So you actually get heavy gamma rays coming down from the sky that can kill you after a neutron bomb goes off. It doesn't do any good to protect yourself from the direct gammas from the bomb. The gammas from the atmosphere produced by this nitrogen-14 reaction will also kill you. Not only that, when you set off a neutron bomb, it hits the krypton, potassium in the rocks and forms what's called argon-40, and it forms it promptly. So there are two, and there's a lot of nitrogen. There's a lot more nitrogen than there is krypton and other things, and there's a lot more argon than there is krypton or xenon. And both of them show evidence of this massive neutron bombardment late in Mars history. It's not in the early rocks with trapped gases. Next slide. Okay, well, anyway, yes. Nitrogen-14 forms nitrogen-15. And so Mars' atmosphere is loaded with nitrogen-15, much more abundant than on Earth in proportion to nitrogen-14, and also makes this argon-40. So there's far more argon-40 in Mars' atmosphere versus like argon-36, which is just fairly inert. So both the nitrogen and the argon, along with the krypton and the show that there was a massive neutron bombardment of Mars late in, and it's found in the younger meteorites, not the really old meteorites. It's the younger ones that are only, in some cases, 300 million years old. Next slide. So we have meteorites from Mars. Well, this is ETA 7901, one of the first meteorites to be even identified from Mars. And parts of it show no neutron irradiation at all. And then what the neutron irradiation is found in what's called nodules of melted regolith, where the lava flow apparently flowed over Mars' surface and picked up surface rocks and melted them, and they became part of the rock. And they are the ones that hold all of the neutron irradiation. So the neutron irradiation happened in a short period, apparently, and may have actually stimulated this lava flow on Mars that picked it up. But the lava itself was not exposed to the neutrons. It was only the surface rocks it melted and incorporated. So, next slide. Okay, a test for this R process is to look for plutonium-244 in Mars samples, in the Mars meteorites. It's a difficult thing to predict, to find. It doesn't emit gamma rays, which are easy to detect. It emits alpha particles, and it has an 80 million year half-life. So we're looking for a recent event on Mars that made plutonium-244. I mentioned this because plutonium-244, people didn't know it existed until we set off our first hydrogen bomb, and then we found it in the residue. Next slide. Now, where did these events apparently occur? They occurred apparently in the north. There are hot spots in potassium. If you irradiate rocks with neutrons, the potassium, some of it becomes radioactive and stays radioactive for billions of years. It has a long memory. And there are two spots of relatively higher radiation from potassium in the north of Mars, where the ocean used to be. And then there's apparently a place where shock waves wrapped around the entire planet and collided with themselves on the far side of the planet in the southern hemisphere and formed another hotspot. Next slide. This is also found in thorium. Thorium has a hotspot, and thorium and potassium are not very much correlated in nature. You get rocks that are rich in potassium, other rocks that are rich in thorium. But on Mars, the radioactive thorium, which lasts a long time, billions of years, is coincident with the radioactive potassium, which is formed by neutrons. Thorium is just naturally radioactive. And once again, you have this same antipode deposit on the far side. Next. Now, as it turns out, Mars rocks have a lot less thorium in them, or not, lot less potassium in them than Earth rocks for some reason. It's the kind of lava that forms most of Mars' surface. And what's really weird is the rocks we get from Mars, the Mars meteorites, they don't have that much potassium in them. But on the surface, there's apparently a thin layer of radioactive potassium in every place. They wouldn't be able to detect it unless it was radioactive, I mean, from orbit. And there's also a place where there's a lot of thorium. So the Mars rocks have very little potassium and thorium in it, but there's a thin layer of potassium, radioactive potassium and thorium, which is naturally radioactive, on the surface. You can see that. The blue points are what they measured from orbit. The red points are what they measured in the actual Mars meteorites in the laboratory on Earth. Next slide. Okay, so it looks like there were two R-process events on Mars. Thermonuclear explosions of massive energy release over the north of Mars. There are no craters at the sites. There's no craters, there's no volcanoes there, there's nothing. It's just smooth. What there is by the way, a lot of glass. Acid etched glass formed by glass, which was then etched by nitric acid, which is also a product of nuclear explosions. They were air bursts, apparently. Next slide. We've seen things like this on Earth, not only at Hiroshima and Nagasaki, but we had a meteorite come in and burst in midair. It was about a megaton worth of energy. That was Tunguska. However, it made no radioactivity. The Russians are very good at nuclear science. They checked thoroughly. There was nothing nuclear about the thing in Siberia. It was just a big rock or comet that blew up in midair. But it didn't create a crater either. Next slide. We can estimate how much energy was released based on the Xenon 129 R process, based on the Krypton 80, and it's 10 to 100 times the amount of energy released when the Chicxulub impact occurred on Earth. This was a global catastrophe. It blew most of Mars' atmosphere off the planet. This happened, this was 10 to 100 times more powerful than the Chicxulub event, and it happened on a planet only half the size of Earth. Now, I published this in a refereed scientific journal now. There was the access at the, you can see the link in the very first slides. And I'm sure Tim can make it available to you. Everybody can read it. Next slide. So in summary, Mars climate may have changed catastrophically from Earth-like in recent geologic time to its present state. Evidence points to massive R-process events, and by that I mean thermonuclear explosions, approximately, we're still trying to nail down the date, probably somewhere between 500 million and 500 million and 300 million years ago on Mars. They were air bursts. Of course, we don't know what caused this. One way to find out if this can really confirm this is look for plutonium-244. If it happened that recent in geologic time, there should still be traces of it. Next slide. Okay. My friends, there's massive evidence for a thermonuclear holocaust on Mars. And it changed Mars from being a living Earth-like planet like Earth to one that has only a residual biosphere, making a little bit of oxygen and methane in the spring and fall on Mars, in the spring and summer on Mars. This does not appear to have been natural. These were air bursts. Somebody suggested, well, maybe there was some kind of weird solar flare. No. If it was that easy to make fusion, I work on nuclear fusion, we would have fusion power already. Besides, a solar flare does not have a lot of thorium in it. Thorium is found in nuclear warheads. They use it to enhance the yield. They look up W71 warhead. It was the big Amchatka test that they did up in Alaska. That was full of thorium, as it turns out. Now we have to go. So this happened on Mars. It does not appear to have been natural. We have to go up there and find out what the hell happened on Mars. Boots on the ground. We have to send up people with shovels and sharp eyes. I have no confidence in Jet Propulsion Lab. They have been looking at this same data for half a century now, and they never connected the dots. Never mind why. But only going up to Mars and finding out what happened, digging down like 6 feet through the dust and finding what the surface looked like when this happened, it's the only way to ensure it won't happen here. This is no longer an academic investigation. This involves the survival of the human race long time in the cosmos. I'm sorry, friends. The way I connect the dots on this, it looks like Mars was targeted for a nuclear attack by somebody, dropping hydrogen bombs as big as the Empire State Building. Now, what this means is that we are not only not alone in the universe, but we live in a tough neighborhood. In fact, I would say the message of the whole UFO experience and the message of Mars are the same. The rest of the universe is just as screwed up as this place is. Human race, which is not a bunch of angels, as you know, is typical of intelligent life in the universe. So we have to go up to Mars, find out what the hell happened. This is a job for Space Command and Houston. We have to send people. This is a people problem. By the way, the same people who want to replace all humans with robots in space also want to replace you all and your grandchildren with robots too, a lot of them. So they are not going to be allowed any leadership role in this thing. This is a human problem and it must be solved by human beings. We can discover all sorts of things about Mars with robots, and we have. But we will not discover, the only way we can discover how we will go to Mars is to go there, and how we will become spacefaring as a species is we go to Mars and we become spacefaring and we find out what the hell happened up there to make sure it doesn't happen here. I'm sorry, in God we trust. We just have to get through this difficult period of finding out that we're not only not alone in the universe, but there's a lot of people out there who are like us, and that's good and bad. So that's my talk, my friends. And as I said, you can read about this in the book Death on Mars, but the scientific article is very recent in a referee journal, and also the scientific article showing that early Mars and early Earth had similar conditions, therefore life started on Mars. Mars was a living planet when this happened. Thank you. I have Tim, you're in charge. I can answer questions if there's time.
Okay, well, let me see. I'm not sure if we have questions. I should mention that Jared has questions. We can give it a couple of moments. I'm losing battery power on my earbuds. So, yes, it has been an all-day run. Hey, you know what?
Oh my God.
We have had one heck of a conference. We have had one heck of a conference.
Tim, this
okay,
is magnificent.
well, let me do this. Let me add everybody in here.
Okay.
Oops, Drew's
you
not
guys.
there. Okay, we got 4 folks here. Big
Fire
hand
away.
of applause from
Thank
Dr.
you so
John
much.
Brandenburg.
By the way, this is sad and tragic news. But the good thing is that we know it now. We know it.
About the earbuds? No, I could just recharge them. It's easy.
Sure.
Yeah.
Ask your AI what to do. I'm sorry.
I got the little case here. So.
Oh, yeah.
Okay. Well, let me see. Jared had some questions.
Jared, please ask. Fire away.
All right, Dr. Brandenburg. First off, I love hearing all of your research on this topic so much. I can't express it enough. I got 3 questions, and we may only have time to get to 2 of them.
Yeah.
All right. So you said 10 to the 26 joules. Quick calculation, back of the napkin. That's a 24 exaton nuke.
Yes.
Okay.
I know.
Hurts the
it's
head.
It's just almost incomprehensible.
Yep. So
the Mars atmosphere, nitrogen may have ignited when this happened.
To me, that sounds like the only possible way you're going to get that kind of density of energy is if it's an antimatter nuke of some kind.
It could, I just took what we know from nuclear tests on Earth and from, by the way, I went to school at Lawrence Livermore National Lab. That's where I got my PhD. They use the same codes to model supernovas they did to model bombs. That's how I know that this physics, they would say, oh, we got some great supernova simulations out of this, this bomb code.
John, now that we've got you here on our StreamYard thing, I want to bring you back in the future. So you have to give some thought to more talks that you can give.
Hey, there's more. Yes, but this is the base. I've given you the basic.
Well, let me do this. I'm going to email you
as they're now published in a refereed scientific journal.
Yeah, I'll email you after. I'll email you after the conference.
Great.
And I have cleanup to do tonight on this. But yeah, I'm really excited. And you'd said some kind words when we first talked. We've been working really hard on the conference, but also this whole community.
It really shows, Tim. This is really, really beautiful.
Well, thank you. It's a group effort. It's a group effort.
I've been actually very distracted getting this stuff published in referee journals now.
Well, it's good to publish it, but when we can steal a few moments of your time for a presentation, I'll always do that.
I'll be filling you in on all. I have other scientific articles on Mars that are being accepted for.
Yeah.
What's interesting is people read the thermonuclear holocaust on Mars. This 2 scientific journals said, please send us your stuff. One's from India, one's from Britain. So
there you go. Yeah, I
there
know
you
the
go. I
U.S.
responded
is
to
a
the
little
British
bit
one. I'm
recalcitrant.
responding to the one from India also.
Can I ask my second question here?
Yes, Chair.
So the locations, you said that at least one of them was over the ocean. I was curious, these are airburst. So when you have an airburst nuke, that's an EMP. You're not doing it necessarily to destroy land, although at this amount it most certainly would. But for the locations of these, is there any way that you can try to track the evaporation or the reduction in the oceans and the coastlines especially? The reason I say that is because 90% of the world's population lives within like 20 miles of the ocean. So
Right.
that would make sense for these locations, these explosions, to at least the airburst, depending on the altitude, it would make sense to knock out with that EMP.
It would create enormous tidal waves in the ocean. Sadly, the bombings at Hiroshima and Nagasaki were airbursts. You don't find any craters there either. And the reason they did that is because that maximizes shockwave damage to people and dwellings, and also the radiation damage. They deliberate, that you notice the designs of the atomic bombs at Nagasaki and Hiroshima. They had radar sensors, so they knew when to go off, and they did it precisely where they wanted to do it to maximize damage and create firestorms over both cities. And apparently these bombs were so powerful, I don't think the ocean, at least directly beneath them, would have made much of an impression. And it created all this glass. I didn't show that, but big glass deposits are around these 2 sites. And the glass is not only like trinitite, which formed with nuclear bomb bursts above ground on Earth, but it's been etched with apparently nitric acid, which also forms in a nuclear weapon. So it's acid etched glass. You can read about that in the journal article about the glass deposits.
All right, I have a third out of fourth question. So many questions. Third out of fourth
One,
question.
by the way, one reason I published this is to prevent a nuclear war on Earth.
So
that's one reason I felt compelled to publish this.
Absolutely necessary. Correct me if I'm wrong. It also appeared as though, may not perfectly antipodal, but it looked like the 2 explosions were somewhat antipodal, like either side of the planet, right? Have you calculated how much off antipodal it was? Specifically, because if it took away the magnetic field, right, it wasn't just an EMP, it was something to actually disrupt the magnetic field of the planet.
Yes. It would have created destruction, not only to anything alive, but also the whole geophysics of Mars. I don't have the tools to actually model what the shock waves from these things were, but apparently they went off at the same time, and the shock waves wrapped around the planet. Now, the southern part of Mars is much higher than the north, and apparently that slowed down the shock waves. So they basically, they came together at a spot kind of more north than they would. It wasn't the exact antipode. You'd have to do the shockwave optics to see if that's what happened. But it is what looks like an antipodal, an approximately antipodal deposit. And by the way, they've seen that on the moon from impacts on the moon. They found a big impact that was recent, and they found that on the far side of the moon at the exact antipode, because the moon has only an atmosphere as soon as you get hit with a meteor. that you got a pile of stuff. Anyway, but that's and the same thing happened on Earth when Krakatoa went off. They tracked the shock wave like 3 times around the Earth just with barometers. The shock waves wrapped around the Earth, collided with themselves up in the North Sea, and then bounced back to Krakatoa and back and forth 3 times. Amazing. You wouldn't want to have been around Krakatoa when that happened either. But anyway, like I said, is this, I mean, I will make a confession. When this finally all sank into me, I wept like a child for about 5 minutes. But then I said, you know, Brandenburg, you got to get a grip on yourself. The important thing is, you know it now. You know, and I'm sharing it with you guys. Now we know that there are forces in the universe, apparently intelligent forces, that are capable of acts such as this.
Okay, and let me
Quite
see,
frankly, it looks like somebody made a radioactive pyramid of heads out of Mars, like Genghis Khan did.
So let me go to Michael. We'll do a question for Michael, and then I think we're at 5:48. So why don't we call it an evening at around 6? How's that sound?
Okay,
Pacific.
Tim, and thank you so much for the opportunity.
Oh, absolutely, John. It is a pleasure. It's always an honor to have you with us. It's such a pleasure.
It's a pleasure to be on your conference. Thank you.
Michael, you're muted, sir.
All right.
There we go.
Thank you. Yeah, thanks, John. Awesome talk there. So
I can send you a nickel. I can send you a nickel if you need one.
We have nickel here. We have everything we need. So
give it a shot.
Yeah, sure. So what I was going to ask is, just so to clarify the timeline, the xenon. So the xenon shows up after Mars loses its atmosphere or before?
Before. I mean, it's the xenon appears apparently about the time Mars lost its atmosphere.
Okay, so
they're coincident.
So
along with the neutron, it's all we know is the rocks that are young on Mars are full of xenon 129. The very old rocks don't have it.
Gotcha. So that would be the existing scientific model would work for that, but not necessarily for the other signatures of radiation on the surface?
No, the other signatures of radiation are also recent.
All right.
I'm talking geologic time. This happened before there were dinosaurs on Earth.
Gotcha.
There's only one coincidental thing that happened on Earth that is a little ominous. The Great Permian extinction happened at approximately the same, and that was the most severe mass extinction on Earth. It wiped out 80% of everything on life on Earth, especially animals with calcium skeletons.
Interesting, which would have been irradiated.
Right, strontium 90.
Mm-hmm. That's interesting.
And they have no. I mean, Chicxulub is well established now. It was just a big meteor impact. There's no radioactive.
Yeah, and in the fossil record on Earth, they say that the ratios of uranium to thorium in seawater also changed at that time.
Oh, in the Permian extinction?
Yeah. They claim that it's due to the hydrogen sulfide in the ocean changing the solubilities, but it stayed different. That's the weird thing. Even after the hydrogen sulfide was gone, or it might have been some other.
Yeah, if you could, here's my email. It's Space Ranger 137 at yahoo.com.
All right.
Space Ranger 137 at yahoo.com.
Tim's got it. I can just.
Oh, he's got, yeah. So
yeah,
if you could send me a link to that, I've become very interested in the Great Permian extinction because.
Oh yeah, and even before that, there's so when in geologic history did this happen on Mars in millions of years?
Approximately somewhere between 300 million and 500 million years ago, somewhere between half a billion and a third of a billion years ago.
Got you.
And I wish I could be more specific. The problem is the evidence from the meteorites was that lava flows formed and scooped up minerals on the surface and incorporated them into the lava flows. And it's the scooped up minerals that were on the surface, they show the neutron exposure, but the fresh lava does not.
Mm-hmm.
So it's very odd.
So on top of that, on a lighter note, perhaps, are you familiar? Yeah. Are you familiar with the Brazilian carbonado diamonds?
No, Brazilian diamonds. That is a lighter note.
Well, so they are from a region far away from other kimberlite pipes on top of a hill in sedimentary rock. And that sedimentary rock happens to be about 2 billion years old.
Interesting.
Interestingly, it's from about the time of the Great Oxygenation Event on Earth.
The Great Oxygenation Event, one of my favorites.
Oh yeah, so
I got an article. I just got an article accepted on that concerns the Great Oxygen Event.
Very cool. So what I was going to say is we got a close look on. Actually, it's on one of Jeremy's older videos as well. We got a close look at some of those carbonado diamonds, and they had acicular grains of what appeared to be titanium and other transition metals that would have been good nitrogen getters, and also just good strengtheners for polycrystalline diamond. So
interesting.
They look artificially. They look engineered. So
hey, once you can accept the idea that we're youngsters in the cosmos and we're not alone in the cosmos, all sorts of pardon this expression, all sorts of strange shit probably happened before we were around.
Oh yeah, deep time is as far away from us as deep space in a way.
And this place may have been a nice stopover. It's in a nice, convenient part of the galaxy. We may, in fact, owe a lot of our genetic heritage to shore leave by these astronauts. Some of these ETs, who the hell knows? Once you have intelligence as a factor, intelligent actors as a factor in our past, even the past before there were human beings, the possibilities just become.
Well,
the scenarios explode.
I would also like to mention the isotope ratios in Brazilian carbonados are extrasolar, so they're from some other solar system or some other region of space, possibly.
Sounds like somebody was emptying their waste here.
Well, I mean, if they're carbonado diamonds, it would have been good spaceship hull material. I was thinking it may. What I'm thinking is it might have been a terraforming probe that introduced photosynthetic life.
So, guys, we have,
all of these things are quite. I think we
could check it.
We should not dismiss these ideas anymore. If we're not alone in the universe, and the universe has been around for. The
universe.
What is the present Hubble time now? It's
13.98.
They'll keep pushing it back.
13.98 billion.
13.
Milky Way. The Milky Way, if I remember right, is
may have pushed it back even further.
Maybe more.
Yeah.
The Milky Way is 13.75 billion. Earth is only 4.6.
The age of the universe.
So
we're latecomers. We're latecomers in the galaxy.
We're new kids on the block.
Yeah.
Just like we have to deal with us present generation have to deal with all the history of the human race before we were born or even a twinkle in our daddy's eyes. The Earth has to deal with the history of this universe, which all occurred.
Mm-hmm. Yeah. And I mean, also, if we want to prove the thing about the Great Oxygenation Event, we can actually take blue-green algae and check for gene drives.
Look for those strombolites. What do they call those? Strombolites?
Stromatolite.
Stromatolites, yeah, they found stromatolites that are like, only a couple million years old, I think now.
Well, there's some alive in Australia, in fact.
What's that?
There's some stromatolites in Australia in some bays.
Yes, there are.
So anyway,
I'm aware of that.
Well, yeah, you take a look at those and you see if they have any gene editing in them, and then
Absolutely.
there you go.
There you go.
Yep.
All right, Michael.
Okay. Well, gentlemen,
Good luck
we're
with your
just about
experiments.
there.
I hope you succeed
Thank you.
amazingly. And you don't even have to cite me. If you do.
We will.
Just file a patent. Just file a patent immediately. Don't even mention me.
Whatever. It's no big
Whatever.
deal. It's
Guys,
no big deal.
let me give you all a wonderful good night. Thank you so much.
Thank you, Tim.
We have
this was an amazing conference.
Oh, wait, you got something?
Yeah, we got the oven open. I don't know if I showed, but yeah. So
can you do it in 2
does it
3
levitate?
minutes?
No, not really. So the first sample didn't have enough copper phosphide. Pretty sure about that. It did eventually get the right color, but it didn't really levitate or anything. There were a couple impurities that must have fallen in at some point that were just iron. Very obviously, just like scrapings from other stuff. We have one small piece of material that seems to move around when the magnets moved around. Looks like it may be either magnetic or diamagnetic.
Sure.
And this other sample that we just prepared, this was the one with the lead oxide and lead sulfate. We skipped the lanarkite step, and if we look inside there, well, I mean the pieces are tiny, but maybe I'll take some microscope pictures with Jeremy tomorrow or Monday.
Great.
But yeah, I mean, so this I don't know if I can.
Most impressive. Most impressive.
It's yeah. There's lanarkite there, so I mean, I'll obviously get better photos of it, but
Yeah, I know basically nothing about this new discovery.
Yeah.
Lanarkite sounds like a good.
Okay,
mineral
well,
name.
guys,
what I'm saying is you don't have to waste. Probably people don't have to waste the step making the lanarkite. They can just use the the lead phosphate and the lead oxide mixed with the copper phosphide at the start of it, and that should, fingers crossed, get the result. At least the addition of the copper phosphide does not prevent the formation of the lanarkite. So that's a good piece of information for people to know.
Okay,
Wonderful.
great.
Guys,
Yeah, Tim,
thank you again.
You gotta go, and
Have
I gotta
a
actually
wonderful
go too.
evening. This has
Okay,
been
you have a
APEC
wonderful evening.
over and
Great
out.
conference, Tim, and thank you for inviting me to present.
Thank you as well.
Thanks, John.
And
Thanks
check out the links. Check out the links. The articles are out there online. You can get them.
Mm-hmm.
Okay.